Oui. Ça serait bien. D'accord. C'est via le Livestream. Ouais, c'était comment encore de qui? Tim Betchley. Le nom de Tim. Ah, ok, oui, non, c'était juste comme ça quand je dans la liste. Merci beaucoup. Bon, bonne journée. Du coup, Lucas, ouais. Tu arrives avec la vidéo, je trouve. Ouais. Voilà. Quand même. Pour que celui-là en présentiel. Juste un truc pour faire la vidéo. Le micro peut être pour les questions aussi. Ah, c'est juste ce qu'il doit présenter.
Good morning, Tongyi.
Hi.
Hi. I think the session chair is still missing. Is that right? Or
I don't know if he's there. Let's see. Do we have Hunhai here, maybe, to comment about that?
Okay, I try to call him. Okay, try to call.
He's indeed supposed to give a talk, so.
Gianmarco, would you basically start sharing so that we don't delay too much, maybe?
Yes, but I haven't prepared anything, so
Okay.
I mean, I cannot show anything.
But there's no introduction, that's right. Okay.
Yeah, so I mean, you can simply skip the introduction, and so we can, you know, if we reach 9:15, we start with the talk directly. I mean,
Yeah.
I can introduce the speakers, and that this is what I can
Yeah,
do.
I think that obviously that's what I meant actually. Okay.
Yes. So we still have time then.
Yeah, please do.
Okay, so our introduction chairman is not available yet. So in the meantime, we will wait a bit. And in case it doesn't show up, I will introduce the three speakers of this morning session.
Okay, shall I say? Shall I start or not?
No, because otherwise we're going to be ahead of the schedule.
Okay.
We can
So,
wait.
okay.
I mean,
okay. I can wait. I can wait.
Manage
no
to reach? Did you manage to reach the?
Yes. We contacted with him already. Okay. He should be online soon.
Okay.
He should be online soon.
Okay, so let's wait then, and then you will make a shorter introduction then.
So maybe just a short explanation to those who are here already. So we will start in a moment, but the reason why we haven't started is that the chairperson who should introduce the whole session isn't there yet, but he will hopefully be there in a very moment. So we still wait for him, and then of course the three speakers are here.
The session chair is online.
Okay, so sorry everybody. So I'm very sorry for I'm late. So let's start the morning session on day 3. Okay, so today we'll have 3 talks in the morning. First talk from Professor Tongyi Zhang from Shanghai University. And the second talk is about Nomad, and third one is about AIDA. So I'm the chair of this session. I'm Yi Liu from Shanghai University. So I'm supposed to have a introduction in the first 15 minutes. So let me share my screen.
Yeah, for the sake of the schedule, I would propose that you don't take 15 minutes. Huh?
Okay. So probably just 5 minutes then. Sorry. Yeah, so probably very, very quick then. So I think so since time is a limit, probably I will skip most of them. I think the topic in this conference also most of us have interest in data-driven material science. So so data science is as the fourth research paradigm. Even it came late. Well, in my opinion, the data science centralized the experiment, theory, and the computation. Okay, so the data science can be used to understand both experiment and computation, and then can do prediction, therefore can design the new experiment and computation. Of course, also data science actually can derive theory by deduction or induction process. So it's even it came late. It's a kind of digital representation of human knowledge since the numbers was invented 1,000 years ago, but never accumulated to so big scale and never been so analyzed in a systematic way or statistical way. So I think that so the data science even came late, but it's important to different field. Also, I think I think another thing is as a material scientist. So not only we do the machine learning, we develop a very accurate machine learning model to predict properties accurately, but we also need to understand what's the physics of material science behind the machine learning model. So so that's why I in my language, so we propose we need to go from machine learning to learning from machine. So as a human being, we should be humble. We learn what machine learned, and then find a new physics, a new knowledge behind the machine learning model. I think that's also important. So in view of computer science, probably they call the model interpretation. Okay. Also, I think we have various data sources came from either public or private. We all learn many big database today, but also we should pay attention to the small data set in the laboratory, in the individual laboratory. Those are also important, should be analyzed and find useful physics. So of course, the NOMAD is a representation of a big data repository or database so far. And Professor Seffler and Jaxel proposed this push this idea. So basically push the idea of a big data driven material science. So it based on the collection of bigger computational data. Now we are having more experiment data, and so we can do a correlate statistical analysis, and eventually we will draw this kind of a map of materials. So I think that this gives us the new opportunity to do the new material science. But as a last sentence, I would like to mention, so in many times in material science, we don't have a big data. And the small data also important. How to find out the new physics of material science behind the small data? That's also a practical question and important. I think the first talk by Professor Tongyi Zhang will talk about this small data with a big noise. So I think that's also an important thing to pay attention. And so I think I used 5 minutes. So let's welcome the first speaker, Professor Tongyi Zhang from Shanghai University. So he's a Chinese academician. He's an expert in solid mechanics and material science. And he's leading material genomes and material informatics movement in China. So let's welcome. So I will stop the screen sharing. So please share your screen, Professor Tongyi Zhang.
Okay, thank you. I'm very happy to have the chance to share with all of you how to handle with small data and also big noise. So we all know the MDI is proposed by the former American President Obama. So the key issue is how to make the materials research use half time and at a half cost. So from talk about this data and the knowledge, the key issue is how we can gain knowledge from data. So now we are talking about machine learning, but actually, as I mentioned here, learning can be done by individual human beings, especially genius. And at the moment, of course, all and by machine that we should have joined. The human being, we utilize all the machine, software, computer to learn all the data together. So the learn's purpose is to understanding why things happened. This is for explanation. To predict what will happen. This is for predict. For the first one for explanation. The second one for prediction. And now the third one purpose is to manage things that are happening. This is for control. Now we have a lot of for those. For control the cars, airplanes, ships, and so on. So the development of nature science is continuous and endless progress that human beings observe nature behavior, develop learning models, and then gain knowledge. I put here Newton's figure here. So we all know the simple is Newton's law, F equal ma, is not derived. It's actually proposed by Newton based on his observation. It's not himself, it's all human being. Okay, we observe the nature behavior, then summarize them, then gain the knowledge. Okay, then gain knowledge. We use knowledge, we express the knowledge by using a simple equations. So data-driven the formula discovery, now we are also trying to develop some algorithm and our program to find the formulas. So we can see historically, most of the important is data and the formula mostly are data-driven. Of course, now as an expert, we can use expert-based formula discovery to gain that get some knowledge based on some principles. But here, at least most of them, they are really we get this from data. Now I put here as one example. I'm working on mechanical behavior of materials. So the major failure mode is a fatigue failure. So fatigue failure, there is a famous law we call Paris law. The Paris law for fatigue crack growth. So you can see that here is the vertical line, that is the crack is a growth rate. Now there is a stress intensity factor region. Then Paris, based on data, he proposed this simple equation, the power law equation. It basically is a power law. So now at the moment, the academic and also industry are widely use the Paris law, okay, in the theoretical study and also in industry practice. So another is also very, very famous is equation, especially in the metals industry or the materials community metals, okay, metal. That we call that is a Hall-Page equation. Now we know most of our widely used metallic materials is for structure. Okay, that's what usually we call that the structure materials, where the human being utilize their mechanical property in our daily life, industry, and so on. So there, the most we use that you see the metallic materials are polycrystalline materials. They are not a single crystal, not like in semiconductor, we widely use a single crystal. Now here is a polycrystal. The Hall and the Patch, those two scholars, they are individual developed, they found this equation. All the mechanical property will get better if when the grain size get smaller and smaller. They get this is purely from data. More interestingly, later on, the Hall-Page equation can be explained by some theoretical modeling. If they are based on the dislocation modeling, we have a different model. We use a different model, we can derive the Hall-Page equation. The Hall-Page equation is further, we have the equation from data. Then later on, we have the theoretical improvement. Okay, we can approve this equation are correct. So the entire metallic industry, what they are doing, they are doing is try to make those metallic materials, how to reduce their grain size. If they can reduce their grain size to lower than micrometer, then they have a super mechanical properties. Those materials will have that super material property. Except the creep, okay? If we want to design some materials against the creep failure, it is better still use the single crystal. But for other materials is mechanical properties, okay? They are also related to reduce the grain size, make the grain size smaller. The smaller, the better. Of course, now academically, we also have found if the grain size is too small, we call that a reversed Hall-Page equation. We are not talking about it because to make such so small nanometer scales is those construction materials is not so easy. Okay, now we are still the entire metallic industry is still working on this. Okay, how to make this D small, the grain size small. Now we all know that the AI, artificial intelligence, is a new powerful tool. So I draw these figures here. Now, no matter you work on which kind of materials, you have your so many different tools. That is wonderful. But now we would like you to learn another new tool to how to optimize, how to use this new tool, put this AI, machine learning into your toolbox. So the fast developed data science, artificial intelligence, machine learning, and the materials and mechanics, I call that informatics. Now we are widely known. So materials informatics is developed so fast. I see this milestone that is we call this AlphaGo. This is software. Okay, we all know that. One app software can be the champion, the world champion of game Go. Okay, so even you take a look at this one, the updated version they call AlphaGo 0. You read this is the title of this article. They call the mastering the game of Go without human knowledge. But before in the old, the original our system Go in that software, they have used a lot of the human beings' experience in their database. But for this AlphaGo 0, they only know human being only just teaching the machine what's the rule of the game of Go. Then the two machines, they will pick it to each other. Then finally, after they trained, then they can say the AlphaGo 0 software will win this is the old version. Also, I like this is a paper. I like the title. They call Lessons Learned. This is talk about this medical doctor. Also, skin. You say that a medical doctor how to diagnose this skin, okay, the human being's skin. So if you read this paper, then you will find that they have a very large database. They all pictures about the human being's skin. Okay, then the medical is a doctor, the skin doctor. When they diagnose that, they say your skin. When they treat that, they convert that to a imaging process. Okay, they just make a comparison. Okay, then they will know what kind of your skin has which kind of problem. Then they will give you a medical treatment. So I also like this one. This one is they talk about the learning from failure. Learning from failure, they talk about this article, talk about they want to synthesize some materials, okay, some materials. Now, sometimes they are successful, sometimes they say they are failed. They want to find at which condition, what's the boundary between the successful and failed, okay? So if you want to say, find this boundary, so you need the data of the failure data. So to data sets or you only data I will talk about is whether your data is reliable or not. Without not means is well, we are not separate successful data or failure data. We are more focused on whether your data are reliable or not. So this is a new article. We talk about as a title is mentioned. This is a mobile robotics chemistry. So that is our goal. As I will mention that now currently we do adaptive design, but actually it's not a cross loop. But in this article, they talk about how to cross loop to do this materials development. So inside here, they have a lot of machine, they are the robotics, okay, big one and the small one, okay. Those then you give them a recipe, then they will fabricate this materials. Then they will testing the materials. If they are not successful, they will recommend what is the next recipe, or they will synthesize. Okay, what's a new materials for the new design? Okay, we will mention that. We will try to develop all the similar this lab at the Shanghai University, but we are still working on this. So now this I just mentioned. Okay, now we are in materials community. I call that materials informatics. I also working on the mechanical behavior of materials. So I also in the mechanics community, I can call them mechanics informatics. Okay. The materials mechanics informatics actually integrates artificial intelligence to material science and engineering, or maybe to mechanics. Okay. This will show that it's adaptive materials mechanics is a discovery. So here is in the center is a domain knowledge. No matter you work on which kind of materials, so your knowledge is extremely important. It's a harbor. Okay, it's really the harbor, the domain knowledge. But in addition to that, we are suggest you to do a data driven, to have the database. Of course, you have your goal. Then those data should come from experimental or competition. Okay, that is we are very, very important. Okay, where those data can come from experimental or computation. Once you have this data, you will do a data pre-processing, then do a build up a machine learning model. Then you have to evaluate this model. Then based on the model's results, you will make a suggestion. What's the next experimental or computation? What I should do? Okay. Now, based on those recommendation from the machine learning model, then you will carry on the next round experimental or computation. Then if you reach your goal, then you will come out. If not reach your goal, then your data will be put into the database again. Then you do this iteration, you do the iteration. So because our goal maybe change. This year, our goal is at this level. Next year, we should put our level is higher. So this one is a dynamic. It's never end. It's a dynamic, never end goal. So let's talk about this a little bit. Is machine learning. Machine learning usually talk to those computer scientists. They will tell me, okay, those they treat that system as a gold black box. So they have input variables, they have output. Actually, the output variable is actually you privacy, you should know that. Then I usually say as machine learning says that's estimation. I put a hat there, okay? But anyway, so there the key issue is you have 100 is a variable. You have a lot of there is a wrong. I should put it. This should be H. I'm sorry for the mistake. So there you have 100 variable. So those 100 variables make those have an intrinsic area. They have an intrinsic area. Here, there's some people tell me to the stock market, the intrinsic area is very, very large. Okay, they could be reached 200%. But we are do science and engineer with well-controlled experimental computation. Then we can make this, I said, approximately equal to 0. It's not that really case. So we can make it as small as possible. We try our best to reduce this area. Okay, to reduce this area. So there is a big difference. So in my whole life, I'm working on something is really true or not. We believe something, okay. But in machine learning, it's not that case. Machine learning believe the real function, you never get it. You never know it. Only you can get is optimal, is a possible, is a approximate is a function. So there are so many possible approximate functions. So machine learning's job is try to find the optimal one. Is try to find the optimal one. So therefore, they have a bias, they have a variance, okay, and this is a simple equation. Tell you if you make a bias area higher, then the variance area will get smaller. So now they have a bias variance dilemma. They have a variance. When I talk about the students, I mentioned that, like you say, a student want to make a boy or girlfriend. If he just want to make that is a friend in his or her classmate among his class. Now the advantage is the information is sufficient. He know all the classmates in her or his class very well. But the problem is he may not find his or her girlfriend or boyfriend in just the class, okay, the classmate, among the class. So that have we get the search space get larger, okay? Maybe it's the entire school that get larger. When you get a search space get larger, the problem is your information will get smaller, okay? That's what we call the information entropy will come in, okay? Very, very important, okay? So that's why they have the bias variance dilemma. So how we do that, okay? But usually what they say there are difficulties. The data is smaller. Now I will specifically mention that how to handle. They have two different types of small data. I will say give more detail about this. And also the influence. Okay, there are so many factors we call feature. Okay, maybe some are friends call descriptors, attributors. To me, I think they are more or less the same. Okay, so I just simply call them features. Okay, that is an influence. Okay, factor. So they are high dimension, very high dimension. And also the noise is big. What means the noise big? To me, I just want to mention the noise big means if you repeat to do the experiment, okay, their experiment scale is big. That is a big noise, big noise. So now we are handled with data. We are handled with data. So they have two critical issues. One is how to select this is a feature. Okay. Another is how associated with this is how we decided to a large space we will do our search. That is another is a feature space. So keep that in mind. Now we are handled with data. The solution usually is not unique. Okay, you can find a different is a model, the machine learning model that feed those data perfectly. Okay, so you have to keep that in mind. So now we talk about those small data. Here, what I mean is small data. They have two kinds of small data. The first one is I schematically show here. Okay, the number of repeated testing is not enough due to greater scattering in the experiment results. So therefore, the mean of the repeated testing results is not statistically reliable. That is the problem. Okay, we do a summary. Just say where we do experiment, you just do a summary actually. If you are ordinary, that is the greater scattering. If your number, of course, if from statistical point of view, if you are some number approaching infinity, that's always true. But we cannot do that. We always handle small data. Another data is just they call, actually this is widely called, that case is a sparsity data. That is in machine learning. For this one, we do have some approach we can handle. The approach usually we call is transfer learning and so on. How to enhance those data. We have so many different technologies. Machine learning is algorithm to handle this. Okay, so this one, even though data is smaller, but they are reliable. So that is easier. Okay, that is to me is relatively easier. Okay, the challenge is if their data is not reliable, what can we do? So now I take one loop, one approach. This is by my friends, is Professor Luckman. So this that is Professor Xue Dezhen, is Professor Luckman is a former student. Now there is a published that paper. So their goal that they propose the adaptive design. The goal in this is an article talk about how to make this delta T small. Okay, how to make this delta T small. So they have originally have 22 initial data. So now there is they take that is 6 features. Then their search space is roughly 80 100,000 alloys. That is to me that is very big. The search space is too big, but because the initial data, the number of their data is too small. So then every time they can suggest to do another 4 experiment. Okay, they can go into that. They do an iteration. So now in the lowest is in the 6th iteration. We found that is the lowest one, delta T. That's in their supporting information. Okay, I copied here. So I said, okay, maybe we can do in a different way. I take all their data. We also put some constraint. We put some limit. We said that we already consider that it B2 to R phase transformation. We are not calling this other types of multi-cyclic phase transformation. Okay, now in this way, we reduce this, we move this 5 data out, then feature we just use the element. Okay, we use the 3 alloy element. The target is the same. Further, I do is a decision tree. Okay, the purpose to do a decision tree is try to reduce this search space. It's reduce the search space. That is the original one. So I put the delta T should be smaller than 4 kelvin. Okay. Now then if that one we get this, we do that. Then finally we will get this. Okay. On this is a leaf. Okay. On this, then we have a totally have a say 35 data. Okay. Then in the 35 data, you can see that the gene index is decreased. Then that indicates the information gain. So inside the 35, we see data that have one data, I call that outlier, that's very, very high. Okay, we have to especially say attention to put on this data. Maybe they have some new mechanisms behind that. Maybe their experiment have not done so well. Okay, so they keep that in mind. So I just remove for the time being. Now we do this similar, we use same machine learning algorithm. So that is the published is in their paper. So that is the predicted number. That is their actually experiment is measured. I use the same machine learning algorithm. We can predict another 5. Okay, actually the predictions is delta T is lower than their predictions delta T. Okay, that's just one of the example. Another challenge is this. Okay, we want to show you the same data can be explained by different machine learning model, not just by machine learning model. Actually, they can explain that can be fit by different theoretical model. So that is the model, the formula proposed by Marshall and Law. Okay, both are my very close friends. Okay, we are all working on some mechanical behavioral materials. So that's why I propose another model. From the equation, you can see they are totally different equation. Okay, I use the same experiment. Okay, the same experiment, but the plot is one you based on this is the equation, another based on another equation. Then from the data fitting point of view, from the fitting, you cannot tell which one is better, which one is worse. They always fit perfect. Okay, so keep that in mind. Not machine learning can give you different results. Even you do a theoretical study based on your different assumption, you also can get different results, a different formula. So keep that in mind. There are another example. So this is an equation. Now they are all from my this Bernick's, very famous is a professor at the Stanford University. Another Professor Gao. You're also working in Germany, probably in Max Planck Institute. So they propose that is a famous equation, and based on this equation, they developed the string gradient plasticity. So when I see they are working on this small one, at that time I said, maybe I should do something. So I propose another equation. You can see the equation looks also different from their Professor Nixon and Professor Gauss's formula. Okay, that's my equation. So now I ask my formula students, this is Wei Hua Xu, I ask him to collect all the data available at that time. Now here are just a few of them. One is fit by this equation, another fit by this equation, the total equation. Okay, now you can see that. So from the data fitting, you cannot tell which equation is better. Okay, they all develop that equation based on different theoretical assumption, a simplification. Keep that in mind. If you do a survey, theoretical study. Okay, so that's just want to tell you. If we do a data, okay, driving the formula development, if you get more equation, not a surprise. Okay, so even though you do a purely theoretical study, you could go maybe also get a different equations. Okay, keep that in mind. So now I come to this one. So this is actually one of my friends, it's Professor Badak from Northwestern. It's a very, very famous scientist. And Professor Hu from Australia. Now they argue to each other how to about this is this size dependent. Okay, there is actually Badak, they have the classical work on size effect. Okay, in fracture mechanics. So basically, when the size gets small, we think that is strings dominant. When they say size get bigger, I believe that there is a fracture mechanics will come in, okay, to do the prediction. So that is this very classical work. So the who are the one they also they call that the boundary effect model. Okay, when they say put this is a problem to me, they ask me to judge which one is better. Okay, now I'm doing say machine learning. I said, oh, I will not personal, I will not do anything like a machine to do it. So I do a machine learning. We use that is basically talk about 3-point banding. 3-point banding, this is how to is experiment setup. That is there they have a pre-notch. They have this is sample size. They also have this height. Okay, we use all the data is from say Professor Badak's data. That's you can see that is a small sample. This is a bigger samples. Okay, they have a really a size effect there. So and also the notch is nominated by that is by this W by the height. So we use the alpha. So you can see that this experiment data. Even though you can see that this repeater, that is the number of repeater testing is not so small. But however, the congregate just so the data scaling so big, okay, so big. So now if you based on say linear fracture mechanics, then you should suppose you should get this. It's not you not satisfy this. Okay, based on this, I said I put that is the common sense. We all know that. Okay, because the data is small and the noise is big. So we put a say here, we all agree. Okay, the standard derivation does not follow. Okay, in the common sense, the possible is the bigger defect existing. Okay, and so on based on this. Okay, so I put a say 4 hypotheses here. That is the larger the congruent sample size is, the lower the strength will be. The larger the congruent sample size is, the smaller the variation will be. The deeper the pre-notch length is, the lower the strength will be. The degree in data scattering should be decreased with the increase of pre-notch length. This is a hypothesis, okay? Because you take a look at their data, they don't follow this. They don't follow this. So therefore, I use the power law, a normal distribution. Okay, that's the simplest one. We use the power law and the normal distribution. We link them together. Okay, link them together. Then from here, because this is small data, you don't know there is a distribution. How the advantage when we propose this, the link together normal distribution, okay, with this power law, then we can, that means when we determine, for example, determine this is a probability density, we have used all the data, okay, including the different density sizes data. We will have used that. So that's why we can distribute, okay, their normal distribution, what's going on. Then we can determine this. All those is those that we call that is those parameters we introduced. We determine that based on the data, so we can determine their value. Okay, we can determine their value. Then we also can put the size pre-notch length dependent. That is a normal distribution model. We'll do the same thing. Then we can use the statistical testing. Oh, sorry for there are some is a Chinese word. Okay, but it's just statistical testing to say whether we accept that or not. So then we also do that is so finally we can say found the where model is really statistically accept is 2 data. Okay, we put is highlight in red. Okay, highlight in red. So now once you have this distribution, then you will see know what's the really the value at 1%. Here it's 1%. Just you can take it. You if you think it's too large, you can put it 0.1%. So failure probability in the congruent strings. Okay, then you can put it there. Their behavior is really like this. Okay, then you can put the probability. Once you know that, then you can always do it. So now the fracture properties, they have two. One we call it in fracture community, we call K1C, the fracture toughness. Another, well, those is a crack propagation in front of the notch. They have a fracture, is a property. They have the fracture processing zone. Okay, what's the size of the zone? So we use this finite element to do a calculation, calculate the stress intensity factor. Then we put this is the fracture processing zone. Then because we argue the K1C fracture toughness is a materials property. It's a constant. They're only related to materials. So we put it there. Then we conduct this way from the finite calculation. We have calculate the stress intensity factor. Then with the experimental data, we can determine what's the fracture toughness and what is the cracking processing zone size. Look at the delta A we introduced. Okay, so this the results seems pretty good. Okay, this emphasize that. Okay, the concrete remarks how do machine learning small data with big noise? To me, it's still a great a challenge. Okay, I hope it's more of our friends or colleagues worldwide that they can pay more attention to this. And in my personal opinion, integrated domain knowledge with machine learning is the best approach. Okay, thank you.
Okay, thanks, Professor Tongyi Zhang. So we still have a few minutes for the questions for this talk.
I don't see any questions here in Louvain. Is there anyone in the online audience?
Well, I don't have a question, but I do have some comment. I think Professor Tongyi Zhang's talk actually addressed the issue. So in material science, in many researchers' own lab, so it's very often we have a small data, especially for experiment, right? It's because material data, experiment data are generated. It's very expensive, right? So, but now we have this data science concept. So we need to rethink how to deal with this experiment data using the data art, data science, or this big data tools, or even small data tools, because they are. These tools are not familiar for material scientists before, actually. So I think that's also direction or something we need to think in the field. I mean, not because the big data is still, not available to everybody or still ongoing. But we still, I think that there are rooms to find the power of statistical analysis for the small data, and that will benefit the material science. Well, that's my personal comment.
So should we put more emphasis on this in the education as well, in let's say how we educate our undergraduates?
Yeah, so I think it's important to tell the student. So for example, we are also teaching material science student. Now we emphasize a lot about this data science. So about machine learning, data mining, etc. So tell them this is really independent, important tools you have to learn and use in the future in your own material science research. So I think the students should learn this as a basic tools, just like computational tools or experiment tools. So data science tool is new independent tools. Still, I'm not sure the other place, but in China, my personal experience, still people kind of mix computational tools and the data science tools. They think they are the same, while they are both use computers for sure, but they don't do real experiment, but actually they are different. So we know. So I think should educate people learn more about the data science. They do have independent tools, concept, and application cases. So yeah, so education is still needed and for the material science. And if I add a little bit more comment, I think one example Professor Tong Yi mentioned is noise. So in experiment data, there are a lot of errors. There's noisy data. So these errors, well, it can be enemy of the data science, but sometimes may be useful. So how to deal with this is a common problem, noisy experiment data. So how to handle this from data science point of view. I think recently, as far as I know, Professor Xue in China, he used this error, put this error into the data analysis and make some progress. Personally, in my personal group, I also try put this error back into the feature as input to the machine learning model, but it turns out it's not successful. But we are learning things. I mean, we need to learn the nature of the data and to see how to deal with this sort of things. Okay, that's my comment. So, so then my point is, so we are, I think, as material data, we are facing challenge from not both big data and small data. Because for the small data, even more challenging because we don't have many data. Then how can we dig out useful information? I think that also rely on the advanced algorithm, also domain knowledge. We need to input the domain knowledge to expand the value of the data. So it's not just the number, so the size of the data, also the quality, and also how to take good advantage of limited data. I think that's also sort of things we need to address, also pay attention. Well, this is my personal opinion.
Another issue, okay, maybe should try more attention, all yours attention. So we usually do is no matter you do is more physical oriented, chemical oriented, maybe like me, mechanical behavior oriented research. So in our research, in my half is life, maybe most of life is research, I really believe with the model I developed. Okay, we think that is always true because based on some assumption, we say I love the formula I developed, I derived. Okay, so I want to try my best to argue my model is correct, my theory is correct. So in that sense, that means I'm very biased my model. But from the data science point of view, that is not this issue. The data is machine learning, as I mentioned here. They're assuming there's a big assumption. They're assuming the true, correlation is not available. All you can find is optimal approximate a formula, a correlation. No matter it's analytic or non-analytic. Okay, that is the approach somehow are different. Okay, so now we are all working in this area. We have to pay more attention to this issue.
Okay, so now I think it's time for the next talk. So let's thank Professor Zhang again. So let's move on to the next talk. It will be given by Marcus from Berlin. I think he's going to talk about Nomad, which is a big data platform. So Marcus, please share your screen and start.
Yes, hi, good morning. Yeah, thanks for the introduction. I hope you can all hear me well. I also hope that you can see the slides properly.
Yes, I can see and hear.
Okay, great.
Yeah, please.
And just to confirm, I have 45 minutes to talk, right?
Yes, yes.
Okay.
Including discussion.
Okay,
and we have a
see.
30 minutes discussion at the end of this session. So,
yeah, that makes sense.
Yeah.
Okay, thank you very much. Yeah, yeah, thanks for inviting me. Yeah, I'm here to present Nomad, which we call a fair data sharing platform for material science. And yeah, material science, those of you that know Nomad, you know, it has a very strong focus on electronic structure simulation data. But this is also why I wanted to talk about FAIR-MAT. And FAIR-MAT is an NFDI consortia. In fact, we are starting with tomorrow. Tomorrow is our official start date for this project. And the goal of FAIR-MAT is to bring data sharing to a wider material science community. And this is where we want to use our Nomad software, our experience that we take from DFT simulations, electronic structure codes, and offer this to the whole community of condensed matter physics. So, yeah, I want to start a little bit with like a high-level overview, talking a little bit about what Nomad actually is. For those of you that don't know it, and then I want to also do the same thing on FAIR-MAT, and then I want to go a little bit more technical and explain to you how Nomad does work internally, what architecture we use, how it's operated, how does it work, how could you extend it or use it for yourself, all these kind of aspects. And then hopefully in the second part, I concentrate more on an idea that's the Nomad Oasis, which is the idea that you can use Nomad also locally in your institutes. And this is also what we want to use in FAIR-MAT mostly, to build really a federated network, a federated data sharing network where everybody can participate and we basically distribute the data over the globe, and thereby making it fair and accessible to everybody. Yeah, so that's the plan for today. So yeah, let me start to hop in and talk a little bit about what Nomad is. So we characterize Nomad as a fair data sharing platform for material science. And here we have two parts. The first part is the data sharing. And we think that data sharing means, and this is in contrast to many other material science databases that you might know, that we are not hosting our own data, right? We are really there to share the data that others provide to us. So the goal is to make your data, the data of the regular researchers, available to others. So that's the fundamental thing of our platform. And the other part is the material science part. And this means, and this is also in contrast to other platforms, like where you are more about generic data sharing, when you think about Zenodo or when you think about Google Data Search or these kind of things. What we want to do is really to be domain specific. We want to extract rich domain specific metadata from the files or from the data that is provided to us. So it's not just about identifying the author and the title and abstract and stuff like this. It's really about digging into the data and finding out what are the specifics. What is the chemistry? What is the concrete crystal system, the structure, whatever that was measured or simulated? What are the parameters used? What are the material properties that were calculated or that were gained by any other means? And currently, Nomad is mostly about ab initio calculations. But of course, and this is where FAIR-MAT comes in. We want to extend this. We want to also open this up to experimental data, to data from synthesis, from data on different scales of computation, material science, and so on. Yeah, and Nomad, in Nomad, all the data is visualized. It can be downloaded, it can be browsed. We have like a search interface. It can be browsed in a common format with a common schema. It has a graphic user interface. It has an API so that you can work with the data programmatically. I have a few screenshots here. The first thing that you see is like our search interface, for example, and then you see like the visualizations, the overview that we have for all the data in there. Then it really depends on what data is about, right? So you see different charts with different properties on it. We also have like this detailed view, the archive, where you can really see all the different numbers and data points that we identified in the data that was provided to us. This is what like later we will talk about a lot about the archive and how it works. And we also have like an analytics platform, like Jupyter notebooks that are run directly on our servers that you can use to access the data and to do some analysis on it. And then there's the whole data providing part, right? So it's a publishing platform. It's really about like people giving us their data or share the data through the normal platform. And we allow everybody to have a simple process of uploading their data. It's completely free. Everybody can publish their data. You can have an embargo on your data, to assist the publishing process. You can get a DOI on your data for your papers for referencing, and then you can share your data with either in private with reviewers, for example, or with colleagues, or like public with everybody. Yeah, that's the whole idea about Nomad, right? To summarize it a little bit. You could say that Nomad is there to assist the overall research process. You basically want to do the same thing that the publishing world is doing to papers, we want to do for data, right? So we want to enable everybody to publish their data.
Your audio is currently stopped, at least in our place. I'm not sure.
Okay, let me check.
We're back. We're back.
Okay. I hope there will be no more interruptions. I have no idea if this was on my side. Yeah, we will see. Let me know if anybody else can't hear me. Just let me know. So where? So yeah, basically we want to do like this publishing game, but with data, right? So it starts with data on your hard drive, and then we allow you to upload your data, and then we allow you to publish your data, and then you publish data that everybody can see. That everybody can explore through our search interface, that everybody can have a look at and see visualizations of data. And then, of course, you can analyze the data with services that we provide. And then the cycle closes, right? So you get inspired by other people's data. You want to reproduce their findings, or you want to do similar analysis or do similar experiments or whatever. Then we are back to you and the data on your hard drive, and the circle begins again. So that's like the overall picture, like having Nomad as a set of central services, like a web page that you can go through and that you can put your data to, that you can also use to see what others have put up there. And then there's this other idea that I briefly mentioned in the beginning. We could also allow people to use the Nomad software, locally and have their own Nomad, right? Why not? Nomad is just a piece of software in the sense that we run on our central servers, but in principle, everybody could run it. And this is what we like to call the Nomad Oasis. And here the same thing applies, but you have like shorter cycles, right? You can upload data to your own Nomad. You can share it with your colleagues in your institute. And then, of course, at some point you can say, okay, my data is ready now. I want to publish it and move it to the central Nomad. But even with your local Nomad, you can do the same things. You can use the search interface to explore the data that's available at your institute, that your PhD students were putting in or whatsoever. So the idea is like you never really lose the data of some PhD student left your institute or that left your group or something like this. And of course, you can use all the analysis tools that we have. Yeah, so that's the other big idea. Like besides having like this overall publishing, we really want to make Nomad available for your daily work, right? Have it at your local institute, and really use it to manage your data. So it's not just about publishing it after the fact, after you're done, and basically you're just about like to write a paper and then publish it. But even in between, for all the intermediate results, it might be a good platform, or a good useful platform for you to just manage your data. And this slide I wanted to highlight a little bit that Nomad is not alone, but it's a large ecosystem of similar projects or related projects that fulfill like different tasks or that have different focuses in this whole thing. I put Nomad in the center. You don't really have to read everything. I try to highlight a few things where we differentiate from our colleagues. So one set of very similar things are all the big databases that you know, like something like the Materials project or the Aflo library, stuff like this. They have like these high throughput workflows that constantly produce new data, and then that they show with a web application, right? So they also have like a search interface usually, and you can see the data and download the data and do something with it. The big differentiator, of course, is that Nomad tries to be a platform where everybody can put their data. It's not just about our own data, and this comes like with unique challenges, right? When it comes to like curating the data and taking care of data quality and stuff like this. Then, of course, there's this whole realm of having methods that provide data, right? Having electronic structure codes that allow you to do simulations, having workflows that allow you to do lots of simulations at the same time, but also look at other branches of material science, like instruments and electronic lab notebooks and stuff like this. Like there's the huge amount of projects that produce data. And with these projects, also there's a huge amount of data formats that need to be supported. We will talk about like data formats and how to convert them and how to find metadata later in the talk. And then there's this whole other side of databases when you think about having just general databases or having something like Zenodo where you can share any data, right? These very generic platforms that allow you to basically put up data, get a DOI, put it in your paper, and then others can download it, which is fine, but it has like on the negative side, it's really hard to identify data or to find the exact data that you want. Like if you ever try to use Google Data Search and try to find like a simulation for a specific system that you're interested in or for a specific material, it's not easy to find anything in there because like the only thing that Google indexes is like the titles of people that gave people their data sets and stuff like this. And then, of course, we have all the research networks like the Deutsche Forschungsnetzwerk or the European Open Science Cloud or these kind of things, which are more like political initiatives, but where it's all about like connecting the dots and having databases interact with each other. And this is where FAIR-MAT plays more like an important role for us. Where we want to use the Nomad software to build like a larger network of connected repositories and also connect to other repositories out there. Yeah, so that's the, and yeah, one last thing I wanted to mention is standards, right? Data formats, of course, are tried to be standardized when you think about something like Nexus that you might have heard of. But there might also be in the future be standards for like larger schema efforts for like having joint ontologies like the MO for material science, for example. And then there are API standards. One thing that a lot of us are working on is the Optimate standard for having like a specific standard for an API that allows you to connect to material science databases in a common way so that it's easier for you to use multiple databases at the same time. And this also makes it easier for projects like FAIR-MAT, for example, to connect databases because it's much easier to get data in a consistent form, to retrieve data or search for data in a consistent form. Okay, that's what I wanted to say about like, the related work and the related stuff. Some of it will come up later again. Let's continue with talking a little bit, or first summarizing a little bit Nomad and then seeing how it plays into the whole FAIR-MAT idea, or what FAIR-MAT actually is all about. Yeah, so just to summarize, like Nomad at the moment is a set of central services. There's a website you can go to, and then you can basically do all the stuff. You can take your computational material science data, zip it up, and just upload it to Nomad, publish it. And then others can see what you have published, right? There's a search interface, and then there's means to visualize and analyze the data. And this whole software package, in principle, could also be run on different servers, right? That's the whole Nomad Oasis idea. And this is what we want to do with FAIR-MAT. Yeah. And the reason is like Nomad is like already a long-running project, and we have like quite some experience with dealing with metadata. And even though it's like focused on a specific domain of materials, but we really want to bring this experience then also to the other domains. So NOMAD was like a little bit of history. NOMAD was created like almost like 7 years ago. And by now we are accumulated like over 11 million code runs that were basically published on NOMAD. We have like over 100 terabytes of raw data. That's like all simulation input and output files. And if you calculate all the different quantities that are in there, like all the systems that go in there, all the elements that go in there, all the energies that are calculated, and everything, will come up to like over 7 billion little pieces of information that are in the database. We support over 40 community codes, so almost all electronic structure codes you might find are supported by NOMAD. And all the data that we have made up from or was provided from over 400 researchers from all over the world, including 3 of the large high throughput databases, OQM, Diaflow, and the Materials project. Around 250 users daily reach our website and use our service in some capacity. Yeah, and now in FAIR-MAT, we basically want to do the same thing, just on a larger scale. We want to use the NOMAD software. We want to still have like a central kind of installation. But now that we are looking into like different kinds of material science, it might not work this way in all cases. Like, for example, we imagine that we have institutes that run experiments that produce like a large amount of data. Data that's so large, like when it goes into the terabyte or petabyte regions, where a centralized idea isn't just working anymore, right? And we really need local repositories, or the institutes really have to take care of their own data. And this is where the idea of the Oasis comes in, right? So people, institutes could run NOMAD software in their own institutes, and then we just have a connection to the central system, right? And the central system then more acts as a central search index, so to speak, like the Google for material science. So we only transfer some of the data, we only transfer the metadata to the central system, and thereby allowing to publish the data, or at least publishing references to the data, while the data stays at the local institute. But the central installation will then make the connections that allow people to reach the different installations. And then we have to accommodate like certain different scenarios that we might expect. So other institutes might have like a different thing where they already have like existing data infrastructures, they already have existing repositories or ways of means of managing the data. But we still think that the Oasis can be an important role, and then basically be put on top of it as an interface, basically to allow the connection to the central servers. Or we might have institutes that run like larger laboratories where lots of instruments need to be connected, where electronic lab notebooks come into play. In essence, just a different source of data. And again, we think that we can use the NOMAD software as a local repository. But there might also be institutes that say, okay, the NOMAD Oasis isn't really working for us. We need like a different set of features. But then still, through API standards and stuff like this, we are striving to make a connection and to allow to index this data on our central installation. Yeah, that's like the overall idea. We really want to build like this network of repositories. And in order to do this, there are like certain tasks and challenges that we have to address. Like the biggest one, or one of the biggest one, and I think that was also discussed here at this workshop in some detail, is like metadata. How to define the metadata, how to align the metadata, right? Different methods mean different metadata, but somehow it has to put together. So that's one big part of the FAIR-MAT project, dealing with metadata. Then, of course, all these repositories have to be established, right? The NOMAD software has to be further developed. It has to be adapted to this Oasis use case, and then we really have to build these local repositories. Another big challenge. And in FAIR-MAT, we basically have 5 bigger experimental methods on board, or institutes that represent these methods. This is basically what we want to start with, and then lead by example, and then hopefully connect to more and more institutes and to connect to more and more different methods. By the way, do you see the map of Germany in the background? That's just because, like, at the moment, NFDI is like funded by Germany. But of course, all these ideas should apply to the whole world. And yeah, another thing is like the central thing, right, which we in the context of FAIR might like to call the portal. And this is where all the data becomes fair in a sense, right? This is what makes data findable, what makes data accessible. That's the central gateway that everybody goes to actually reach the data that might then be stored in different repositories. And then, of course, there's lots of efforts when it comes to connecting everything. Like we really have to see this as a connected network, and not an isolated network, right? And then there's also efforts to connect this to like larger research networks, like the Deutsche Forschungsnetzwerk or the European Open Science Cloud. And of course others as well. And then another big point in this whole FAIR thing is like electronic notebooks and laboratory information systems, like local IT infrastructures that already connect laboratories and the different tools and instruments that are used there into each other, which is like on a local scale, very important for us to integrate the data already and provide metadata in a sensible way, so that it's not just about like singular measurements, but really about like whole experiments and workflows and stuff like this. Yeah, this is a little bit what we plan for the FAIR project, or what the different focus areas are, and how the overall architecture that we envision should look like. And for us, the important thing is to really have this like a connected network and reach out to the community and basically make people work together and build this network together in order to have to finally have a way to really make the data reproducible, to really share the data, and not just having papers where we write about your data, but really make your data available and make others help others use the data. Okay, that was my high-level overview about everything. I took quite some time on this, but I think it's important that you get the picture. I will increase now a little bit in speed to get some of the technical ideas out. Yeah, how does Nomad work from a user's perspective, right? Yeah, it starts all with the files that you have on your computers. Like imagine that you have done a few vast DFT calculations, for example, and you want to publish them. Typically, what our users can do is they just take all the files that they have as they are, they just put them into a zip archive or into a tar file, and then they just upload it to Nomad. And then on our sides, we basically extract the archive. We go through everything that you provided, all the files that they are there, and we just try to look for files that we recognize. And this is what we call the main files, right? To each file that we recognize, for example, the VASP1 XML, something like this, will then represent a new entry in Nomad. And then that entry might consist of more files, but it's the one is the main file, and then with like auxiliary files or your input files or other files that you generated or files that you just put into the same directory. This is what we call auxiliary files. And then we put our parsers on the main file. Like for each of the different codes that we support, we have basically a parser, and then the parser digs into the file and tries to find all the information and to very fine detail. And then it transforms this information, this data and metadata, into a common format that we call the archive. So each entry will get one archive, and this archive provides all the information about the applied method, the studied system, the calculated properties, and more, and everything under a common schema and the common format. Entries for similar systems are then aggregated into materials, and this is what we call the Nomad encyclopedia, where we basically collect entries that are simulations that were done for the same material, and provide them in a way that you can see, okay, for this material, these and these kind of information were put together. And all the data, all the raw files that were provided, the archives, the entries, and the material data is all available through our user interface, but there's also like an API that you can use to work with this data programmatically. And we also provide a Python library that you can use to like easily use this API to get the data and extract certain archive parts that you like for analysis, for example, in your local Python environment. Or you use our analytics toolkit where you can run the Python directly on our servers. Yeah, let's talk a little bit about the archives. So, because these are really important for us, the Nomad archives, our common file format is the basis for everything. It provides the necessary metadata for our search system, for our representation and visualization in graphic user interface, for the encyclopedia, and also for analysis. This is what the typical archive looks like in our user interface. The archive is basically a structured format. It's hierarchical. Everything is structured into sections. Sections can have subsections. It's like a book, basically. And then sections can also contain quantities, right? Like the actual data. So in this example, for example, we see like a typical archive for a simulation run. So we have something like the section run, and then the section run is subdivided into a section method where everything about the method goes, a section calculation where the calculation results are going, and a section system that describes the system that was simulated. And then in this example, if we dove into the system, and you see all the quantities that make up the system, like all the site positions and the atoms there, and what the lattice is, and all these kind of things. So you see some visualization of the system here, and then I highlighted the lattice vectors, and you see like a mathematical representation of what the lattice vectors typically look like a 3x3 matrix and stuff like this. So this is like our archive. Like we really try to dissect all the information and provide it in this hierarchical form. Yeah, let me skip this a little bit. I think you're all pretty much familiar with this, what data and data schemas and metadata are. Let's talk a little bit more about like how to homogenize like heterogeneous data or metadata. I use like different colors and different symbols here to represent different things. So when you look at a structured metadata file, for example, there are two things to consider. One is like the information inside that might be heterogeneous. One method like really produces completely different information from another method. Like a microscopy picture is a completely different thing from a DFT calculation. And then another thing, this is what I want to represent with the symbols. And then another thing is the colors, because like the data format, right? JSON is different from HD5, and then ASCII is different from XML, and these kind of things, right? And these can be considered like separately. Converting the data format is usually the easier task, right? Because you basically keep the same information structure, you just change the underlying bit-by-bit representation of the data. So getting rid of the colors usually is not that big of a problem, right? It usually needs a converter or parser of some sort to read the information and just write it into a different format. But the more challenging part is to deal with the differences in information, right? How can you align like a microscopy picture with a DFT calculation? How do you identify what's similar in them? What is like joint information and what is like completely disjoint information? And usually in material science, it's the material that makes the connection, right? Or one of the aspects that can make the connection. And this is like where the challenge then really begins when it comes to defining metadata, to finding schemas that work for multiple methods, or at least that have parts that work for multiple methods. This is also where ontologies come in order to make sense of all the data, and so on and so forth. Yeah, so in essence, in order to combine data and make it available in a common platform or in a shared platform, we have to get rid of the data format, like we have to get rid of the color, and then we at least have to integrate different symbols, right? And find ways to find like these hierarchies that then allow you to represent information in a common hierarchy, even though that information might be different. And in Nomad, it works a little bit like this. We have our parsers that go for different file formats and try to convert this into an archive. I wrote this here in blue, like all the blue parts coming directly from the parser. Let's say if a parser looked at the simulation, it produces like this section 1, which then contains the data about the simulation. If it tries to parse like the data that comes from experiments, for example, like a measurement of some sort, it produces a completely different hierarchy of information. But then we have another part, and this is where we try to join the pieces of information. That's the red part here. That's our results section, where we basically try to identify, okay, what is the material that was simulated, or what is the material that was observed with the measurement, and extract this information into a common place. And also have a common place where we try to structure all the method information that went into this. So even though that we are talking about different methods, like a DFT calculation, completely different from like taking a microscopy picture, for example, but there are still similarities when you think in terms of hierarchies, right? You have a DFT calculation on one side, but you might have a molecular dynamics simulation on the other side. They're different methods and they might produce different metadata, but there are also some common metadata. For example, for both of them, you use a computer program to do the simulation, right? So the program name, the program version, maybe the operating system or some numeric parameters might be the same or might share some metadata. And this is what we try to do with these hierarchies, like put the more common information more on top and the more detailed information more on the bottom, and then somehow make this available through a search interface so that you can really select, like either you are on the top level, you're just interested in materials, you want to see everything for a material, or you want to dive deep and go to certain methods and then a filter based on certain criteria that these methods offer. Let's say for you are looking for a certain DFT code or for a certain functionality that is used or something like this. Okay, let me skip this very technical stuff. Maybe a few words on our architecture. We try to make the whole Nomad thing as coherent as possible. So we have like one large source space. We try to use as less tools as are feasible. So everything is based on Python. We use just one framework for doing the API. We have a processing framework. And then we have like lots and lots of these parsers, of course. But everything is connected with one source code project, and then we generate one Docker image from this project and one Python package from this project. And then the Docker image is what we use to operate the system. But everything is like together. It's not like 20 services that are then operated independently. It's basically one image that you have to spin up in your environment, and then you can basically sort of know there are a few databases attached and stuff like this. But we try to make it as simple as possible to foster the idea that others might also be able to install this and run this. And we are at a point where we have like a very short tutorial on what's necessary to run Nomad. And we have like the first 5 institutes that are now running in Oasis that we're able to deal with this. So it's just physicists that are able to run this software and maintain it locally and have these Oases run. Yeah, that's sort of like the core idea about the architecture that I want to convey here in the little time that I have. And let's go on and talk a little bit more about the Oasis and different use cases that we have for the Oasis. So I talked about the Oasis quite a lot already, right? So I think I understand that this is the idea of having Nomad at your local institute. But why would you do this? What are like typical use case scenarios for this? So we have the Nomad software, and it can run in different scenarios. The most important scenario for us is of course our central installation, where we basically have a huge amount of public data, then some private data, embargoed data that's not yet published. And we have our central user management and stuff like this one. But then, of course, there are different things that you could also use the software for. For example, you just want to manage your data locally, right? You don't want to publish it yet. You just want to manage it locally. And once you think your data is ready, then you want to publish it and push it to the central system. This is what you might call the academic Oasis. Then we have other scenarios where you want to build a Nomad mirror, just because, like, I don't know, you are in a far distant country, and the connections isn't always this what you want to have. And if you want to have like larger amounts of data available, maybe you want to build a local mirror of Nomad. That might be another use case. So basically you take all the public data and mirror it. Then we have the industry Oasis, like let's say industry wants to do like large scale analysis on all the data that we have using artificial intelligence and stuff like this. But of course, industry is industry, and they don't really want to see anybody what they are doing. So they don't really want to use the central Nomad. They rather use a mirror of all the public data, but then also manage their local data, of course, use their own local user management. So really don't have any connection to the internet at all, and just run the Oasis in private. And then, of course, we have the FAIR-DI Oasis. This is like what we want to do in FAIR-DI, where we have like each institute is run its own Nomad, and then they work on the data locally, either public or private. It really depends on the use case. But some of the data they want to make public, right? So mostly the metadata for their experiments and stuff like this, they want to make public and transfer to the central Nomad, while the larger part of the data remains in the repositories. Yeah, so these are the common use cases for the Nomad Oasis. And now it's basically up to us to make the software as flexible as possible to foster all these use cases. And we already made the first steps, and it's now installable in a pretty easy fashion. And we also can make a connection to the central Nomad, like on your Oasis. If you have some data, you can press a button, and it's automatically going through the internet into the central system. It's not right. I have more slides, but for some reason they don't show up. But maybe my time is already up, and maybe it's a good, good point in time to stop here. Yeah, so I think in summary, I showed you a little bit what NOMAD is, how it works internally a little bit, and I also talked about this FAIR-MAT idea and how we want to use NOMAD to connect like multiple institutes to each other. And the core ideas are that we really want to have like this domain specificity. We are deliberately chosen this bottom-up approach where we use parsers to dissect different data formats and then try to homogenize it after the fact, because we believe this works much better than to just try to dictate data formats to everybody, which usually doesn't really work. That's one key aspect. And another key aspect is that we really want to build this network, because we believe, okay, data is really big, especially when you look in experiments and certain methods there. You can't have just one server where you try to put all your data. It doesn't really work. You really have to build this network. But of course, data has to be fair. You have to be able to find it everywhere. And this is what we want to achieve with this central portal, or the whole FAIR-MAT idea, where we use one central metadata repository, basically, in order to allow the search and then access the data in different installations. Yeah, okay. Yeah, thank you very much. Let me end with this picture here. Hopefully it will inspire a few questions. Yeah, thank you again for listening.
Okay, thank you. Thanks, Marcus. So are there any questions about a NOMAD and a FAIR-MAT?
I have one question here in Louvain.
Yes,
hello.
Please.
I have a very general question, because as you mentioned, NOMAD has been around for quite a while, and you listed how many people visit the website and so on. So is there any data on how useful things turn out to be? I mean, are there new breakthroughs, papers? Is there some statistics on the actual effect of NOMAD in this particular case?
I think this is very difficult to achieve. I know what you mean, and it certainly will be necessary in the future to actually demonstrate that this really works and has an effect. But of course, the questions arise: how do you do this, right? One thing that we try to do, even though they are not yet really public statistics about it, is to track the references of the DOIs that people create with NOMAD, right? So what people can do when they uploaded the data, they can create data sets and have a DOI for this. And in principle, you could do the Google Scholar thing and try to look where these DOIs were actually used, how many publications are there with data in NOMAD. But this does not really tell us really how much this was used. But then you really have to look at the citations to make sense of this. That's one way to go about it, to go through publications and try to find something there. Otherwise, we only have like statistics on how many people are using this, right? We can look at our servers and see how many people are requesting something, how many people are downloading something. But then we only make assumptions about what they might do with it, right? And how successful they might be with it. Yeah, so that's the ideas that we have in this regard. At some point, we really want to have these statistics and also make them publicly available. Yeah, but that's what I can say to this question, I guess. Maybe you have better ideas on how to do this, how to actually track the usage of a database, and not just how it was used, but also how much was the impact that was generated from this.
I definitely don't have better ideas, but because you say DOE here, so. But sometimes people use, say, 100,000 data points, right, from all over the place in artificial intelligence. And so I don't think that's going to be referenced in any paper. So a lot of this will be hidden.
Yeah, but this is another thing that we want to enable, right? We want to also enable people to create data sets for data that they use in analysis, right? So when we think about data sets, so the data set isn't really the data you uploaded. The data set is really, you can look at the data that's there and you can create a data set from this, right? It's like a tag or a label or like an album or whatever. And then you can make reference to this. So in principle, you could write a paper and reference like a set of data that you use for analysis, instead of just referencing your own data.
Okay, thank you.
Yeah. I can read some questions from the chat if you like.
Yeah, and there is also
yeah.
some raised hands, so we can start from the chat maybe.
Maybe we start with the raised hands because I get the feeling they are directed towards the last question.
Then it's Matthias.
Actually, mine is related to the last question because it would be really great in measuring the impact. But of course, a lot of the impact is that people look what is there and then they don't have to redo the calculation again. And of course, I mean, that will never be cited. And you said actually some people may just use the data and do it for use it for artificial intelligence. They should cite it, but very often they will not. So any ideas how to measure impact from the broader audience would be really great. And we like really to do that if you give us really an idea. But it should be, of course, not too restrictive, right? I mean, you still actually like to keep the privacy of people. So any ideas from anyone in this group here would be actually great to learn.
Claudia?
Yeah, I actually wanted to say exactly the same. So if I see how my group, for instance, is using the data, they just avoid doing calculations again, or they use input files and check outputs if they get the same results and so. So I think there's a lot of impact which we cannot measure. So I think it's just along the lines what Matthias just said.
So then I would continue with the chat if it's fine, or is there more?
There's still one question. There's one question here in Louvain from Michael.
Okay.
Thank you very much. I have one question about maybe the inner working in Nomad. Do you have any projects or developments going on where you try to put links between entries? For instance, if you would say, this entry is a structure that is basically a supercell of this structure with this kind of defect, or this calculation seems to be an interface between this material and that material.
Yeah, so I mean, there are a number of things I could mention in this direction. Like one is the encyclopedia itself, which makes the connection based on the material. And at the moment, this is like very simple, where we basically just create, where we say, okay, if it's the same atoms in a similar labs with the same symmetry and stuff like this, and we say, okay, this is like it's the same material and make connections like this. This of course wouldn't catch like stuff like this. Another thing that I could say is that we at least try to make most of the metadata that's relevant for these kind of questions available through the search interface, and you could try to make these connections for yourself if you're really interested. Let's say you have a structure that has a certain defects, and you also know the normal, the idealized whatever structure that would fit the defect. You could basically search for those and try to make the connection. In the encyclopedia, we have a few ways to do automated, no, maybe not, let's not go there. Then the last thing I wanted to say is like workflows is like a big driver for connections that we actually try to formalize. That's a key point currently in our development. We are looking at various workflow engines and try to gather the information that they saw about the workflow in order to make a connection there. So that let's say you do like a let's say constants kind of thing where you use like various DFT calculations together to compute elastic constants, for example, that you can really see, okay, these were the calculations that went into this, or like phonons or another thing. Or so we currently have support like for certain specific workflow codes, like PhonoPy, for example. But we really want to broaden this to the more generic approaches where you use like a workflow engine like Fireworks or ASE, ASR, these kind of things, and help users to persist the connections that they have between the data points in Nomad. And this also for the whole FAIR-MAT thing, very important there. There are other questions in the chat that go in this direction. How do you add, how you allow users to add their own piece of information, right? So our parsers only detect what's in there, what's in the VASP calculation, for example, but they have a really hard time in detecting why you are doing the VASP calculation and how it is connected to other calculations, and really want to enable the user to basically provide these links for us, so to make it easier. But this is also then, like, besides technical challenges, also has like this cultural impact, because when people really have to spend some time and some effort in actually curating the data and going the extra mile to provide more metadata than just what we can discover automatically.
Yeah, I think this is a very important point to try to make these connections. And I think maybe the big success here is that people can just upload data without doing too much work, right? So I think if your amount of data starts growing, and there would be some automated processes to try to automatically find, just based on the structures, these kind of connections, I think that would greatly enhance the usefulness of the results in the database.
I think workflows can be like a short-term kind of thing to attack this, and in the longer term, like artificial intelligence, ontologies, all these kind of more miracle machines might have some potential to help us there to do these automated connections. And of course, these are all technologies that we look into.
So I just wanted to add to the question that a little bit of that is there already. So we are looking, for example, for similarities. So Claudia's group has really a concept that you'd say, actually, I would like to really have materials which have a similar density of states as this one, and then you get really the results. And so in the encyclopedia and in the artificial toolkit, we are exactly really developing these things to find similar properties, which at the end you then really will result in materials which you could actually combine even.
Yeah, that was the point that I wasn't daring to dive into, because it's more complicated if you want to look at it in detail. Yeah, but yes, this is like one example project where we are trying to do. And on a technical level, I mean, there's also like other initiatives that we have where we want to look into these sub-descriptors for structures, and this where it's really more about machine learning and things to make connections. And yeah. I feel like there's in any case, there's like a great potential for future work and research in these areas. And this is also what we want to enable with something like Nomad, like making the data available would be the first step for people to find new mechanisms and new methods to make these connections.
Maybe you can take the two questions that are in the chat, Marcus.
Yeah, Andreas Pönicke is asking if the decentralized approach of Nomad databases, how does it achieve persistence of the data? So I think the idea is that many research institutes have a hard time to deal with this on their own when it really comes to long-term persistence and storing stuff for like forever, basically. And how we want to do this in the centralized architecture, in this federated architecture, sorry. So yeah, the idea is that we think of the available data as pyramid, and in this pyramid you have like more useful data and less useful data. Typically you produce large amounts of data that you typically then just throw away, right? You were just doing experiments that was just garbage data that came out. Then along the research process, you refine your data more and more, and lots of it is like filtering, right? And then the data becomes more and more valuable along the road. Let's say you've done lots of pictures and identified those pictures that actually gave you some clean data, and then from there you start further analysis, and then you provide like a more condensed version of this, and so on and so forth. And at the very top, you have like this nice picture that you put in your paper, right? This is like how typically it works. And the idea is like when we are limited in what we can actually preserve in a long time, just because the size is super large and whatnot, we want to facilitate these pyramids and say, okay, for the very top, for the published data, for the high quality data, this is where we can offer something. And this is then where you just want to centralize data and put it into a central system that's hosted by research by HPC centers and data centers that know what they're doing, and then have the long-term persistence there. So there might be 2 or 3 mirrors of the central node that are capable of taking some amount of data from the various institutes, so that we can at least store or at least have long-term persistence for published data or for high-quality data. How much of the pyramid we can store then really depends on how much data is there, how does network technology, storage technology, and so on develop over the years. I hope that answers the questions at least a little bit. Yeah, the short answer, of course, is we can't really store all data and have like long-term persistence for everything. We're just producing too much. I mean, there are instruments that are producing like terabytes per second, where you basically need special storage structures just to keep the data for a couple of seconds, and then you have to throw them away because it's just too much information coming out of the sensors. So there has to be some clipping at some point, and you have to make decisions on what's valuable and what's not. There's another question from Matthew Evans. For computational data, we have well-defined inputs and outputs, but for experimental data, the outputs, from an instrument will be typically have no knowledge of the system, of the sample system or whatever. At least it's up to the user to manually enter this. Do you think parsers for existing electron notebooks is enough to capture the complexities of experimental inputs when it comes to constituents, materials, synthesis conditions, processing parameters, and so on and so forth? I think for this question, the workflow part is really valuable. And I think this is what ELNs will hopefully provide us with the connections, not so much the data itself, but the connections between different data points. If you think about that the sample came from somewhere, it was probably synthesized somewhere, and then you do some characteristics on the sample with certain measurements, and then you send the sample around and then use it here and there and so on and so forth. But the idea is like, if all the data is available and we find a good mechanism, for example, to identify samples, you could basically draw a history of the sample, right, and see in what measurements it was used and so on and so forth. Thereby getting idea how the sample might have changed. I mean, that's another aspect, where the sample might not, like some of the methods might be to some degree destructive or whatever. Then you get an idea of what the sample was, and you also make connections between all these measurements, and thereby might get an idea of what was actually measured, what was lying under the microscope, and so forth. On the other hand, it will greatly depend on user input, and as you mentioned, that's certainly a weak point, and the divergence from our NOMAD approach, where we do everything with parsers and stuff like this. You have to provide people with like manual input opportunities. Electronic map workbooks are certainly the more common way to do this. And then the question is how to formalize these lab notebooks. Like some lab notebooks are really just notebooks that we just write down arbitrary text that doesn't really help you. So one aspect of FAIR-MAT is to develop like these laboratory information systems together with lab notebooks, so that you have like a tight integration between the various instruments, and then really have formal kind of metadata entry masks and forms and stuff like this, where you ask for certain information. But still, of course, you never know what the user enters in there, right? And how reliable this is. But again, as with all data in it, we just have to provide even more metadata to allow you to make assumptions about how reliable some information is. This is also a problem that we currently have with computational data, right? We have all this computational data in there, but we can't really tell people how good the data is. They have to discover this themselves, and we providing the metadata for this, right? We say what the functions are and what the parameters are, and everything is there. And then you have to make a decision on your own how reliable this data might be. And maybe in the future, all kinds of ontologies and artificial intelligence might help you there. And then it's related to the other questions that we already answered a little bit. Yeah, I hope that helps you, Matthew.
Thank you, Marcus. Claudia, I saw that you lowered your hand. If it's not important, then maybe you can take a break, because otherwise it's going to be very short. It's okay? Okay. So we can reconvene in 22 minutes then. See you later. Thank you all.
Bye-bye. Thank you.
Yeah. So I have a quick question, if anyone there. I mean, during the break, not important, just free. So Marcus is okay. So I just have a quick question about. So is there kind of thing like a data index in the NOMAD now? So by data index, I mean, so people, if I want to do some calculation on some system, so I'm able to just search on this data index in the NOMAD, and then if I found they were already done, and the data in the NOMAD
so you
repository, I don't have to redo it, because that's, I think, the great advantage for the big database to avoid the repeated work, right?
Yeah.
Because that could be more convenient, better than the literature search or something like that.
That's the whole idea, right? We want to provide enough possible criteria in the search so that you can really find the stuff that you're interested in. So at the moment, you can search, for example, for the elements that go into a simulation. You can search for the type of system. Was it like a 2D material, a bulk material, or just a molecule or whatever? You can search for symmetry. Let's say you're searching for bulk materials and you want to pick certain space group numbers or something like this. This is stuff you can search for. You could search for the functional that was used if it's a deep calculation, for example. And you can also search for what people actually tried to output in there. Did they do a geometry optimization? Did they do like a density of states or something like this? So it's a band structure in there. These kind of things you can search for. You can search for certain authors. You can search for when was something provided. So these are the typical criteria that we have in there. And through our search interface, you can like click all the buttons and basically refine reduce the amount of available data to those data that you're actually interested in. And then you can download all the raw data. You can download all the input-output files that people uploaded. So you typically would get everything that you need to reproduce it, or not reproduce it, just use the data that's there.
Yeah, that sounds great. So I think in future, if the database is big enough and I mean very become big enough, and so the publisher or editor of the journal may just ask the author. So please check if what you did is overlapped or already repeated is done at Nomad repository, and then that would actually increase the impact of Nomad. That's the first question. I think.
Yeah.
Also encourage people to use the data in Nomad already and avoid the repeated work and do the new work. That's kind of become a kind of standard check, or just check overlap the papers or something.
Yeah.
So that would be great. I mean, is that possible in future?
What many publishers do at the moment is at least they ask their people to upload data to somewhere, right? So most publishers are requesting now that you have the data available somehow. It would be like a first step. Then it's like, I mean, it's a little bit up to the reviewers, to the authors to make sure that they didn't really duplicate anything, especially the reviewers should like be aware of it. And Nomad can certainly help, right? If you read in the paper, okay, someone was like doing simulations for this and that, you could like try to have a look and see if there's already something there. Like in the same way that you would use Google Scholar or something to find if like a paper or something is already published. And then maybe in the future with like natural language processing and AI or something, you can have a machinery that identifies what people are writing about and then matches it to something that is in a database somewhere. That's certainly, this could certainly be a project for someone that's like good at these things. But if you know artificial intelligence and how to distract information from papers, you could try to find, and there are people out there that are trying to do this, right? They especially in synthesis, there are people that are trying to go to like history of publications to find information about material synthesis and what people have experienced when they try to melt certain things together and stuff like this, and try to discover this automatically through machine learning. And if you have a machine like this that can answer, that can tell you, okay, this paper is writing about this and this material, then you can have a check back in a database and see if there's already something on this. And this could also help you as an author to find related work, right? And this is also what's in Nomad, right? You ask people to put references in there. So for each data that you uploaded, you can put in the paper references and stuff like this. So we try to make the connection both ways. So people use our DOIs to cite the data in their papers, but we also ask them to take their papers and put them to the data so that there's a one-on-one connection. And once you find data, there's a high likelihood that you also find papers about the data.
Yeah, so even if could include the unpublished data, those might be useful. So it just doesn't form a paper, but may be useful as a part of a database.
Yeah, that's another thing, like all the negative data, the negative results where you don't find a publisher for, you can at least publish the
Yeah. So that's actually bring up another question. I'm not sure if now is a good time for discussion, but just about the cleaning of data or error checking. So I mean, they we human made a mistake, and we cannot avoid a mistake intentionally or unintentionally in both cases. So I think I guess there's some error checking or procedure in Nomad, right? Before
the boundaries to publish data on Nomad are very, very low, and this is intentional. We basically want to have all the data, even the garbage data, because you never really know how useful it might be in the future. And thinking about artificial intelligence and new methods and stuff like this, things that looks negative for a certain use case, like you were producing data to achieve a certain goal or to compute a certain quantity, you might have failed in reaching this, but the computation might still be useful to someone in a different context. And this is why we are not doing much data cleaning in the sense, right? So once you upload something and we are able to see this is a mass calculation, then we are fine with it, even though it might be not very useful at the time, but for other people it might be useful, and that's why you can publish this. This is like a strength and a weakness, right? On one hand side, okay, we have all the data and you might do something with it in the future. The weakness, of course, is that you have a lot of data that might not be useful to you. And then you have to use the search and stuff like this to really find the data that is sensible for the application that you have in mind. But in the end, it's always pretty application specific. It really depends on what you want to do with the calculation, right? Whether you can use it or not. For some properties to compute, it might be enough to have a very low precision kind of calculation. For other applications, you need like a different thing. And our philosophy is we try to provide all the metadata that's necessary to identify whatever you need. And if it's like a functional that is like running really fast but doesn't really give much precision, for some applications it's good, for others it's not. And you can't really make the decision if some calculation is good or bad beforehand, right? Not even as a human. You might say, okay, that's bad for me, but you can't really say it's bad for others. Does it make sense?
Let me just actually say one thing. I mean, I fully agree what you just said. Actually, to some extent, there is no garbage, right? If you have all the metadata, everything is meaningful. And so that is the only thing. But I just wanted to say, leave some of the discussion for your discussion section, because you have half an hour discussion, and these are important questions, I feel.
Yeah. Sorry for that. I just
no,
yeah,
sorry.
so
I mean, I just wanted to
post.
say that these are good questions, but filling half an hour for a Zoom meeting is not so easy usually.
Yeah. So we have 30 minutes at the end of this session. So let's leave. I have a few more questions actually.
Yeah, keep them.
Yeah, keep them. Yeah, at the end. Yeah. So
okay, see you
when
then.
more people. Yeah. So let's have a real break. Sorry.
Yeah. Okay.
Sorry about that.
Yeah. See you later.
See you later. So our next session will start in a few minutes, right? In 1 minute.
Yes.
Okay, so yeah, so please, Givonia, could you share your screen?
Sure. Can you see my slide and hear me correctly?
Yes, yeah, I can hear you and see you, your slides.
Great.
I think now it's time to start next session. So let's welcome Dr. Givonia Pizzi from Lausanne, Switzerland. So he will talk about AIDA, Material Cloud, and computational workflows. So please.
Thank you very much for the introduction, and thanks everybody. It's been a very interesting workshop up to now, and what I want to discuss today is two aspects actually. The first one is how in AIDA and Materials Cloud we achieve fair data access and sharing. In particular, of course, focusing on the field of computational material science is what we do. And I would also add one more R actually to the R of FAIR, which is the R of reproducibility, which is something we push a lot with our infrastructure. But this will be probably the first third of my talk. But in the second part, I want to discuss how to push FAIR beyond the quotation mark just data. I want to discuss about how we can achieve fair simulations and fair access and sharing of codes and workflows. So let me start, maybe for just a comment. I tried to put at the top right here some FAIR letters. Some of them will be red sometimes. I'm trying to say which of the FAIR pillars I'm addressing mostly in that specific slide. Let me start with quickly introduction of the challenges we have when we want to run high throughput simulations in a HPC fashion. And the first one is workflow automation. We need to have the tools to be able to run and manage complex workflows with advanced error handling. As we know, the codes can crash, and we need to have a way to deal with those. And we'll discuss this later, how important this is. At the same time, of course, you don't need only the workflows themselves, but you also need to have an engine where the workflows can run in a robust way. And once you run all of this, you need to manage all the data which is produced, not only to store it in an efficient way, but also to be able to query for it. And finally, an important point for us is the one of reproducibility. And the fact you store enough information in order to be able to fully reproduce any computational workflow. In order to address these challenges, we've been developing what we call the AIDA platform, which is a computational science infrastructure for high throughput workflows with full data provenance. It's an open source Python code. You have here some links, which indeed provides a number of features, including a scalable workflow engine, automated tracking with the full data provenance. I'm going to discuss in a moment what this means for those of you who don't know. Has built-in support for HPC computation, so you can just submit simulation on HPC facility, and has a flexible plugin system. As we show, we now have a support for over 100 different codes from material science mostly. So let me first start with the first part of the talk about fair data access and sharing as opposed to fair simulation access and sharing, which we'll discuss later. The key aspect we started from in the core design of AIDA is the idea that you really want to represent the full data provenance, the full history of any piece of data you have and you bring into life when you run simulations. And the way it's designed is very simple. You start from the concept that any calculation has a number of inputs and a number of outputs. This could be a crystal structure, some parameters, and some output structure, some output forces and stresses, etc. And now, if you imagine that any piece of data can be the input of another calculation, you end up with a structure, which is that of a cyclic graph, where if you have a final result, let's say a band structure, you can easily just look at the graph and understand this structure, this band structure was generated by a given calculation with some parameters, and the structure itself, the input crystal structure itself, was actually the output of another calculation, and all the inputs and all the outputs of any step, going up to the very original structure, let's say, imported from some experimental, for instance, crystallographic database. And this graph just gives you the idea of the concept, but when you look at real provenance graphs as created by AIDA, they look like this. So they are very easily quite complex, not because we represent things in a complex way, but it's really what we do as material scientists. When you run a molecular dynamics, maybe with a mixed method, DFT, mixed with some semi-classical method, you have to run a lot of runs, you have to do some pre-processing, prepare the structure, run some dynamics and so on. So the graph, which represents the inputs and the outputs of every calculation, becomes very quickly very complex. And the one in the bottom here is a graphical representation of an actual database with the calculation of basic electronic properties and binary functions of only, I would say, only quotation mark 500 materials. So it's not even a high throughput database. I would say it's a mid throughput, maybe, or mid to low throughput database. Still, the amount of connections you have in the database is already so large that it's essentially impossible to reconstruct a posteriori. And indeed, in this talk, I will try to also mention how we address some of the issues which have been touched upon in the final questions before the coffee break, how we can also infer by storing this graph the reason why certain calculations have been run. And so even the best willing scientist who has been running this will not be able to really reproduce in detail what has been done, but just and describe it in a paper. You really need to have a tool like AIDA that tracks this provenance while the simulation are run and keeps track of the full metadata, the full provenance information for any calculation. And once you have this, it becomes relatively easy, a posteriori in a sense, to look at this graph and understand what's happened and create any type of metadata format you want. And a few years ago, we already showed in practice how this could work in the case of integration of AIDA with a theoretical crystallographic open database, the theoretical counterpart of the COD database. That defines the metadata format, and we were able to implement an automatic converter that, taken the AIDA graph, was able to create all the theoretical metadata about the calculations. And since here we're speaking about FAIR data, the other important thing is also how to make it easy for others to reuse the data. And so AIDA has features to export the full graph you have in your computer or parts of this graph, say maybe a subset of your calculations, and either share them with collaborators or upload them to public repositories. And one of them, which is the one we maintain and develop, is called Materials Cloud, which has specific features tailored toward AIDA. And in this sense, what I want to show just in the next 3 slides is how combining the graphs automatically generated with AIDA with the data sharing capabilities of Materials Cloud, you can really achieve FAIR data sharing. By the way, Materials Cloud is one of the GoFair implementation networks. So Materials Cloud has a number of sections, some of which are more geared toward data generation. What I will focus now on just the last 3 sections, Discover, Explore, and Archive, which are the one more relevant for the topic of FAIR data sharing. The first one I want to mention is the archive. Is something in a sense very similar to Zenodo. Is an archive where you can deposit files and data associated to a paper you've been produced. As you know, most funding agencies now require you to write a DMP and to publish also the data associated to your paper in a fair way. And Materials Cloud Archive uses the same actually backend called Invenio as Zenodo, and is, however, a curated and so actually moderated, I would say moderated and topical database. It's about only materials science, and is moderated in the sense that any entry submit, it's open to the world, so any of you can submit here data associated with your papers if it's about material science. The moderation is not a scientific peer review. It's just a very lightweight process where one of our moderators will look at your entry and give positive suggestions in order to improve the quality of the data you're submitting. And actually, our experience, I would say, more than half of the entries require some request for feedback, but all authors typically get it in a very positive way, because requests could be things like, please don't use an Excel format, use maybe some more open format, maybe make sure this file is in another open format, it's clear, there's a README explaining what the data is about, etc. The archive is recommended by a number of journals already, like the Nature's Journal Scientific Data, and now also by the Open Research Europe journal. And when you publish data there, beside the user fields, authors, affiliations, etc., it also gives you a DOI to your data, and you can put data there which is going to be guaranteed to be there for the next 10 years. And now, if you also have data which is being generated through AIDA, which is optional. In a sense, you can upload data here, which are just files and without using AIDA. But if you use AIDA, you can very easily create new sections in the other two sections I was mentioning, Discover and Explore. And we just show very briefly with an example what this means with the example of one of our studies, which is about discovering two-dimensional materials by simulations, by computational exfoliation. And since we did this with AIDA, we created one Discover section, which is what our Discover sections are essentially project-based curated data sets. So that's a section about two-dimensional materials, where for every material, we have a list of computed properties and of interactive plots, so three-dimensional widgets to show the structure, interactive band structure plots, etc. But for any computed quantity, you have these little AIDA icons. And when you click on them, you jump on the Explore section, which is essentially a browser for the full provenance graph. If you want, if you think AIDA like Git, so Git keeps track of the history of your source code and AIDA keeps track of the history of your simulation data, the Explore section plays the role of GitHub. It's a place where you can upload your Git repositories, or in this case, your AIDA graphs, and you can graphically inspect them. And so in this specific case, let's say I want to know how the band structure of magnesium bromide was computed. I can just click here, and not only I see the band structure, but here on the right, I see a small portion of the provenance graph, which I'm going to show live with a small video now, where the central node is your band structure itself. And you can see this was generated by this green square, which is a quantum espresso calculation. If you click on it on this provenance browser, you can inspect all the inputs and all the outputs of the calculation, not only the raw inputs. So if you're and you know how quantum espresso works, you will recognize it is a quantum espresso input and a quantum espresso output, but you see the full part of the subset of the graph where you see all the inputs and outputs of this calculation. And so, for instance, if you go to the input structure, you can visualize the structure, you can download the structure, but also you can also, again, discover what is the calculation that generated it. And you can go up in the history and discover, for instance, the input structure was generated by a quantum espresso variable cell calculation, and you can continue to go up and see all the parameters with which this structure was relaxed, and so on. So this kind of concludes the first part of my talk, which is about FAIR data sharing. I try to very quickly give you an idea why, by putting together the provenance capabilities of AIDA and the visualization capabilities and sharing capabilities of Materials Cloud, you can achieve FAIR data sharing for computational data. But what I want to stress more in the next part of my talk is about how we can also have and try to achieve fair access and sharing for simulations. And as a kind of preliminary introduction, the first thing I want to stress, which is probably obvious, is that given a material, what we do when we do research is we typically compute relatively advanced quantities. We can start from basic ones, like a band structure in this example, but we very easily go to much more advanced properties. We can be the output of GW calculation, of molecular dynamics, and so on. And these are always the result of a relatively complex workflow, as I was mentioning before. Now, the AIDA provenance graph, if you use AIDA, is a very detailed description of how that specific piece of data came to existence and which parameters were used to generate it. So if you have it, if you want, it's like a log of what has happened in the past or what someone else has run. However, having workflows is one step beyond, because now you have, thanks to the workflow engine of AIDA, which provides a flexible Python interface to run these workflows, you can not only have a description of what has been done by someone else, but you can run a new calculation on maybe another material or on the same material with different parameters using the same logic in a very simple way. The advantage of the workflow engine, which already provides out of the box a number of interesting features like robustness for connection drops to the supercomputer, and for instance, has a feature to allow to very easily implement error handlers, which are essentially functions which detect when a code crashes or has an issue and know how to fix the inputs and the outputs to make the calculation work. I will be describing this more in detail in a moment. Just to stress this, it's not that AIDA provides the error handlers for any code. Every code workflow implementer will have to implement them, but AIDA provides a framework to write these error handlers and make this very easy. And of course, there's another bonus. If you run workflows for AIDA, not only you have the full automation of the workflow, but also automatically the provenance graph will be stored for you. Now, the first step to make this appealing and interesting for the community is that AIDA should support a relatively large number of codes. And this, in a sense, is also about findability. What we've been doing since 2017 is to create on GitHub what we call the AIDA plugin registry, which is a very lightweight registry where anybody who has been developing a plugin or a workflow or any kind of support for AIDA can register it and just point to the GitHub repository of that code, the documentation, etc. Today, actually, in the past 5 years, we've been spending quite some effort to create a community around AIDA. And as you see from the number of plugin packages in the past 5 years, it's been steadily growing. From the very beginning, when there were only 2 or 3, there were kind of Quantum Espresso and a couple more, to now where we have 66 different GitHub repositories providing different types of plugins with essentially 100 or more codes supported and more than 100 different workflows, which range from very basic ones to just take care of fixing and error handling of a code to relatively advanced ones for materials properties. Now, however, having a code is the first step. It's just the way to tell AIDA how to generate the input files, how to parse the output files of a code, and maybe how to deal with workflows. But what we really want to go is to have some kind of turnkey solutions, turnkey workflows. And here we'll try to use some similar analogy to what Stefan did yesterday. So I'm making an analogy with cars. And if you have a car, say you want to drive your kids to school or you want to drive work, etc., you don't want to be an expert of an engine to know which pipes to connect to what, and you don't want to, if you change car, you want to have to learn again how to drive. You just want to be able to turn the key and drive. And in a sense, that's what we are trying to achieve with this idea of what I'm trying to mention about fair access to simulation. We really want to have something where I press a button and I get a reliable simulation. And this again is about robustness. So we don't want the engine to break. So in the same way, we don't want the calculation to break. But also we want to make it as simple as possible. As in cars, you still need a driving license. So you might still want to have a user running it, have some basic knowledge of what a crystal structure is, what a bond structure is, what properties are being computed, and what are the limitations of the methods we are using. But then we don't want to need, like in a car, if you want to change car and switch brand, you don't need to learn again how to drive, right? So the same way, it would be nice to have a way where if you've been using, I don't know, Siesta, and you want to switch to VASP, you don't have to learn again how to run these simulations. And so trying to make this a bit more concrete in our domain, as a non-expert, and here, when I say non-expert, I'm speaking, as you see here, at the top about accessibility of simulations. I'm speaking maybe of a computational, experimental scientist who want to have access to some simulation results, and maybe didn't do a PhD in simulations. So as a non-expert of simulations, I would like to be able to ask for something like this. I'd like to have the question of state, maybe run with this code, just because I have it maybe, or because I know it's better, I have a license for it, whatever reason, which I have on this supercomputer with given number of nodes. But I like that all the numerical parameters are automatically chosen for me, the basis set size, the k points, etc., to get converged results. And what I care in the end is I press a button, I wait for it to run, and I like to get some plot. And at the same time, however, and we show how this was a key design aspect for us. If now I have an expert user, a person with a PhD in simulations, I'd like to be able to understand which parameter we use, check them, and possibly adapt them as I want. Because of course, maybe the default parameters which are chosen here are not the one I want. And again, maybe one important thing, which maybe some people might ask, the goal of all of this is not to take out of the play, the simulation people, expert people in simulations. That's actually the opposite. If now the people expert in simulation can just help and discuss with experimentalists and focus on the science, we are essentially removing all the technicalities from it, of knowing if my simulation is a converged cutoff and things like this. Really, the goal of us as researchers should be really to focus on the science and not on the technicalities. And so if you want to make this possible, and in the next slide, I show what we implemented actually. There are, I think, 3 main challenges. One, we want to have these turnkey solutions, which involve a number of aspects. We involve robustness, so making sure we get a result, automatic error recovery, but also automatic parameter choice. The second aspect, as I mentioned, is we want to get this balance between accessibility for non-experts but with full control for experts, for instance, about parameter choice. And also I'd like to have interoperability among different engines. As I said, I'd like to be able to switch code because maybe I prefer to do something in a plain web basis set for some reason and maybe a localized basis set for some other task, with same inputs and output formats without having to relearn everything. But as we learned very quickly, that is not any of these three is a large challenge. The largest challenge is to achieve all three of them at the same time. And so what did we do? Well, just a month ago, we published this paper, which is this demonstration of the implementation of common workflow interfaces to compute materials properties using 11 different quantum engines. That's an effort which started within the scope of the Max Center of Excellence, but actually very quickly was open to many more contributions. You see here all the code which are involved, some of them like CP2K, FLIR, Siesta, Quantum Espresso, etc. are part of Max, but many others are not. And as we show in a moment, everything we did is fully open, both the data generated, but also the code. So you can find the code here and you can look into the paper, which is mentioned here. What I will do in the next few slides, I will try to give you a sense of what we've been doing. So the idea in the end is the following. Let's say I want to compute an equational state for, say, aluminum with the Siesta code. Then now it's possible to just run this line. I just ask the AIDA common workflows to launch an equational state with Siesta on the aluminum crystal structure, but here you can put any structure you want with a precise protocol. So with a choice of numerical parameters, which hopefully gives some kind of relatively high level of accuracy. And the important thing is now I can just change the string with any of the other 11 codes which were involved in the study, just press a button again, and the result I will get will be something like this, where hopefully everything matches, but I didn't have to tell the code which parameters to use. This is an actual figure from the paper. We'll be discussing the results in a moment. For now, I want to discuss a bit the philosophy behind it, and then I will show what the results are and what are the steps forward. So the first topic I mentioned is the automatic parameter determination. As you, of course, I guess, understand, and probably I think all of you had this experience, if you describe what you did in the supplementary material, the method section of a paper, it's in 99.9% of the cases not enough. I'm pretty sure all of you had this experience trying to reproduce a paper, reading there and not being able necessarily to reproduce everything. Because it's not because of even the best will of the author, there will always be little things you cannot write in a PDF text. Now, in order to determine these parameters, one option which we didn't do, which is quite complex, I think, is to define in a unique way all the possible parameters for any code. Say, if you define a cutoff, that's how it's called, that's the units, and that's how you specify it. And then define a global best choice for any code. I know that it's very tricky because of codes might have different basis sets, different organization methods, so this would be very tricky. So we went for a more practical approach. We just define these protocol strings. So essentially we say every code will have to implement a protocol called precise, a protocol called moderate, and so on. And what this means, it's up to the workflow implementer, to the code-specific expert. With the requirement that when we then compare the results, at least to the precise protocol, results should match within a certain level of precision. And again, the name is just a kind of human readable name. And in our supplementary information, we try to give him kind of an expert should be able to read and understand and get a sense of what level of precision we are using. But as you will see, since this all run through AIDA, you can go and check exactly every numerical parameter once the simulation is run. So that's the part about parameter determination. So every workflow decides some parameters. And as I can tell you at the beginning, when we started this, the first plot we got for the question of states, many of these plots were all over the place. But by iterative discussion together, we managed to align them and essentially to find robust choices of initial parameters. Now, our experience with running a lot of simulations also tells us that already choosing good initial parameters is key to robustness of a simulation. If you choose wrong parameters, the simulation might fail for a number of reasons. Already just choosing good ones helps. This, however, is not enough. If you run any DFT code, I would say with confidence almost any DFT code, I'm sure you have a number of issues you might encounter. Some are relatively basic, like the wall time your supercomputer was reached, so you have to restart. But there may be a number of other things, like SCF is not converged, or metagonalization method crashed, or the last SCF had a large pressure, you have to restart the relaxation, etc. And for each of them, an experienced say researcher for that code knows how to fix that problem, how to change the parameter in most cases. And so this can be automated. And I stress this fixing of errors is very code specific. And so AIDA, as I mentioned earlier, makes it easy to define handlers. We just cite error by error, how to fix it, what inputs to change in order to try to achieve a converged result. Implementing it is up to each of these 11 or more plugin developers. And so the level of robustness of different codes we have might be different. Some might be much more advanced than others, but the good thing is it's very easy to add more. So if you discover there's a specific type of error failure, it's just a matter of adding one Python function to your workflow, which detects the error and will take care of it. Still, if you put together automatic parameters and robustness, it's already a lot of things, but it's not enough. Because still every code will have different ways of specifying the inputs, different output formats, different flows through which the workflow goes. And this is not easy for a person to switch. Just to give an example, that's a real graph from how relaxation in siesta in quantum espresso happens when it's run through AIDA, or even when then it's used as a component of an equation of state. And you see then graphically the topology even of this graph is different. And so what we did, the last step, and that's why it's called common workflows, is we define a common format for the inputs and the outputs. We defined a very little set of mandatory inputs for a crystal structure relaxation. It was the first common workflow interface we defined. We just need to define the crystal structure itself, of course, a protocol string, the type of relaxation you want to do. Essentially, if you want to not move the atoms just to an SCF, or move just the atoms, just the cell, both atoms and cell, etc. And the engine. So which code on which computer you want to run with which CPU resources and what time. We also standardize already a set of optional but standard metadata form inputs. So things like thresholds for forces and stresses, the electronic type, if you know it's an insulator or radio or not, it's a metal, etc. The spin type, if you want to use magnetic or non-magnetic systems. And in case you want to study an antiferromagnetic material, you can already specify in a common way for all these codes how to specify the initial magnetization per site. At the same time, we also standardize, of course, the output, because once you can run it, you also need to have a way to easily understand which simulations were run. So things like forces, stresses, total energy, relaxed structure at the end, and the total magnetization are all standardized. And one point to mention is the total energy here is not standardized in the sense that it's the same total energy for all codes, but it's standardized in the sense that energy differences are well defined and define the forces on the atoms. Now, with this set of common inputs, as you see, it's quite limited, it's quite small, which means it achieves this aspect of having a relatively transparent interface. It's quite easy for a non-expert to run. You just pass a structure, you say, I want something precise on quantum espresso on the supercomputer. But as it seems here, naively, one could expect it's not good for experts. Because as an expert, I might want to change a lot of things here. I might want to use a different function. I might want to use LDA plus U or change some numerical parameters, etc. So a fully transparent interface seems to be not enough. And so let's say this graphical representation means if you have the common workflow, here, let's say I didn't put any input, but let's say you might have only this common input, and this will call a number of sub workflows or specific executables with very code-specific inputs. If I hide them from the caller, which is what I'm doing, I'm not asking the user to tell me how to specify the cutoff in a given code. This makes it very transparent, but also not suitable for experts. Now, if I look, the solution apparently to go to the opposite, which is to make it fully opaque in the sense that any input is exposed. So when I run this workflow, I can set any single input. However, as you can imagine, this makes it okay for an expert, but not good for a non-expert. And so what was a practical solution we came up with? It's a kind of technical design implementation. What was critical is splitting the common workflows in two. So we have common inputs at the top. This we agree, we want them, and common outputs at the bottom. We also agree we want common outputs. But the way it's implemented is the following. The workflow, word chain is just a name in AIDA for a workflow, is going to be code specific. So this could be a quantum espresso word chain to relax an atom. The only requirement it has is to produce the output in the common format, but the input can be anything it wants, can be very specific and very detailed. However, at the same time, the second requirement we have is that any of these workflows comes together with an input generator. And this time the input generator will take common inputs and will generate any output needed to be then directly passed through to the workflow. And so this kind of two-level design achieves what we call optional transparency. So a non-expert user would just use the tool as a black box, would just put the common inputs, take whatever their input generator generates, pass it to the Relax word chain, and then just look at the common outputs. But an expert user could just then, instead, an expert quantum espresso user or siesta user could then go in, look at this intermediate outputs and change them at will with anything they want. How does this look in code? So like I said, it's a Python, it's all in Python. So you essentially just load with a factory the specific implementation. Let's say I want the siesta common workflow. You import the structure in a way which is the same for all codes. You can be from a file, from a zip file, it can be from a database, etc. Then you just specify, again, in a common format, which code you want to run, with how many nodes and what is the workload time. And then you just call this input generator I was mentioning, take the outputs, and generate what we call a builder, essentially a wrapper around all the inputs where you pass the structure, the engines, and the protocol, and possibly the other optional inputs. Now, if you are a non-expert, you just submit it. If you're an expert, you go here, you add some lines to modify the inputs in the builder. Okay, this was the more technical side. I move on now toward the final part of my talk, where I kind of say what we do with this and what are the results. So what I showed you here is how to define common workflow interfaces to specific tasks. Here we focus, for instance, on crystal structure relaxation. However, once we have these common workflow interfaces to various implementations, one per code, now we unleash the power of it because we can now implement single workflows for advanced properties, which will be the very same code for any implementation. So what we already did, for instance, is implementation of equation of state of the association curves, because once you implement the concept of an equation of state, you just delegate the role of actually doing the calculation to the common workflow interface implementation. So now the question you might all have, I guess, is, does it work? Is it possible to really make it work for 11 different codes? And well, the answer I would say is yes. The thing I want to stress is that in the first paper, the goal was not about demonstrating numerical accuracy, but more to demonstrate the concept works and it's possible. We are now, we mentioned in a couple of slides, in the process of making a more severe or stringent set of validations, as Stefan mentioned yesterday, using this oxide set that Stefan spoke about. So these are, what we did was just to pick one example per category. We took an insulator, silicon, a metal, aluminum. We took a more complex material with a non-cubic cell to look how, relaxation works also when the cell is not cubic, like germanium telluride. And we also looked into magnetic systems. So we looked into ferromagnetic and antiferromagnetic BCC, BCC iron. And these are the results you get for all the different codes. And as you see, they're not perfect, but already are in very good agreement, I would say. And the important thing is that there is always a margin for improvement in this automatic choice of parameters. As I said before, at the beginning, these plots were not as you see, or much worse. And we learned together what codes had to improve their choice of parameter, their choice of basis set, etc., in order to achieve this kind of level of agreement. And similar, just another example, we implemented a common workflow for the association curve of H2, and we ran it for all the codes, and this is the kind of level of results you get when you run these common workflows. Now, this already achieves a number of aspects. It's accessible, it's easy to be run, it's interoperable across codes, it's also actually reproducible. But in order to really make it accessible, we need to go even one step beyond, because a non-expert user might not want to install AIDA and use the command line. So the first thing we do is we release everything inside what we call the Quantum Mobile. The Quantum Mobile is a virtual machine which contains AIDA. It contains all the quantum codes I mentioned, which have an open license. Some of them just by license cannot be included. It contains all the AIDA plugins and workflows. Plus, since since May, it also contains the implementation of the common workflows, and actually more. It contains also visualization, etc. Actually, as a small disclaimer, if you're running a tutorial or a course where you need to have a virtual machine for your code, feel free to look into the Quantum Mobile or contact us. It's built in a very modular way, so it's extremely easy to, let's say you want a slimmer version, you can remove some of these codes, or you want to add something, it's very easy to do it in a modular way, so your code will stay there also in future versions. But focusing more on the common workflows, when you start, just download it and start this virtual machine. You get a Ubuntu terminal. You can just run the command I was showing earlier from the command line. I'm running here a Quantum Espresso silicon equation of state with a fast protocol. I just delegate it to the daemon. This means either will run it for me, will run or queue the various jobs. And this can run on your laptop, or you can also easily run on a different computer. At the end, you just run a command and it will show you the results. That's what you have to do. And since it was run with AIDA, you automatically have all the provenance. This is to run those, but also from the tests we run in the paper, what we did is to publish on our Materials Cloud archive all the AIDA export file and the scripts to reproduce it. So if you go to this specific DOI, you can actually look at it. You can download everything, the AIDA export file and all the script to use it. And if you import it, what I did yesterday, I imported it in a Quantum Mobile and I connected it to Materials Cloud. What you can see, you can actually go and look at all the exact inputs that each of the implementers of the workflows decide to do. So here I just picked 3, for instance, for custard, Siesta, and Quantum Espresso. If you know one of these codes, we recognize the inputs, hopefully. And just to give a sense, this was the input for germanium telluride, where we wanted to keep, during the equation of state, the volume fixed, but let the shape of the cell change. And here we can, if you know the code, you can go back and see how each code defined this in a different way. In custard, it write fixed vol true. In Siesta, it write MD constant volume true. In Quantum Espresso, cell do free shape. Very different way of doing it. But thanks to the common workflow, you just say it in a single way, and it's up to the common workflow implementation to write this in the right format. Now, I'm getting closer to the end of my talk. I wanted to briefly mention the current plans. Now we are already actively working in a second phase of this collaboration on the common workflows. We're trying to achieve a number of different goals. The first one, we are adding a number of new codes. 3 already are being added, and if you are interested, you can contact me. The ULI KKR code, the GPO code in Denmark, and the Win2K code. We are extending and increasing the number of common workflow interfaces that we want to implement for different codes. I stress that each of these common workflow interfaces requires sitting down and agreeing on what is the format of the input for a band structure, what is the format of the output of a band structure, or density of states, etc. So it's also not only, of course, the implementation of each of them, but also the first part is really a design of how the input and the output for each of these common workflow interfaces should look like. And we're already looking into band structure, density of states, and potentially projected density of states, and then also Born effective charges and dielectric constants as the ingredients to the actual common workflows for phonons, for instance, based on PhonoPy. The other important thing that was already mentioned a couple of times yesterday and by me earlier is that we are now wanted to use this to do a proper cross-active road validation, that's called cross-verification of these codes in a more stringent way. And what we will do is to use this set of oxides that Stefan has been presenting yesterday, so 6 oxides per chemical element for the whole periodic table, where we will run the equation of state for all the codes, for all the oxides, compare them and get comparison and try to improve, understand if there is margin for improvement. Many of the codes are also code developers involved. There are even people willing to improve the pseudopotentials or other aspects. So we are very, say, optimistic that this collaboration will really help not only validating the accuracy of the codes, but also implementing automatic recipes for anybody to run the codes at that level of accuracy. And the final thing I want just to mention as the final video before concluding is that all this has been designed with the idea that it can be used in a graphical user interface. All the inputs and which inputs are available to each code is machine inspectable. So it's very easy to convert into a GUI. And what we want to do is to implement a GUI for the common workflows into our AIDA lab graphical user interface, which is a user interface for AIDA based on Jupyter. What I'm going to show you is the current implementation for Quantum Espresso, but as you will see, it's already ready to be expanded to any code. The way it works now is essentially you have first a selection of a structure. You can do it in different ways, import from file, but also you can use, for instance, now the Optimade language to query any databases. And let's say you want to search for structure which contain silver, chloride, and oxygen. You can just click on a button, search for thanks to the Optimade API, look at the structure you're interested in, and press a button to then select the parameters. You have very simple inputs, which are mirroring the inputs I was mentioning earlier. But if you're an expert, you have an expert mode, then you can go in and change more advanced properties. Then you can just submit, and you let AIDA and the common workflows do their job. You will have a way to inspect graphically what's going on, which steps are running, and if your calculation is running, you can look live to the output scrolling if you're interested. But what's important at the end, we'll just go and see the final result in a graphical form you can inspect independent of the code. With this, I'd like to conclude. I just want to thank all the people who have made this possible. First of all, the AIDA Materials Cloud teams, all the people contributing to AIDA and the various plugins, all the authors of the Common Workflows project, but also all the new collaborators which are now working together for the next generation of Common Workflows. I'd like to thank also the funding which made this possible, in particular the NCCR Marvel in Switzerland, the Max European Center of Excellence, the Swiss Universities Fund, but also a number of European projects like Marketplace, DOM, Intersect, BigMap, and FFA, and a number of new ones. And finally, I want to conclude saying that on one side, I showed at the beginning how AIDA and Materials Cloud make it possible to have fair access to simulation data. But at the same time, we also really were pushing toward fair simulations thanks to AIDA and the common workflows. What we already implemented and delivered are open source robust turnkey workflows for materials properties with a common interface across 11 quantum engines, and more will be coming, which are very easy to use, but at the same time flexible for experts and designed to be interfaced to graphical user interfaces. And they will be the basis for verification and validation studies for this oxide set and the starting point for more common workflows. And with this, I thank you for your attention. I'm happy to take any questions.
Thank you, Givoni. For the next talk, I have a quick question. So you develop the common workflows across many quantum code. So do you think it's possible to connect this with the high throughput computing? I mean, by varying, for example, across different crystal structure or various doping element, etc. Combine these two.
Yeah, so that's exactly our goal. So what we actually did before is actually we are already using some of this common workflow for high throughput simulations. In particular, ourselves are mostly using Quantum Espresso. That's because our code of choice, and that's why the Quantum Espresso plugin and workflows are relatively advanced and contain a lot of robustness, as I mentioned. We are running, actually in 2 weeks, we'll be running on the next pre-exascale machine, Lumi in Finland, for a month. We try to fill this machine with, running hundreds of thousands of materials. Of course, what we want to do now, the other colleagues were doing the same with Siesta, with Castap, etc. And what we wanted to do is also to make it easy for others to run this. But indeed, the original reason we started all this effort was exactly high throughput simulations of materials.
Okay, thanks. Any other questions from the on-site?
There's one in Louvain here.
Thank you very much. It was very, very clear, clear overview. I have one maybe a little bit provocative question.
Sure.
How far did you go in terms of testing to the real ultimate limit, right? So one of my former colleagues used to say, everything works for silicon, and that's the first paradigm of computational material science. And obviously you have the example of how well things work for silicon. What is the biggest, most complex systems that you can push through the common workflows without breaking everything?
That's an excellent question. And as you say, indeed, and this is what I mentioned at the beginning, the first paper was already just to convince first ourselves and then the others that it's possible to implement for 11 workflows, for 11 codes, common interfaces, which is already something which I think, to me at least, wasn't fully obvious at the beginning. Now, as I mentioned, exactly because of the question you're asking, what we are going to do is exactly this validation on the oxides, which I mentioned somewhere here. Now I lost. So what we will do is, let me see if I find it. There we go. We will test already any chemical element on all these oxide configurations for all of them. And this already, I think, is very powerful because it will also give us quantitative agreement or disagreement between the codes. That's not enough. Of course, there are more complex systems which will not work. And the point here, again, is not the guarantee. I won't guarantee that you take any structure, you put in any of the code, and it will always work. That's a part of the robustness I was mentioning, because many of this implementation I never saw. I mean, I had no idea of how the CS or custom implementation work. I trust the people using it. But these people are using these codes for their own high throughput research. And I can tell you for the quantum espresso part, for instance, that we are running hundreds of thousands of materials through this. We're running the whole ICSD, the Pauling file, the crystallographic open database. And thanks to a number of efforts, and again, I'm now going to speak specifically about quantum espresso, on the robustness of the choice of parameters, the robustness of the workflows and these handlers to know how to fix, but also the robustness of the underlying code, which is very important. We are now able to move from, I would say basically 50-60% with just running the code to 70-80% of success rate when running through the workflows to 99% success rate now by using a new implementation which is being developed at the Swiss Supercomputer Center, CSCS, which is called Sirius, which uses a variational method to converge the electronic structure and not an iterative method. So in order to really get to the final result of robustness, 99% robustness, you need to work a lot. It's not just about the interface. What I showed you here is a way to make it easy for people to run. And I think this helps a lot also for robustness, because once I give this to an experimentalist, I'm pretty sure after running 5 or 10 times, it will break it. But this means it's very easy to go to the experienced code developer and say, this material breaks, how do we fix it? So I think by making it easy, we also help speed up the process of robustification, if you want.
Yeah, thank you.
Any more questions? Actually, we enter into the last
We have questions in Louvain. We have questions in Louvain.
Yeah, please.
So we know by now that the agreement between different DFT codes is quite all right, and yet in your approach you propose a 2-layer system into dealing with workflows. Do you think it would be feasible to have sort of a translator to have a unique workflow that would just direct based on the engine will create the input file with the correct input variables instead of redesigning every time you want to do a calculation with a different code, the workflow and the specific expert variables that one might want to use?
So I think it's an interesting question. I think the answer is it depends. So as you see here, the codes we've been dealing with are very, very different algorithms and basis sets. We have quantum chemistry codes like Gaussian and Orca. We have plane wave basis sets, BNIT, VASP, quantum espresso, etc. We have localized basis set, wavelets, and all electron codes, etc. So defining in a unique way what the right parameters are, I don't think it's possible. And maybe one important thing to stress is, of course, I could pick if I didn't care about the computational time, I had an unlimited budget, I would just pick a very extreme parameter for all of these codes. I would be sure they are converged and would be happy. Since this comes from a context of high throughput simulations, we want to find the smallest, but the cheapest parameters will give me converged results. So this will always be code specific, I think, especially if the methods are different. At the same time, once the methods are the same, like make an example, plane wave codes with pseudopotential basis sets. If you take a BNIT, VASP, CASTEP, and quantum espresso, there we are working within the context of this collaboration to try to agree together, okay, the cutoff which is converged is this, the mirroring we need to use is this, etc. But we did this design of having just a string and let the implementer of the workflow decide, exactly because the codes are so different, even if they compute very similar properties, which I honestly doubt that it will be possible to do what you say at the level of the low-level calculations. But the good thing is that there are I think there are a few very important low-level calculations, relaxation, some basic properties, etc. All the rest can hopefully be built on top of them. And so when you define what an equation of state is, as long as the calculation is converged, you don't need to worry anymore, and then you just have a single equation of state workflow. I don't know if this answers your question.
Okay, thank you, Giovanni, for the nice talk. I have a very simple question. So I want to know if the AIDA workflow can support the calculations considering spin orbital coupling, as well as if it is possible to produce the linear functions directly if I want to consider the spin orbital coupling. That's it.
Yes, so thanks. It's a very important question. So in general, again, maybe let me, just to clarify, maybe it's obvious, let me divide the common workflow interface from the actual implementation. So all codes that support spin-orbit, you can run through AIDA with spin-orbit. In the common workflow interface in the first round, which is this one, we didn't implement or specify spin-orbit just because we had to make some decision on where to stop. But already, like last week, we are discussing, and there will be a few more options to activate also, spinners and the spin orbit. So this will be possible in a few months. And it should be very easy to implement because for most codes, it's just a matter of activating certain input flags. So that's for the first part. So if you want the version you find online now, no, for the common workflow, but it will be there, I think, in a couple of months. For what concerns the vanilla functions, that's also another completely different topic if you want, but very important. And I'm working on this personally. Already last year, we published a paper where we show using the SCDM method how it's possible to give a structure. And in the case of Quantum Espresso, run the Quantum Espresso calculation, then run the vanilla functions without having to specify the input, the input projections. There are a number of other efforts also in the literature in the past few years which do something similar, but what we did was fully implement into AIDA, and actually there is also a tutorial online. Maybe when I stop sharing, I will put in the chat a link to the tutorial. So there is an example where you can, in a virtual machine like Quantum Mobile, you put a structure and we give you the final vanilla functions and interpolated band structure for you. And what we are doing now is not part of what I presented, it's part of our research. We have a new improved method for automatically choosing the vanilla functions and finding the vanilla functions, which is much more robust also in the case of spin orbit, which was a bit, I think, the weaker aspect of the SCDM method. So hopefully this is something we're going to run in this big run in Lumi in a month. And so hopefully by the end of the year, we'll probably have a preprint where we explain this, and also the code will be available.
Thank you very much. Looking forward to your progress.
Thanks.
Yes, another question a bit related to what was already mentioned, but I have seen that you plan to have the phonon calculations implemented on top of PhonoPy, which I can understand because I guess this will be a very general tool for all engines to be able to generate the phonons. But on the other hand, one also knows that using DFPT is more well efficient in order to compute phonon band structure. What is your plan in the future with respect to such formalism like DFPT that are not implemented in many codes but still can be very useful in some situation?
Oh, that's an excellent question, thanks. And indeed, I mean, I realized when I'm now coordinating this project with 20, 30, 40 people, maybe more, it's very important to try to be kind of concrete and practical and decide a minimal deliverable which is still valuable, and then build on top of it with the idea that this can be extended. So in practice, we decided to go for PhonoPy just because in this way we demonstrate the value of this common relaxation workflows, and because it's easy to do for all codes, as you say. But once the common interface to run a phonon calculation through PhonoPy will be written down, and this will happen hopefully in the next 1 or 2 months, it's going to be, say, easy, quotation mark. It's clear, let's put it this way. I mean, not easy, but clear for an expert person of a code, could be a Binit, Quantum Espresso, or any other code implementing DFPT, how to just map the common inputs to their own workflow inputs for their code to run the FPT. So I don't see, so the fact I mentioned PhonoPy is just a practical issue, just to demonstrate it works and make it available for free for all implementations. But definitely I see, codes like Abinit or Quantum Espresso implement, or many of them already have actually Python implementation, I guess AbiPy for you and our IDA workflows for us, which can compute phonons for the FPT. They should be at the point relatively easy to map the common inputs to those workflows.
Thanks.
Okay.
In a sense, just to conclude, in a sense, this will give the responsibility to the user to decide at point which implementation to use, and they can also actually compare and things like this. Sorry.
Okay, I have one more question. So I think the point to have these common workflows to compare performance among different codes. And then for example, I show some, even the overall agreement is good between different code for aluminum equational state, for example. There are still some small difference. So in this case, we want to make sure we do apple-to-apple comparison. I think the biggest, well, of course, we can choose the same functional, no problem. But I think the biggest possible difference among the code are basis set. So I think it's very hard to compare like a plane wave and the numerical basis set and the local basis set like a Gaussian type or Slater type. For example, the 400 EV in plane wave cutoff is equivalent to, it's a triple zeta in numerical basis set, or 6311 G++ in Gaussian basis set, etc. How could we make a real, I mean, they are equivalent in terms of basis set. I mean, the level of convergency, as you mentioned earlier, 90%, we cannot reach the full convergency for sure. For practical application, but we want to make sure we reach the same level of convergency. So in both, in all cases, there's, for example, 90% of convergency. That's a fair comparison. Otherwise, if there are any difference, we are not sure where it's from. It can be just convergence level are different.
Yeah, no, that's
the same thing for the shoulder potential, right? They could be different. Yeah, that's sort of.
Yeah, so maybe to answer that, indeed, the first thing you want to compare the same level of theory. In this first demonstrator, if you want, we used only PB, but we're already discussing how to make for the DFT implementation. And now they are all DFT, but in principle, the common interface could work also for non-DFT. But for the DFT implementation, we are now defined how to define in a common way the functional based on DBXC. That's what our plan. So we will be able to switch this. Now, in terms of basis set, you're right. That's the main difference. But as you see here already, of course, there are differences. Like CSA for some reason is different. This might be because of the basis set. But indeed, the way, I agree what you say, the way in which we can decide if two set of parameters for very different basis sets are equivalent is exactly by having a quantitative error. And this goes also in the direction of error estimation of DFT calculations, because no, you have here all electron, plane wave, localized basis set. You can say if the delta factor is within 1%, that's the kind of level of accuracy we want to achieve. And that's what for us means having a precise protocol. Maybe a fast protocol means 10% and a moderate protocol means 5%. So indeed, the way I see we can make this equivalence is by looking at the results and defining an accuracy level and making sure all the results are with that accuracy across the periodic table. An important point you mentioned correctly is for pseudopotential code, the pseudopotential. That's why I say the good thing that for the elemental element was already shown in the Delta study. We have now pseudopotentials which work relatively well. What we will see now that what Stefan is doing, and was already shown yesterday, and we will hopefully do more in this in the context of this work. Sometimes the pseudopotential may not be good enough yet for more complex system with oxides and different oxidation states. So indeed, this work might point out the need of improving certain pseudopotentials for certain codes. But one thing we try to do is to compare also very similar codes, let's say, I don't know, Abinit and Quantum Espresso, trying to use the same pseudopotentials, same cutoffs, etc., to see where the discrepancies come from. And actually, I can tell you one thing which maybe was a bit surprising for us, is that there were kind of important disagreements due to this choices mirroring and sizes mirroring for methods. So even things which one might not think immediately to are at this point start to become the important discrepancy reasons. Here I just maybe show an example of a preliminary result of quantum espresso runs against Win2K runs by Stefan. And some come very well, some come very different. We are in the process of investigating why they're different. Some can be pseudo-potential, some can be smearing, some can be something else. Our goal is by the end of the year to get to a very good agreement for all of them, for all the codes.
Okay, thank you. So we still have 15 minutes for the discussion. I think this is the discussion session for all talks. So if anyone have questions about Nomad, so I think, yeah, Marcus there is waiting for questions, right? I have some questions about Nomad. I think the first question about Nomad is about impact, how to evaluate the impact of Nomad. So my personal thought is we cannot evaluate a Nomad as a, of course, if the publication is one of them, but it's not a major merit for evaluating Nomad. I think, so now people are proud of a number of papers indexed by ICI, for example. But in future, would it be possible people are proud of how many my own data are indexed by Nomad, by giving Nomad DOI. So number of data indexed by the Nomad, maybe if we become a kind of standard in the field, I think that's a value of Nomad or impact of Nomad, just like ICI or other similar merit. Another thing is that I think the number of users or number of access users or the number of local copies download. That also, I think, it's an important measure for the impact of Nomad. I think that sort of thing, I think more practical rather than just number of publications or because this is a database should be used in practical application. That's kind of my view. I think also similarly for for the AIDA workflow. So if that workflow, I think is very common to many code, if it can be shared or standardized, so people don't have to develop their own workflow. And then that's also easy for comparison for different system, something like that. So standardization, I think it's at the biggest impact of Nomad. Also, I think AIDA workflow.
I think
that's my personal thought.
Yeah, let's take this as a very general question to all kind of databases, code systems, whatever, right? Because this is basically, you can ask this to everything, how to measure the impact of some methodology database or system. And I think that's the problem with metrics overall. There's also a big discussion in publications, I think, is that if you just count numbers, you often miss stuff, right? If you think about calculations, for example, they could be very, very compute intense and work heavy calculations that people have put in much work and stuff like this, and others are just run like the full thingies that you just try out when you download the code or something like this, right? So it's really hard to make a comparison just by numbers. But with metadata available, maybe you can make a better assessment and say, okay, this is like a calculation, or this is like a property computed with has a like giant workflow behind it, and it was run like for weeks on an HPC system, and this is something that just someone computed on his laptop in his time. These kind of differences you want to capture. And I think the user numbers that might also like be super deceiving, depending on how you lure your users in and how you, I don't know, capturing what does it mean to use a system well and use the system with some impact. Only the number is like also very difficult. And the other question is, of course, what do we actually want to have with these impact metrics? What do we want to measure by these impact metrics? Of course, it's important feedback for the database, for example, to see where can we improve and how does it develop. Like, do we get more impact or less impact, and what can be improved on the platform? That would be one thing. But besides this, why is it so important to have these metrics, and what are other use cases for these kind of metrics?
Okay, thank you. Also, another comment is about the fusion of data. So, I think now we mainly focus on vast data calculation as the AIDA's or effort. So there are so many quantum code. So if we can fuse the data or combine the different quantum code, result, and put into one big database, because they share the common, say, properties like elastic constant, something, and then that would be make the NOMAD even more useful and become sort of more unique. If someone want to do AI analysis, you have a better or bigger combined or fused database, and then people prefer to use this one, or probably the only choice. Then that would be make NOMAD like a unique choice. And then that, well, of course, cite NOMAD, because there are no other place can do this. They cannot hide this fact. And then that would be, I think, another way to, to become more unique. That's another way to make a more impact. That's my point.
Yeah. That's maybe also not really a NOMAD question, because we have to be honest here, right? We to some degree we are competitors. We have like different people, different databases for different needs and with different use cases in mind. But in the end, we are also like kind of competitors and trying to find impact in the same sphere of influence, so to speak. But I think it's fair to say that most of the databases systems out there, that they have their specific applications and specific niche. No, not niche, that's the wrong word. I don't want to bias this. If you look at it, it's like trying to be very general, trying to offer all kinds of data from everybody, and then trying to have the metadata. But this also puts a lot of burden on our users, because they have to identify what are the good calculations, what are the bad calculations for them. And other databases, for example, or something like the cloud might be then better for them because it's more specific. It's easier to find like high value kind of workloads run in certain systems that you're interested in, then it would be on NOMAD. So I think that all the competitors out there, so to speak, have their own kind of thing, speciality. But anyhow, in the long run, it would make sense if we like, and Optimate, for example, is one of these initiatives, like where we try to put effort together and try to standardize something that connect the different systems a little bit at least. So yeah.
I was actually going to comment on that line. You're perfectly right that we cannot avoid some form of competition between different projects. And so, I think that the way to go is indeed to have the same query language to query the different databases. And then from the user point of view, it doesn't care whether the data is here, there, or elsewhere, provided that he can query the database in the same way.
If I can add maybe two comments, one on a previous question about ontologies, and then another comment. So the first one about ontologies, in the way we see our common workflow implementation is a kind of a way to help defining ontologies for material science. So by having now an implementation that works with some kind of standardized input format, is not yet at the ontology level, but it would make it easy now to, and actually next week there is a workshop about this, where actually many people and probably here are going also to participate exactly on ontologies. And I think my idea is that we can use these or other similar efforts like ASR from the ASC group to define ontologies for material science. And this part on ASR actually comes to the question of Marcus that he wrote in the chat. So maybe I try to quickly reply to that as well. He was asking how our effort compares to other workflow engines, in particular like exactly ASC and ASR. So I think ASR is in a sense in scope is very similar. They also define the concept of what a calculation is, and I have to say they are much more advanced in the list of properties they can compute. They have a quite very extensive long list of properties. On the other hand, I think we are more advanced in two aspects. And again, it's not a competition, just to, I think, to say what the status is. On one side, I think is the robustness aspect, where in AIDA we have all these features in many of the codes to take care of failures, and they have this concept of restarting, etc. It's not just a single run. And the other thing is that they acknowledge in their paper, in the ACR paper, and the conclusion that while the concept is exactly designed to be decoupled from the actual code, they acknowledge, I'm reading here from the paper, the coupling is not in place, and the majority of recipes are actually specific to the GPO electronic code. So I think that's okay. Of course, it's a starting point, and I'm pretty sure being based on ASC would be easy for them to extend to more codes. But I think we went into kind of two orthogonal but both very important directions. For them, it was to define as many properties as possible. For us, was to define few properties to begin with, but implement them from many codes. And I think putting these two together will be very powerful. And if I see also potential for interaction between the implementation at some point, which doesn't mean reusing the same implementation, be one calling the other or things like this.
I think this is a good general point, right? Because when you want to overcome heterogeneity and join information in general, going for the overlap is always like pretty easy, but usually overlap's like super small. And when you want to go away from the overlap and go into the specifics, which often is necessary for many use cases, then it becomes like far more complicated. And these are the challenges that I think most of the databases and everyone is facing. It doesn't really matter if you want to integrate a calculation into a workflow system or into a database or make it available through API. There's then always the same questions. How can you standardize these specifics? And with Optimate, for example, we are at a point where we're very good at defining the system and everything goes in there. But then when we think about workflows, when we think about properties, then it becomes far more complicated because everything then so different.
I was going to add in the same direction as Giovanni was pointing. So the effort of the common workflow is there's one workflow for different codes. And now we have the other step that we have to bridge, I would think so, is that there are many different workflow managers, and it would be nice to have some kind of common workflow language that is accepted by the different workflow managers in such a way that then, you can have the different workflows managed by different workflow managers with different codes, ideally. That would be indeed very powerful, but it's a long way to go, I think.
If I can give a direct answer to this, to Gianmarco, I think one has to be, I think my gut feeling, I don't have a response, but my gut feeling, one has to be careful at which level one want to make this common. Of course, many of all of these workflow engines, AIDA, but could be ASC, could be Fireworks, have their own specificity and their reason they are like this, and actually it's good, sometimes they're a bit different. I think it's a bit dangerous or risky to try to really go to a kind of converter of the workflow between one language and the other. I think a practical approach would actually be to maybe exactly on the direction of ontology. So we agree that the concept of relaxation of a crystal, so what is a crystal structure? What is the concept of relaxing a crystal structure? And through an ontological definition, we have a way to say, I want to do this relaxation for this structure with workflow engine ABC. In a sense, it's going one step further. What we did for, I want to relax with this code, we would do for the workflow engines. And then I think this could be a practical way, because in practice, because of technical and maybe also psychological or historical reasons, it's going to be very, very tricky to merge them, which I think is not possible. But also converting between them, I think that even if they're all using Python, it might still be technically very challenging. You have to read the Python, parse the Python code and convert. So maybe that's not what you had in mind, but yeah.
No, I fully agree, Giovanni, that it's not something that's going to be easy. But if you take the point of view of a developer of a code, once or a developer of a new functionality. Okay, so for instance, we've been working here on an electron phonon coupling, and so we've been implementing a workflow first in the Python package that controls ABinit. But then, ideally, we would like that workflow to be usable by the different workflow manager, and otherwise, it means that we have to implement that workflow once in ASR, once in Fireworks, once for AIDA, and you know, if some other people come up with another workflow manager, then it means that from the Abinet point of view, we need to develop plugin for every single thing. So that's not feasible.
No, I totally see, and I see your point. I think I get the challenging part will be to understand at which level the things are common. But I think you have your specific use case is very good because you're interacting with probably all of them. So you need to, I know you're planning to solve this issue. So
hopefully.
So I think when we talk about what Gianmarco just said, right, I think the first and maybe the most important step is to recognize the steps in a workflow that has been used, right? Not necessarily that you go from this is my abstract definition of a workflow to doing this workflow in different managers, but be able to kind of see that this workflow in this manager is the same in a certain sense to what you have been doing with another workflow, right? So that you kind of pull this metadata out of one workflow or another workflow from different parts, right? So that you can kind of merge and be sure that you have the same data. And then the design of a certain workflow can be kind of compared to the design of another one. If you kind of have these ontologies to kind of map an abstract workflow to the different ways it has been implemented in the different packages.
Perfect. Actually, now is the time of ending this session, but of course we can continue a little bit. Any more questions, or just we finish? Oh, seems
we have one question in Louvain.
Yeah.
So thanks for the for all the people here. That I want to ask for the database developers and the framework developers that if you can share some experience with the like DFT code developers. That for example, if when you develop the workflow, like in AIDA, you have something like every code can say that I want some calculation to be with just input of precision with high, then perhaps every code is working on to simplify the user input to achieve this, but they are all having their own recipe. So is it possible that like the framework developers to share the experience, or to make it possible to for the DFT codes to make a common effort to make a recipe on how to make this possible? And another thing might be that for the to define perhaps what the future DFT code should do to adapt to the frameworks. Like every DFT code has its own method to do the relaxation, to do the MD and things like that. But now in every framework, I think that is also implemented. So perhaps for some DFT code, it doesn't have to put a lot of effort to do this, but it's possible that if you can share the experience or how to make the code more adapted to the frameworks, and also the input and output, how to make them more easier to be passed by the framework and the databases. And also if we have a standard like input output, when we put that into the database, well, now that if all the data is stored in some kind of database, but still sometimes we want not just the data from there. Every code has its output, which has its specific output, which is perhaps not inside the database. And if we can make an effort to standardize the outputs and inputs, then and also the post-processing scripts to then that can be shared by all the codes. I would like to know your opinion about the impact when these data frameworks can make this happen.
Do you want to start, Giovanni?
Maybe I can just give a quick answer. Then, unfortunately, I need to run away in 2 minutes because I have a doctor appointment for my kid. So I go and I let you continue. So it's a very important question. I can tell you practically what we've been doing. So already in our specific high throughput runs with Quantum Espresso through AIDA, we've been in contact all the time with the developers to give back the feedback on what we learn about the codes and code failures. In the end, many of these codes have been designed before the era of high throughput, and so they would run for simple inputs. But when they're put to the test of running a lot of materials, a number of things happen. So that's definitely something very important. I think for any other workflow engine, other workflow developer, having a direct contact with the developers of the code is key. Also because for me, the things, part of your question was about what can we do to make the codes easier to interact. I think there are 3 important things I see from my experience that a code could do to be ready to be interfaced with a workflow engine, etc. It's not much for me having a common input or common output. That's something we can define a posteriori. We have been writing a lot of parsers. The Nomad have been writing a lot of parsers for various codes. Of course, if we cannot unify, it's good. But for me, the important thing is reliable format for the output. So a machine can parse it independent of the version of the code. The format doesn't change, so the parser doesn't have to change. A reliable way to detect warnings, errors in a robust way, because you want at least to detect them and inform the user there was an error. And more generally, that's maybe the most important thing, is the robustness of the engine. You want, and many of these robustness aspects, capability to converge to a correct solution without crashing, is something that very often has to be or should be implemented in the code. And in this sense, interaction, I think, with developers would help. Of course, the workflow engine can do some tricks and workarounds to try to make it work, but very often, as I mentioned earlier in my example, we went to 80% to 99% success rate because the code changed the algorithm, not because we fixed something from the outside. And the final note, there's a different community, the MOL SSI I'm aware of, that actually they managed to kind of put together people and really have a kind of common format for inputs and outputs for quantum chemistry codes. That's quite interesting as an effort. I think it's a bit more challenging for us in practice. And again, I think it's not the first priority. I would say it's the second priority. That's my comment. And then maybe I'll let others, maybe Marcus or others reply. Yeah. Unfortunately, I need to leave, but I will be there in the afternoon. Sorry.
Thank you, Giovanni. Yeah, I can put a few cents to this. So first of all, I agree with what Giovanni was saying. And yeah, when you look at this, it's like different levels. I would say first is like the data format itself. Right? Putting out ASCII files doesn't make it easy to parse them, right? If the data format itself would be like more formal, let's say you use HDF5 or you use JSON or you use XML or whatever, that would be a first thing that makes it much easier to consume the data that you're producing. Also for inputs, that it's the same thing. And it's like, I think that even the code developers should think about this, finding definitions and schemas for the data. And you have all written documentation and stuff like this about what the different parts of the output mean or what the user needs to be inputting. But if this schema could be formalized as part of your code base, basically, right? It should be part of your software that you say this input has this name and means that this and that and has this unit and shape and so on and so forth. These kind of schema information would be there, and then it would also make it a parser developer, for example, or someone who wants to integrate the data would have a much easier job. Or deriving ontologies for all this information would be much easier if there would be also already some kind of formality behind the data that you use it as inputs and outputs. So for a very long time, code developers basically just being on their own, developing their code and being fine with this, and then physicists trying to understand this. But then you have like all the workflow engines, like ASE, for example, is like trying to build all kinds of parsers and producing inputs for various codes. The AIDA guys are doing this, Nomad guys are trying to produce parsers and something like this. And Giovanni is fine with it, but I think it would still be much easier if like you would make it easier for the parser developers to build these kind of things. But in general, data integration and data formats. It's like a messy business. It's probably not 100% avoidable, but going for some levels of standardization would be great. Even if it's just bits and pieces, like for example, you could pick up on the Optimate standard to just have a common format for inputs, like how to define a system, for example. Already make stuff much easier. You saw this in Giovanni's presentation. He was like integrating with other databases using the Optimate API, and you suddenly can pull a crystal from this and there and then put it to your workflow. These kind of things would be then possible. Yeah, and of course the ontology thing is something that we should pursue as a community as a whole, right? And everybody should take pieces of this and try to integrate their parts of the chain with it, like being a co-developer, so database maintainers.
Yeah, I fully agree. So it was pointed actually by Mikil a bit earlier that for the input-output, I think that there would need to be something which is an API, again, that is kind of stable in time, and to which the different codes can then write their specific Python interface in such a way that, you know, they are responsible on how they generate the input from something that is common to all the code to something that is specific to their own code, and then they translate the output of their specific code into something that is common. I mean, that's some work that we did in the framework of ABIPy, where we translated that into stuff that was understandable by Pamagen, but it would be ideal if there was something that was understandable by many different things again. So that's this kind of API common to many different things that would be ideal to define in some way. And indeed, Optimate can serve as an umbrella for developing something like that.
I think it's very important but because if you look at the whole chain, there's so many translations involved, right? Yeah, so like, let's say you take a code, it takes input from something like ASR or what we just saw. So there's one translation for the input, and the code produces something. It has to be passed again by the workflow engine to make sense of it. Then the workflow putting everything together, also producing some form of data. Then the database like Nomad picks it up and tries to parse it again. And then in the end, you have so many translation steps that lots of stuff gets lost in translation. Right? Yeah, and if we could agree on a common ontology and then derive of this on the common format for like most of the information that we have in material science, then it would be much easier because everybody could already put the information already in a form that's that everybody understands, and then there wouldn't, like, we would all speak the same language to keep up with the translation metaphor.
Indeed.
I guess it all starts with machine readable output, right? I mean,
yeah, that would be the big
one. Fast made this step to XML output. In Abinit, we have the netcdf files, and that basically means that it is something you can read and that can afterwards be, you can add things to this, right? And it's still there, but what you have there is still there. But like parsing these human readable output files that then from one version to another version have one empty line somewhere more, that's obviously the biggest horror nightmare for all of these frameworks. So I think if anything, that would be the lesson or like the message to the code developers, right? Please provide stable human readable, machine readable output files.
Yeah, that's totally that's totally right. That it has some baked in backwards compatibility. You could just, with XML, you could just ignore stuff that you don't recognize as a parser and still pick up on those things that you know.
Yeah, exactly. So that it stays what it is, right? So that the output stays what it is, and that there can be more. Like XML will do this in trees, a JSON file will do this. If it's just a dictionary, you just pick up what you know, and what you don't know, you leave, or you kind of add the procedure in there. And the same goes for the netcdf or HDF5, right? So it doesn't really matter. I think then in the end, it doesn't really matter that much, as long as we at least start to stick to this paradigm.
Maybe you can stop here in order to have a decent lunch.
Yeah. So maybe, yeah. So so thanks all the audience on site and online also. I think as a few words, I would like to add a little bit more. So I think we have a big word. So we allow the freedom and you know, of course we hope we have more standardized format input output. Also AI may handle some integration standardization, but actually that's the point of a big database. So if the result from different code come into the database, they have to be standardized or they show their original intrinsic meaning. So that's also a way to move to the unified knowledge or that by the database, or even across different format or for different database. I think in scientific world, still we have more unified or common language than political or other system. So that's my ending words. So thanks for everybody. I think I finished my job today. So thanks for the invitation. I think maybe also interesting across different part of the world, the conference. I think we have also do broadcasting online in China. We have a lot of Chinese audience, not in this room, but online. So, so thanks for this great opportunity to share the knowledge and your suggestions. So I think I finished my part. So thanks for your invitation. Hopefully see you sometimes again. So back to the host conference in Belgium. Yeah. Okay, so let's just end of this session.
afternoon session. So I'm Gianmarco Rianese, and I'll be chairing the session, which is about machine learning. So we have 15 minutes introduction, in which I will give about the topics that will be covered in this session. So as we have seen in the previous talks, there's a number of computed materials database properties that have become available online. So we've already seen a few talks about Flow, or QMD, Nomad, the Materials Cloud. We haven't seen the Materials project yet, but there's going to be a talk related to that this afternoon. And then one has to realize that when you have to compute materials property, the time that it takes, sorry, the video didn't change compared to my screen. So the time that it takes to compute different properties can be quite different. When you compute the structure, properties related to chemistry or to the electronic structure, that's rather small compared to the time that is needed to, say, compute the elastic properties of a system or the piezoelectric properties of a system. And so it's not surprising that when you look into the databases that I was mentioning before, most of the information that has been computed is related precisely to those properties that are easy to compute, because it takes a huge amount of CPU hours to compute properties anyway. And so those that are more complicated have a limited amount of data. And so this is where machine learning can really become important, because it can help for those properties that have not been computed in a large amount to train the machine learning model, and that gets some idea of an idea of the range that the property can get for some materials, and then maybe do an actual calculation that is long, but you can afford it when it's for a limited number of materials. And so we have seen that material science is actually witnessing a shift to the so-called fourth paradigm. So we have the first three, which are empirical science, theoretical science, and computational science. And now we're moving to this big, and the big is between parentheses, because we know that indeed there are cases in which there is a limited amount of data. So big data-driven science. And so this can be seen if you look at the number of publications that is growing almost exponentially. So you can see that now. And so what we are going to have here this afternoon is discussing about that. And so what is nice about the fact that the field is growing is that you can find plenty of review articles. If you're new to the field, you can go through, just search a review about machine learning in material science, and we will find really plenty of those. There is a huge number of those. Okay, so in all the cases, what machine learning will be used for is this idea of going from the processing condition that I use to synthesize a material, then the structure that these materials get, then move from the structures to the properties, and finally get the performance of the material. So the first step, this relationship is a relationship of cause and effect. The process induces a given structure, the structure induces the properties, and the properties induce the performance. And so the materials informatics can generate such forward model that can allow you to predict, for instance, the property as a function of the processing condition, the composition, and the structure. That's an example. But what we are interested in also is to go the other way around. Is, let's say that I want to achieve a given performance. What is the processing? What are the structure that I want to get? What are the properties that I need to have in order to achieve that performance? So that's this inverse relation, which is called the inverse design, because we want, for instance, to maximize a property such that it meets my requirement for the application that I have in mind. In all the cases, when you do these kind of things, the first part is to featureize the data. And so that's really a crucial point. So for instance, if I take the example of going from the structure to the property, I want to convert my crystal or my molecule into a bunch of numbers that describe the structure. This is a vector of number that basically describe this the structure. And so this afternoon, we're going to have a number of different such featureization process that will be used. So in the talk of Elias Vliek, I saw that he was using DeepChem, which is a repository where different ways to transform a molecule into a number of descriptors are used. We're going to have a talk by Anubhav Jain, in which will use MatMiner, which is also another repository that generates a bunch of features based on the crystal structure. We're going to see that in the talk of Yusung Jun, so the first speaker, that uses invertible image-based featurization because it is clear that the field of machine learning developed quite a lot in the field of images. And so there's a lot of featurization that has already been achieved and studied different methods as far as images are concerned. In the talks of yesterday, we've heard about SOAP, ACE, and there are many more that I'm not able to cite now. So in this afternoon session, so we'll first have several talks that will deal with this forward relationship that goes from the cause to the effect. And with the first talk by, it's actually not the first talk of this afternoon because of the time schedule. So the first talk by Elias Vlieg is going to be about he's coming from the Radboud University in Nijmegen in the Netherlands. And so he's going to speak about how artificial networks can be used to make predictions about co-crystals. So the idea is that you have two molecules and you see whether or not they can form a co-crystal together. So we'll learn about much more about that in his talk. Then there's going to be a talk by Asaf Anderson from Tel Aviv, Israel. So he's from a private company, Materials Zone. And because it's a private company, actually, I was not able to find exactly the kind of methods that they are using. So I'm not able to, to identify which of the methods they are using. And so I guess that we'll learn much more from that from Asaf. Then in the talk of Anubhav, he's going to be presenting something about benchmarking the different models that have been defined, because there are different models that are available from machine learning, and they have developed a workbench where you can test the new methods that you develop and see how they perform compared to previous methods. And then finally, the last talk is going to be about the inverse design thing. So that's, developing a material that is such that it will have a targeted performance. So that's the performance that guides the whole chain of processing structures and properties. So that's something that is called inverse design, and that will be covered in the talk of Yusung Jun from the Korea Advanced Institute of Science and Technology. And so it will show us how they handle that. Among other things, what they have to define is to have something that is called an autoencoder, and that allows to define a latent space. And just to give you an example of what can be done with that, maybe some of you have seen that, again, coming to images, which is the field in which the machine learning has developed quite a lot. So what they've been able to do there is to define the latent space that allows them to identify, in the case of faces, to identify the region where the pictures look like much more to a woman than to a man. And as a result, you can take one existing picture and push it in the direction of making it more women-like or more men-like. And so this is something that if we could do something like that with materials, we would be able to define, say, for instance, a direction in which a material becomes more conducting or less conducting, material becomes more transparent, less transparent, stuff like that. So this is really something that we should try to aim at. I know that is something difficult, but I hope that we will hear about that in the talk by Yusung Jun. And so with that, I have finished my presentation, and as usual, I was quite fast in doing that. So I don't know if there are questions about my introduction. Otherwise, we can start a bit earlier with the first talk. I don't know if Yusung is here already. Yeah, yes. Yeah, I'm just going to present the order of the presentation, and then the word will be yours, Yusung. So the first talk indeed is going to be by Yusung Jun. Then the second one is going to be by Elias Vlieg, who is here in Louvain. Then we will hear Asaf Anderson, who is in Tel Aviv. And finally, after the coffee break, we'll hear Anubhav Jains, who is in California and most probably still sleeping a bit at the moment. So Yusung, the floor is yours. You can share your screen and then start your presentation. We're a bit ahead of schedule, but I think that's fine.
Okay, thank you very much, Gianmarco, for a very kind introduction. And also, thank you very much for introducing our paper on the image-based representation of the solid-state structures. Incidentally, I designed my talk such that I will not just focus on image-based representation and its application to generative model, but also general overview of research along the use of machine learning for materials research that's going in my group.
That's perfectly fine.
If that's okay. Thank you.
Perfect.
So yeah, so thank you very much again. It's a great pleasure for me to.
Maybe you can put your screen in full screen mode because we see the slide on the side.
Okay, yes, I can do that. So let me see.
It's probably the arrow there, yeah.
Yeah.
Great.
So yeah, so it's a great pleasure for me to be part of this FAIR-DI workshop, and as we all know, in materials informatics, basically, what we want to do is to understand the structure property relationships of the materials based on the data, and then we really want to predict the property of the materials given the structure, and that's the forward prediction, and also as Gianmarco mentioned. You can also go the other way around. In other words, we define the property first, and then property that you want to achieve, and I try to come up with a structure that would have such a property, and there will be an inverse design. And so by doing this kind of mapping forward or inverse, you basically want to dramatically reduce the time and cost for the novel discovery. There are several ingredients that are needed to do the materials informatics. By the way, do you see the old title, or do you see
perfect.
This?
We see everything.
Okay, great. So there are several key ingredients to the materials informatics, and of course, this is data-driven approach. You need the data, and you need the representation for the materials. And once you have the data and representation, then you can perform a simple regression to make a model that would allow us to do the property predictions. And once you have such a tool to make a property prediction, the next important task, perhaps much more challenging task, is to explore the chemical space to pinpoint the material or molecule that would have such a target property. And this is very difficult because the chemical space is essentially almost infinite in practice. And so it's almost like finding a needle in a haystack. And the third aspect is that we more or less all know that many of those materials that are computationally designed, if not most, are discarded in the laboratory because they are not synthesized. And so it'd be good to have a model that would allow us to predict the synthesizability of those materials ahead of the experiments. So today I'm going to talk about some of the works that have been going on in my group along the lines of these three different subjects. So there'll be a short intro of my talk, and I'll start with the property prediction. And so, like I said, once you have the data and representation, then you can perform simple regressions and make a property prediction model. And so far, these kind of prediction models are mainly based on feature engineering. In other words, you basically come up with features that would represent the physics of the property that you are interested in. And for example, for catalysis applications, where you, for example, want to predict the binding energy of CO on top of various metal surfaces, and you can use some kind of mean field descriptors like electron negativity, radiative band width, and then you can sort of predict the binding energy using these kinds of mean field descriptors. But these kinds of feature-derived descriptors are promising, but they could be cumbersome, because if you want to predict a different property, then you need to come up with a different set of descriptors. And also, these kinds of features are heavily dependent on the expert knowledge that could differ from person to person. And so it'd be good to have descriptors that could be generally applicable regardless of different properties. And so to do that, people are trying to use a structural encoding. And this is similar to situations in electronic structure calculations where you basically use Hamiltonian of the system no matter what property that you're calculating. And so because regardless of properties, you basically use the coordinates of atoms and identities of atoms, and that's all. And so you can sort of expect similar things in machine learning if you do some kind of structural encoding. And there are a number of different ways of encoding the structures of the molecules and crystals. And one of the more promising approaches is to represent the molecules and materials using graphs. In graphs, representation is basically represent the atoms as nodes and chemical bonds as edges. And by sort of a mathematical operation called convolutions, you can incorporate the information of the remote atoms locally. And by performing several such convolutions, you can basically encode the information of the entire molecule. And these graph methods have been shown to yield promising performance for different properties for molecules and crystals. And for catalysis application, again, Ulysses group showed that they obtained about 0.13 electron volt better for the prediction of CO and H binding energies on different metal surfaces. So it was good, except that in order to use graph, when you make a prediction, you basically need the structure of the material. And so in practice, in order to use this kind of graph model, you basically need to perform DFT geometry relaxations ahead of time. And of course, if you have already done the DFT relaxations, there's no need to use a machine learning model. So the motivation of us working on this field was that it'd be good to have a model that could predict the binding energies without geometry relaxations. And so to do that, to that end, we basically removed adsorbates on top of the surfaces and label the active site atoms in a pseudoatom, in a fake atom. And instead of encoding the adsorbate bound structures, which needs to be optimized, we basically just encode these slab geometries with the active sites labeled in different fake atoms. And so by doing that, you can actually remove the geometry relaxations and you have the adsorbate bound. And also, even these slab geometries can be obtained from the bulk optimized structures from, for example, Materials project databases. And then you can completely remove all DFT relaxations associated with the prediction of binding energies. And so we benchmarked our method against a couple of methods in literature, and we obtained the accuracy pretty comparable, or sometimes slightly better, sometimes slightly worse than these existing methods. But the key difference is that our methods does not require the geometry relaxations, either surfaces or adsorbate bound surfaces. And so without that, this could be used as a practical way of representing the catalyst surfaces for binding energy applications. And in fact, we sort of the motivation of us working on this subject was to study this kind of system. This is a jagged platinum nanowires, and this has been synthesized by the Duan group in UCLA. And they started with the nickel platinum straight binary nanowire, and then they somehow de-alloy the nickel atoms, and then they are left with only platinum atoms. And along the way of de-alloying process, this structure of the nanowire becomes very rough and jagged, ups and downs. And they show that this jagged platinum nanowire exhibited very high specific activities for hydrogen evolution reactions and oxygen reduction reactions. We all know, or some of us know, that even for the same platinum, depending on different surfaces, 110, 100, or 111, because they have different coordination numbers, they have very different activities. And having said that, you can easily imagine that this kind of very much amorphous platinum nanowires would have all sorts of coordination environments. And so in order to understand the experiments, you cannot use a couple of ideal surfaces. And instead, you need to be able to evaluate every single active site of this entire Jagged Platinum nanowires, and then take some kind of ensemble averages. And so to do that, one cannot simply do the geometry optimization for every single site, and that's where we needed this kind of method, which allows us to predict the binding energies without geometry relaxations. And so we did that, and then we did some kind of multi-scale microkinetic modeling, and then from that we obtained current densities as a function of the potential for the hydrogen evolution reactions, and the circles are the simulation results using our method, and this solid lines is an experiment, and they have a pretty good agreement. And the other experimental parameters are also well reproduced. And so by establishing this agreement between theory and experiments, we were able to understand why this Jagged Platinum nanowire showed such an enhanced activity. Hydrogen evolution reaction usually consists of two steps. First step is the adsorption of hydrogen from water onto the platinum surface, and the second hydrogen comes in. And then these two hydrogens are coupled and to produce hydrogen molecules. And the first step is called Balmer, and the second step is called TAFO. And we find that some of these active sites are very good at hydrogen adsorption, and some of the sites are very good at hydrogen coupling. And because the diffusion along the platinum surface is very fast, we find that hydrogen basically gets adsorbed on the Balmer favorable site and diffuses through to TAFO favorable site and get coupled to evolve hydrogen molecules. And so it's basically a bifunctional mechanism, but it differs from the conventional bifunctional mechanism in the sense that in conventional cases, you basically have two different materials, one material doing one good thing and another material doing another thing good. And by combining the two, you get the synergy. But in our case, it's completely just a monometallic material consisting of a simple platinum atoms, but it exhibits bifunctional mechanism due to the morphology. So we call it auto bifunctional mechanism, and to our knowledge, this is the first observation of such phenomena. And I want to emphasize that this understanding was entirely possible because of the development of this pseudo-atom site labeling method that does not require geometry relaxations. Okay, so I'm gonna switch it and then to a second subject of doing the inverse design. So like I said, once you have this kind of sort of property prediction models, the next important task is to explore the chemical space. And in this review article, we categorized the strategies for inverse design into three different categories: high-throughput virtual screening, global optimization, and generative models. In high-throughput virtual screening, as the name implies, you basically take the database and evaluate the property of each candidate one by one until you find the target material. But of course, if the target material is not in the database, then there's no chance that you will find the target material. In global optimization, for example, in the evolutionary algorithm, you basically start with some reasonable guess, and then you do some kind of, you evaluate the property of the candidate and do some kind of mutations or crossovers, and you basically balance between exploitation and explorations, and then you try to optimize, you try to find the optimal sort of point. And along the way, you basically utilize the information of the prior visit. And so you can say that global optimization may be more efficient than high-throughput virtual screening. And the third category is the generative model, which I will focus on today. And this is the most data-intensive approach. And in generative model, what we are basically trying to do is to take the database, and you take the entire database, you basically try to learn the distribution of data in the database. And if you learned the distribution of the data, then you basically know where in the latent space you need to sample to get the optimal property. And so by sampling these regions intensively, you basically have a better chance of finding a novel material with the target property. And one of the first sort of works to use variational autoencoders in chemical science is the work by Alan. And in this work, they encoded the molecular structures into the strings format, SMILES strings, and they encode the SMILES information into the latent space, map that into the latent space. So basically, each point in this vector space represents a molecule. And along the training of this autoencoder, you can add a separate property prediction model. And if you, by adding this property prediction model, you can basically restructure the latent space. And so you can see that these red regions and yellow regions, they all correspond to sort of different property regions. And so once you know such sort of a property embedded latent space, then you know where to sample. And you can even do the sort of some kind of optimization by using the gradients of the property. And so in this work that Gianmarco kindly mentioned, we basically extended this variational autoencoder work to the solid state materials cases. But the first bottleneck was to realize what would be the representation of the proper way of representing the solid state structures. And we used images. And so we represent the unit cells using images, and we construct the variational autoencoders. And this is the two-dimensional projection of the latent space. And because we included the stability prediction model along the training, you can see that this latent space is restructured according to the stability or the formation energies of the material. So this is corresponding to the stable materials, and this is corresponding to the unstable region for the vanadium oxide compound space. And so by sort of sampling in this stable region, we were able to find some novel structures. So on the lower left corner, you see this formation as a function of vanadium composition, and these blue circles are the structures that are already in the Materials project database, and these orange circles are the structures that are newly generated out of our generative model. And you can see that these compositions correspond to completely new compositions. And some of those structures are very close or quite reasonably close to the convexal minimum, suggesting that they might be synthesizable, at least thermodynamically. And we then extended this model and explored the ternary compound space instead of binary. And in this case, we also used GAN, to be precise, WGAN, instead of a variational autoencoder. And on the left-hand side, I'm showing you the phase diagram of magnesium mangan oxide ternary compound space. And these red circles are the existing materials in the Materials project database. On the right-hand side, I'm plotting the same phase diagram, except that I added these red circles are corresponding to the structures generated from our GAN model. And you can clearly see that by using GAN, you can basically fill up the hidden portion of the chemical space between the known structures. So basically by using GAN, you can explore the hidden chemical space, hopefully efficiently. And because we chose this system, because this is some compositions of this compound space are already known to be active as photoanode material, we then examined whether some of these structures might be promising as photoanode applications. And indeed, we find that some of the structures have reasonably good Poubet stability and band gaps, so that they might be testable experimentally as a promising photoanode application material. Okay, so so in the remaining 5 or 7 minutes or so, let me talk about synthesizability. So like I said, many of these structures or materials that are computationally designed, either using property prediction models or generative models or high-throughput screening, many of them end up being discarded because they are not synthesized. So it'd be good to have a model that can predict the synthesizability. However, such a classification model it differs from the conventional classification, because in conventional classification, you have a positive data and negative data. And by training the model, if you have an unknown data, then by using that as an input, the model will be able to tell you whether the unknown data will be positive or negative. But in the synthesizability prediction task, you only have the positive data and no negative data, because if the material has been synthesized, it's already a positive data. But if it's not synthesized yet, then that doesn't mean that it is unsynthesizable, because it may be synthesized later on. So basically, you only have the positive data and unlabeled data. So for that, we use this kind of iterative, positive, unlabeled learning technique. And I can answer the question if there are questions technically at the end of my talk. So I'll just show the results. So we trained the model with the Materials project, where we have about 50,000 positive data with the ICSD tag, and about 80,000 hypothetical data, which are basically obtained by the substitution of the existing materials. And our model has a prediction accuracy, recall accuracy, positivity recall accuracy is about 87%. To validate our model, we basically only used the synthesized data up to year 2015, and then determined whether that model is able to predict the synthesizability of those materials that are synthesized between 2016 and 2020. And we again obtained about 86 to 87% accuracy. And one thing that we found interesting was this figure. It compares the synthesizability score on the x-axis, 1 being highly synthesizable, 0 being highly unsynthesizable, and y-axis is the thermodynamic stability. And we find that synthesizability and thermodynamics is not correlated. I mean, so including us, we usually use formation energies or energy of a pole as a rough estimate of the synthesizability of inorganic crystal structures. But this suggests that that may not be true. And so there might be something more than thermodynamics for predicting the synthesizability. And on the right lower corner, I'm showing the synthesizability of hypothetical materials of the various databases. And MP database, virtual, hypothetical data, about 20% of them are synthesizable according to our model. And OQMD, in the OQMD case, about 10% is synthesizable. And that means that even if there are many hypothetical materials in those databases, we may not really need to explore all of those for our applications when you perform some kind of high-throughput virtual screening, because even if they are selected as promising, they may not be synthesizable. So if our model is reliable enough, that would save a lot of time and cost. To further validate our model, we out of this 80,000 hypothetical data, we ranked them according to the synthesizability score and explored whether any of top 100 hypothetical materials have been synthesized in literature. We find that about 70% of them have been indeed synthesized. And this is the case where they have been synthesized and they have been reported in literature, but they have not been deposited in the database yet. So this sort of shows that the validity of the model is very reasonable, and so this could be taken as another validation. And for experimentalists, it'd be good to have a model that can predict the synthesizability based only on the composition, because often in cases you don't know the structure ahead of experimental synthesis. So it'd be good to have a model that can predict the synthesizability only based on the chemical composition AXBY, and that kind of thing. And we find we have about 94 to 95% of accuracy, even higher accuracy. And now, since we have the synthesizability prediction models for structure-based and composition-based, we can compare them. And we found an interesting sort of a relationship between the two. So these diagonal parts are the parts where both predictions are mutually consistent. But these off-diagonal parts are parts that where both predictions are mutually inconsistent. In other words, this is the case where structure-based synthesizability model predicts that they may not be synthesizable, but composition-based model predicts them to be synthesizable. So that means that because given composition, there may be different kinds of structures, namely polymorphs. So this sort of 40% of this region strongly indicates that many of the compositions in the Materials project may be polymorphs. They have not been found yet, but they may be synthesizable. So we are exploring along the line. And we apply that to this tonal compound space, barium, vanadium, oxygen space. And these stars are the materials that are already synthesized and reported. And we overlaid these results on top of our color-coded synthesizability map. And these blue regions are the highly synthesizable region, and the red regions highly unsynthesizable region. And you can clearly see that all those structures that have been synthesized lie in the synthesizable region, according to our model. And because our model, this positive unlabeled learning, is ensemble-based method, you can even estimate the uncertainty of the predictions. And luckily, all those structures that have been synthesized lie in the sort of a certain region, certain prediction regions. Okay, so let me see. So this is so far I've been talking about this inorganic sort of materials informatics, but for organic sort of molecular science, instead of a synthesizability, a more proper or relevant question might be synthesis pathway planning. And so we've been working on the prediction of a synthesis pathways for organic molecules. And so, for example, on the right-hand side, you can see that for a USPTO patent data set, there are about 500,000 chemical reactions, and we can derive about 20,000 local reaction templates. By local reaction template, I mean remove all the parts that are same between the reactant and the product, and then you only look at the changes of the reactions between the reactant and product. And this is one kind of reaction template, and you can derive about 20,000 of them by looking at these 500,000 reaction databases. And then you can train the model in short, such that the model predicts the conditional probability of each atom or bonds going through different kinds of reaction template. And so the sort of the dimension of this prediction vector would be 20,000 times number of atoms and number of bonds. And so you will have this ranking system, and then scores give you sort of the reactions with different priority. And we get about 85 to 92 top 5 accuracy. This means that about 90% of the time, the correct reaction pathway will be within the rank 5 predictions. And for example, this is sort of a compound.
Sorry, Yusung, but it would be nice if you could slowly wrap up in such a way that there can be some questions to your talk.
Yeah, so thank you. This is actually in my last slide. So you can apply the same this retrosynthesis model and predict reaction pathways applying the method. Okay, so I've talked about 3 different aspects: property predictions and then exploring the chemical space and the synthesizer predictions, all using machine learning. And these are the 5 students that worked on all the things that I presented today. And I would like to thank my collaborators, Alan, John, Zach, Bill, Tao, and Xiangping. And thank you for your attention. And I'm sorry for taking longer time. Thank you.
Questions in the audience here?
Yep. Thank you for this beautiful talk. My question was about the experimental verification methods that you have. If you talk about the chemical reaction methods of, for instance, your platinum structure. So is there any way to validate the reactivity as you modeled it versus experiments? For instance, on single crystal surfaces, or is there any way to validate these reactivities?
Right. So eventually, the most important task is the experimental validation. So that's a very good point. And for platinum, check the platinum case, there is already an experiment that shows that these jagged platinum nanowires exhibits much enhanced activity towards hydrogen evolution reaction and oxygen reduction reactions. And our model confirms that. So that can be seen as a confirmation. And for other binding energy predictions, you are very right that one has to synthesize those alloys and demonstrate those computationally designed alloys would have the properties that are as predicted. And there are cases where these machine learning predicted properties are experimentally validated. But for our case, we have not. So the very first subject that I mentioned, using these mean field descriptors, we identified several alloys that might be more active for CO2 reduction to CO. They have not been synthesized yet, and so there was no experimental confirmation for that part. And so they might be the case where the synthesizability may also be important as well.
Maybe you can take the question by Hongbin Zhang.
Yes, I hope you can hear me. Thank you very much for this very nice talk. We have been very much inspired by this crystal representation you kind of designed for inverse design. But a specific question from my side would be about the evaluation of the formation energy or the convex Hall for the oxides. So I think, like from the literature, it is well known that we have to do some corrections to the formation energy convex halls. So then how did you get this done for the vanadium oxide and magnesium oxide?
So that is related to the use of U corrections and the functionals and other technical details. And so I don't remember all the details, and maybe it might be too lengthy to discuss. And so I would like to refer you to the supporting information of our paper. But like you said, these spin states and then the root corrections, they need to be carefully checked and validated against the known experimental data and also other theoretical calculations in the literature. So we've done that. And we can email exchange if you need further clarifications. I'll be very happy to answer the questions.
Thank you. That is appreciated.
Thank you.
We have a question here.
So it's also about the inverse design part. So I guess that the algorithms you used require a lot of data, and concerning the vanadium oxides, I think the actual amount is quite limited. Did you use any technique to augment the number of data points?
Yeah. So as you mentioned, generative model is very data intensive, so you need a lot of data to train in the first place. And we did not augment the data in the first version of the paper. So by augmentation, I don't know what you mean by augmentation, but if you define it to be sort of data that are obtained by the substitution of the materials with other elements, then we did the augmentation. But if you define the augmentation by rotations and translations, and you can generate all sorts of maybe 100 structures for the same unicell, then we did not do that augmentation. Okay. So maybe referring to the first aspect. So there are about 100 vanadium oxide compounds in the Materials project database, and 100 of them is far not sufficient. So we augmented those vanadium oxide compounds by substitutions of the existing materials, and eventually we had about 10,000 or 20,000 structures for training. Was that your question?
Yeah, thank you.
Yeah.
Okay, so maybe I have a question, but in the meantime, so Elias is, are you ready? Yeah, okay. So maybe I can keep my question. Are you going to be staying for the discussion that we have at the end? I know that it's late for you, but that would be nice if you can.
Yeah, I'll try, but I'm not sure. But if you leave it as a text or message now, yeah.
Thank you. Okay, so our next talk is by Elias Vlieg from the Radboud University, and so the floor is yours. Sorry. Yeah.
Yeah. Thank you, Chairman, and thank everybody. I'm very happy to be here. The subject I'll be talking about is not exactly the same as what we've been hearing. I actually will talk about organic molecules in a slightly different database. And I am definitely by no means an expert in this field, but it's our venture into something, and I hope to tell a story that is relevant. So I'll talk about co-crystals, and the persons involved are listed here. So I'm the speaker, but I have to mention that Jan Joris de Vogelaar is actually a PhD student. He really did the work, and he defended his thesis about 2 weeks ago. So he deserves a lot of credit here. I will talk about 3 things: co-crystals, just to explain you what they are and why we use them. I'll talk about link prediction, which is slightly different from artificial neural networks, and then artificial neural networks. But if you have to summarize what we are doing, then you could say it's partner search for molecules. That's the name of the game. Now, what is a co-crystal? Well, it's a type of molecular crystal. We'll talk about organic molecules here, and they can crystallize in many different shapes and forms. And you have many multi-component crystals. So these are molecular crystals which have at least 2 different molecules, and there's a classification which I list here: solvates, salts, and co-crystals is one of them. And it's really defined as a molecular multi-component crystal in which both molecules are solid at room temperature if they're a single compound. So that's very specific. You think, who cares? But actually, people do care, because in pharmaceutical industry, this is something important, whether you have a solvate or not. So it has to do with regulations. So it is relevant. And so this is the particular class of materials that I will be describing. Now, why do you care about co-crystals? Well, in fact, so typically a molecule is something that people want to use: a drug, an agrochemical with a certain functionality. And if you crystallize as a single compound, it will have certain properties. But if you can find a different crystalline form, you can vary the properties and maybe make them more favorable. And that's the idea. So it's a nice route to change any type of property. And in pharmaceutical industry, bioavailability, how rapidly a medicine becomes available, is an important quantity. And I show here as the example of a drug where you have the solubility as a function of pH as the pure material, and with 3 co-crystal forms. And you see it's very different. And so this is a nice way to tune things. And it's nice because you keep the target molecule unmodified. So it will eventually do the same thing yeah, it's unmodified. And you have lots of options to play with co-crystals. So it's a nice space to explore if you want to change the properties that you're interested in. Now, and that brings to the question of how can you find the most suitable co-crystals and which co-crystals are possible. And normally this is done by experimental screening, trial and error, which is a big effort. And so you'd like to predict this. And this is, of course, an obvious idea. And several methods have already been in use for many years. And typically, what people do is they start with the chemistry. You have syntons, you have particular bonds, hydrogen bonds, van der Waals interactions. And so you can sort of rationalize what goes on. And this is something that works up to a point. But it's not a, you could say, a holistic approach. You zoom in on particular aspects of co-crystals, and what our aim was to see if we can use a database. Hence, I'm here to see if you can do similar things, but in a different way. And so our approach is to use, in fact, a very classic crystal structure database, the Cambridge Structure Database. I think it's one of the oldest around. It has well over 1 million crystal structures deposited, of which about 10,000 co-crystals. And I think it's been around for a long time. It's well organized, well respected. Many people use it. And one thing that's special, you could say, in the context of this meeting, it's not free. You actually have a limited free access, but you have to pay a fee. And so we're going to use this database, and we're not going to say we look at a particular type of chemistry. We're just going to look at the whole thing in one way or the other. And the whole thing is by doing, and this is the two approaches that I'll be describing. One is look at the network of the co-crystals, and then subsequently apply machine learning on this. So let's start with the network analysis and what is called link prediction. So the 10,000 two-component co-crystals that are part of the CCDC, you can describe as a network in which every co-former, that's the name of one of the two molecules of a binary co-crystal, is a node. And if there's an edge in between, then the combination is a co-crystal. So it's a nice way of representing all the co-crystals in the system. And there's a lot of network science, right? Networks are important. I mean, social networks, all kinds of networks. So you can actually learn from this environment about how you can treat this and how you can predict co-crystals using this knowledge. And so this is, so you could say, a crash course in network science, and it's also where my knowledge is exhausted immediately. But anyway, you have different network types. One of them is called monopartite, where every node can be connected to every other one. And Facebook is an example, right? Everybody can be friends in principle with everybody else. A different type of network is bipartite, where an example would be an author's article network. I mean, you can't mix them up. And so it's, you have two separate species, but there are many, many links possible. Now, in order to understand what you're doing and predict properties, it's important to know what kind of network you have. You could also have, of course, a mixed type. Now, so the network of co-crystals from the database was analyzed, and it's found that it's in fact predominantly bipartite. So that's something that's relevant to know, because that tells you what kinds of things you can and cannot expect. So it means you have two types of molecules effectively. And so you could type 1, type 2, and you know that type 1s will not combine. That's what you learn from this. So if you do predictions, you know what to look for and what not. And once you have this network, it also allows you to see if there are interesting, scientifically relevant groupings. From a chemical point of view, people say, okay, you have these things with syntons, hydrogen bonding or whatever. But here we can, so we don't look at the structure, we simply look at the network per se. And in the network perspective, you can look at how many co-crystals they share. Because if they have many shared co-formers, then probably they are similar in some fashion. And exactly what similar is, whether it's hydrogen bonding or not, we leave out of there, but we say this is a form of similarity. And so, yeah, it means that you can have similar properties. And this actually allows you to group coformers and it turns out to be meaningful. So here, well, the thing is a bit slower, I see. Here is, well, actually, this is a subset of coformers that have many partners. But if you do this grouping, then you'll find that there are sort of subclusters, and you see them on the right, where within a cluster you see very few edges. So internally, they don't bond together. So this is another example of this complementarity that I've been describing about different types of behavior. And if you zoom in into these clusters, you actually sort of retrieve the chemistry. So the Synton approach that people have been using, which is a valid approach, but you largely get this back simply by looking at how the network is operating. What you also find is that some coformers are extremely popular and some are not so popular. It's almost like a social network, right? You have these big influencers and some people are not so popular. This is how things are. Okay, now knowing this actually gives you a tool to predict possible coformers. In a social network, this is done by looking locally which friends there are. And so here the question could be whether John and Grace could become friends. Well, they have several mutual friends, so probably. So they probably will receive an invitation, whether they like it or not. LinkedIn has got these things, right? Suggesting friends for you and this kind of thing. So that's network science for you. And the same thing is true for co-crystals. So you can locally look at a network and how many coformers are there in common. Now we just learned that our coformers are bipartite. So in the example that I show here, naproxen and ibuprofen, well, they're the blue ones, not the pink ones. So actually those will not be linked, but you can ask the question whether this is a likely connection. And of course, the more coformers they have in common, the more likely this is. So this is put in a formalism, you get a score, and this is how you can do link prediction. You can look at missing links by looking at the local environment. Now this link prediction, well, we did on the entire CSD data, so all the 10,000 coformers, and well, you get a whole ranking, and so the top 10, of course, should be extremely likely. So that's making our life relatively easy. So these were predicted, and in fact, they were all synthesized. So without not too much effort, you can find 10 new crystals. Now that's as easy as it gets, right? I mean, you take the top 10 of your thousands of predictions, but at least that's a promising start. Next, we use the same thing for an actual drug, praziquantel, drug against some parasitic disease that you don't want to have. And that was already known in the system. It's a well-known drug, and 8 co-crystals were reported in the database. And so you can use the same machinery, and the machinery gives you a list, in this particular case, of 30 interesting possible co-crystals. And by doing experiments, 12 of them were found to be new co-crystals. So that's, I mean, it's not perfect, right? And also maybe we should try harder and everything, but at least it's a relatively straightforward way to find new co-crystals, but also will have new properties. Okay, that was link prediction. So now let's switch to artificial neural networks, the topic of this afternoon, after all. Now, because this is all nice and useful, but this obviously only works if you know something about the crystal, if it's part of a database. And suppose you have a new molecule, then what? Well, so link prediction is not going to help you there. And this is where, well, artificial neural networks could help you. And so, because what we learned from this network analysis is that actually there's a lot of information in there. It's a rational source. It's not just a random gathering of molecules. There's information in there. So if you can extract this information, that ought to be helpful in extracting, predicting useful combinations out of that. And so, this is what we have tried to do to predict co-crystals like that. And so, and we actually we saw similar discussion already in the previous talks. What you need, of course, is a descriptor that sort of mimics, the information you're looking for. Now, you don't know exactly what you're looking for, but at least it has to catch this. So this is not something which is trivial. Now, and of course, we don't have to invent these things ourselves. There's lots of stuffs out there. And so the PhD student tried many, many different things. But in the end, he selected things that are relatively common. I'm not the expert here, I already admitted. So two things that he tried and found to be successful are circular fingerprints and molecular graphs. GCN is an acronym I've seen coming around a few times more. So this is well known in this field. And this you can do for each molecule, but you can also make a merge form as a representation of the potential co-former that you're interested in. And then, of course, you have to train this. Now, the database is a beautiful case of positive results. You have 10,000 working examples. But if you want to train a artificial neural network, you have to also give negative examples. And experimentally, well, there's no database. I mean, people have locally in the logbooks failed experiments, but there's not an experimental database for that. And well, we've seen examples also this week of where theory, of course, can provide unlikely cases. And in our case, what we did is to use the link prediction that I just described to make a case, a data set of unlikely combinations. You can never be, I mean, so true positives do exist. If you make something, it's there. But you can never guarantee that something is impossible to make, right? Maybe if you try harder and slaughter a few animals on the way, whatever you do to black magic to make something, you can never be quite sure. But this is one way of doing it. Actually, I think that if we are going along this direction, it might actually be useful to also have a negative database, right? That you say, I failed. And of course, you cannot be sure, but with some likelihood, put it in there experimentally. Why not? If it's, you can deposit it without being blamed as being a loser or whatever, right? Then it's still useful information. And and for the rest, we use the standard tools that are out there to do the training. So Bayesian optimization, I think, is something that people use all the time. And so a PhD student has learned how to do this. So you have these descriptors and let the system do its magic, train it. And so here's an example how a training session works. So it's the usual cross-validation. You take a significant 90% of the data set, optimize all the different way vectors in there, and you can quickly get good prediction values with that. And the remaining 10% is then used for validation. And well, I think this is standard stuff for people in this field. And what we found by doing this is that these two descriptors that we used actually have very similar performances. There's no, so even though it's a different way of describing the behavior, well, the magic of deep learning somehow finds the same kind of information hidden in the network. And so you could see the graph on the right, precision, accuracy, and loss. Between the red and the blue, it's hardly significant. So what we in the end decided to do is to take a weighted average of both of them to have somewhat more robust way of looking at things. You don't want to have any particular bias. And so, so the accuracy of this training is of the order of actually 97%. So from the data set, it classifies the co-crystals. Well, 19 out of 20 are correct. So that's a nice score. But of course, that's the simple part, because this is the data in the structural database where there's a lot of information. So this is something that you would expect to be reasonably well. This is not what you want to use the system for. You want to use it for new predictions. And so to have a more serious test, we used a molecule carbamazepine, which is actually part of the data set. but that was removed. All entries were removed. Then the training was redone. So it's like a test case where you know nothing about the molecule and then see what happens. And we chose this because there was a recent quite careful set of experiments done where lots of co-crystals were reported, so we could have a direct comparison. And here I show lots of examples. In fact, I show here example 26 to 50 of the co-formers that we have used. And so you see lots of molecules here. Green means there's a good agreement. Red, there's disagreement. The number is the numerical value of the likelihood of forming a co-former. There's a check mark. It means that it was found experimentally in the reference that I refer to. If there's a cross, it was not found experimentally. And the crossed zeros are in fact the symbols that were not tested experimentally, but these were the negative data set that we produced ourselves from the link prediction. Now, this is far less beautiful than the 97% I showed you earlier, but this is a more realistic case. And here, the accuracy is about 80%. So it's, I mean, 80% is not bad, 8 out of 10. And there's also one case, you see 41. There's it's red because there's a prediction of the value is 1.0 and it was not found. And 42, it looks exactly the same, but it's green. And the reason is that for this particular one, we tried to see if we could find this co-crystal and we found it. So even though the other careful experiments found nothing, if you try again with different methods, you can, there are many different ways to try to produce co-crystals, liquid assisted grinding, and so on. So some of the non-found may be existing there. If you have a prediction of 1.0, you could have an incentive to give it a go. Now, and finally, and this is really what you want to do, this is where we applied it to what is called an active pharmaceutical ingredient, and this is what is called API. I mean, I've heard the acronym API several times here, but in the context that I'm talking about, it's an active pharmaceutical ingredient. So different fields have different, or the same acronyms, but different meanings. And ketoprofen, it's a painkiller, actually has really nothing in the database in terms of co-formers. And so, well, the whole machine is run. And so here you see prediction, 75 co-formers. They're grouped again here, and you see on the right-hand side the prediction. And so there is a certain class, I won't go into the details here, the green ones and the pink and blue ones, that say this kind of co-formers are likely. Now, we did not go through the extent of doing all of them, but there was one example which was particularly interesting, carbamazepine, which is a drug already mentioned earlier. Turns out that this predicts that you can have a dual drug. Now, this is not always what you want, right? Because one could do something, something else could do something else. So there actually are examples out there where you have dual drugs, but this is a nice example. So we went through it and we actually found indeed that this was forming. So it's a bit of a surprise, but yeah, this prediction lets you in the right direction. And we found 2 crystal forms, 2 polymorphs, because what I've been talking about now is simply whether you have the existence of a co-crystal, not whether you have different polymorphs or not. There's no, this is not something we put in the training at all. Now, since then, actually earlier this year, we did some more because you could say a real application. We was a pharmaceutical company said, well, this is interesting, looks promising, but okay, let's see how it really works. So they provided us, and I'm not allowed to talk about this kind of thing, but with proprietary compounds, which they had information, which is of course not part of the crystal structure database in Cambridge. And they said, okay, this is a compound, what would you predict? And we were comparing what they already knew experimentally, but what we've been doing. And what we learned from this real life comparison, but actually rather complex molecules, a bit more complex than the things you find on average in the Cambridge structural database, is that indeed this helps you. It's not perfect, but it helps you. So if you don't know anything, the artificial neural network is definitely a good starting point to have a few tries. But you should not expect everything from this. So if you have a few suggestions, go to the lab. If you find them, if you have real cases that work, you should immediately use this information. You should not say, oh, I don't want to do first principles. I don't want to do anything to do with experiments. No, use this information, both with the artificial neural networks, you can retrain. Even a few examples of highly relevant compounds can change the weighting factors and lead to better predictions. And certainly, as soon as you have one example, the link prediction approach will help you again. So, yeah, so you should not be too principled. You just want to get good results. And so combining these things is really something that works quite well. And that brings me to my conclusions. And so this is just an example of things that we have been doing. But what we found is that understanding the structure of the data set, the network, is important to get good results out of that. Negative data is important. And so I'm say plugging here for a negative experimental data set could be useful in the long run. And what we found is that co-crystal prediction is indeed is possible using link prediction and artificial neural networks. And you should really try to combine it with new experimental data because it helps you along the way. And of course, it requires a good database, which we have. And in the closing, I have a few more things that I want to say, just for the discussion, because this database is not free. And I think, who cares, right? I mean, if you pay like I say, fair price, but I think it's still okay. Because nobody's complaining about the CSD. It's not a commercial enterprise. It's reasonable. Industry pays more, users pay less, and it's reasonable. So I don't think, from my perspective, this is a black and white issue. We've been using the CSD for many, many years, deposit crystal structures, checked whether a structure was there. So for us, this work was quite nice. The fact that all of a sudden this, well, you might say boring, I don't know, but just a whole pile of structures, all of a sudden allows you to gain novel insight, something that is useful. You can really predict something that you couldn't do. So and so this is a nice example. Also, you could say a lucky case because this database happened to have the exact right information that you needed, which was very simple, just structure, but this is, it was all there. So this is a nice case. But I also was wondering, so again, for the discussion, is that we used, say, 10,000 data points. Now, our paper doesn't have 10,000 references because we don't do that. And so the people that deposited this in the past don't benefit directly from this. So you should wonder how you should do this, right? What is the incentive for people doing this? And even if you have data descriptors, DOEs and so on, would be 10,000 here. So I don't know how practical this is, something to think about. And so this is an example where we really learned what you can get out of such data. And I think that, as I said here, the data structure was perfect for our application. I think it's very useful to think about what you want to do with the data set, to design all the metadata. There's also discussion here. I don't know how much metadata you really need. You can say, I just put everything in there. Okay, but I think having some applications in mind might help you getting to a more trimmed down version that is maybe more usable than if you just put everything there. But this is open for discussion. So thank you very much for your attention.
Thank you, Elias. Is there any question in the audience here? Yes.
So on the future of this kind of machine learning of these co-crystals, so what do you see? Do you see that this will go into a direction where you enhance the database by entering other entities such as energy of formation or various others? Or do you think that it goes in the direction where you go against machine learning and that you try to have the molecular understanding of how the bonding works in detail? Could you speculate?
So definitely there's more to be done, right? And so, I mean, this is a tool, and so it will only become better if the database grows. So in that sense, you should keep using this, but you can do more things, right? Because this is only, well, checking whether they could potentially exist, but you can also add things. You could do crystal structure prediction, for instance, to make a more likelihood to be even more refined prediction. You might, but that depends on the metadata. But if the solubilities of the co-crystals would be part of the database, you could also add that, because in the end of the day, a pharmaceutical company is not interested in the co-crystal per se, but its properties. And so you could also add properties, but then you need already more data. And this is typically, well, scarcely available in this particular database. Yeah. But I definitely see a future also for other multi-component crystals, salts, solvates, you can do the same treatment, I think.
Have you actually been doing something with it? I mean, like improving it, or maybe do something which is called active learning, where from the prediction that you had, you made some tests to see.
Yeah. So the examples I showed you are exactly like that. So we made predictions.
Do you have a plan to continue that in some way to have something which is even better in terms of prediction, or?
Yeah. So the proprietary example that I mentioned is actually where we did this. So of course, we didn't have to do the experiments because they were done by the company, but they sort of, we said, we want to do this experiment, and they could give you immediately the answer. Works, doesn't work. And so based on that, we took the next step. And so this is, I think, how you can do these things. Yeah. But for the rest, yeah, the mechanism is the same. I mean, if the database is twice as large, you just train on twice the database, and it hopefully is better. But also, it's not clear whether the global approach, and because I saw this clustering, right? So we train on everything. Maybe, but this remains to be tested, you should focus on a cluster. You have a molecule which you can say, oh, this is part of this type of behavior. So maybe you should train only on a subset of the database, and maybe have higher scoring rate. We haven't tested that.
Mm-hmm. So maybe, as Tom was pointing, one step could be indeed to analyze the result, to try to see if there is some physics, chemistry to understand that.
So also, when he talked about this, he got lots of papers. So, come on, you have to do the chemistry, and I think it's true. I mean, chemistry that's nice, but even if you ignore the chemistry, I mean, Facebook is successful without actually. There's also chemistry using people, but it says, I mean, just connecting people, connecting molecules is successful despite. Just looking at the relations is already getting you there. So this is a different approach.
Thank you very much, Elias. So, given the time that is passed, we can slowly move to the next talk. So you can stop sharing your screen, and then Asaf can start sharing his. So the next talk is by Asaf Andersson from Materials Zone.
Yes, hi, good afternoon, everyone. Thank you for inviting me. And sorry for not being able to come over. So just a second, sharing my screen. Okay. Can you see my screen?
Yes.
Okay, thank you. So hello everyone, my name is Asaf Andersson, and I'm the CEO and the co-founder of Materials Zone. A bit about myself, I have a PhD in chemistry from Imperial College London, and I was doing research on photovoltaics a lot of years. Big part of my career was actually establishing and running a high throughput combinatorial platform, which I will show a few slides about. And before my undergrads, I worked for, before and during my undergrads, I worked for a couple of Israeli startups, working on networks and databases, and it's like a price comparison engine and security. So Materials Zone was established 5 years ago from the Nano Center at Bar-Ilan University in Israel, and it was incorporated a bit more than 3 years ago. Recently, we just concluded round A, and from what I've seen, I guess we are a bit a rare creature on this session. So another thing that I want to mention is that Materials Zone is a material discovery platform. We are in the session of the machine learning, but machine learning is just a part of the story here. So I think, you know, you guys all know the problems with materials data. This is what FAIR-DI is talking about. My story starts maybe, you know, a bit before. And I think, it sort of coincides, with the same arguments. And I think we can all say that, there are problems with materials data and research data. So it's not ready for AI ML. It's not exchangeable, it's not interoperable, so exchangeable between people and interoperable between software. It's not standardized, it's very difficult to collect, it's very expensive to generate and even to reproduce, and there is a serious lack of experts, and this is like, the meaning here is like researchers that knows both material science and data science, and this is the story. We also extend it a little bit to manufacturing, where we involve process engineers also at a later stage of the process. And this is really a critical part of the platform. So Materials is an AI/ML powered agnostic collaborative platform. On the left side, it covers accelerated research and development. So the idea, of course, is to discover new and improved and economical materials, to improve processes and scale up rapidly to production. On the right side, once we establish a manufacturing line, some companies experience failures and clients complaints, and many times it's related to the materials, and the idea is to go from the R&D to manufacturing and back in the same sort of environment, in the same language. So the platform's agnostic nature enabled to implement and apply, our solutions on multiple verticals and multiple domains. So the way the platform is constructed, we have like a data workflow and a collaboration engine, and we have the insight components, the artificial intelligence and machine learning component. And for manufacturing, we have a track and trending alerts and alarm component. And the idea is to have all sources of data connected together, whether it's like the lab instruments or existing databases, existing spreadsheets, data from publications, computational data, data from existing systems like MES and LIMS, lab notebooks, and basically to be able to capture everything that is happening on the lab floor. So the platform is funneling this information from all these sources, standardize it, normalize it, and provide the insights that are needed to get better decisions. So if you look on the flow of research, let me see if I can. So I split it to the three different players: what's covered by the material scientist, what's covered by the data scientist, and what's covered by the process engineer. And this is sort of to highlight, the lack of overlapping in expertise. But if you look on the story of the research all the way to manufacturing, then it's obviously starting from materials, and here we sort of bring materials descriptors. So we create like a repository of many materials, and we constantly enrich these materials with additional information, whether it's experimental or computational information, and we sort of tag everything, so it's having all the metadata in place. The next step is obviously mixing and preparing samples. These samples needs to be tracked. So each sample has in Materials has a unique ID, unique identifier, unique URL, and you can generate a QR code for it. Once you have the samples, you obviously go through a sequence of measurements, and the idea is really to create something agnostic. So we created a unique parsing engine that basically learns new types of measurements, and we support I think more than 200 files already, and we classify, the physical measurement, and sorry about that. We classify the physical measurement and the manufacturers, the type of instruments, model, and everything, and we can sort of bring measurements from various instruments from various manufacturers into the same data structure, which is really important for the next stage. Then the next stage, we created a unique engine for app development. So we have like all the backend Kubernetes cluster and continuous deployment. This is running on a Bouquet server, and we can very quickly create apps for specific workflows where our users can sort of digest whether it's like protocols of preparation or measurements data, and create sort of tagged data for the next stage. So it's generate observation protocols, and then the observation protocols are going into the machine learning engine. And here we provide the basic tools that can basically be used by any of the players. These are all web interfaces. So with a few clicks of a button, everyone can generate predictions, visualize the data using histograms, overlay spectral data from the same type of physical measurement, and find correlations between any parameter to any parameter. And the last step, which is sometimes, it's the first step for some of our users, is the manufacturing part, where we cover the track and training and alerts and alarms component. This is being facilitated also using multivariable modeling of the data, where we can basically predict failures based on materials data before they occur. So this is one example of the platform. This is sorry about that. So this is an example of the interface. It runs on any device, whether it's a mobile device or a tablet or a PC. You can use the camera to scan QR codes, and it immediately links you to the URL. If you have permission, you can log in into the specific sample or specific material that stands behind this identifier. And then you can quickly view all the data that was collected on this specific sample. You can, if you have edit permissions, then you can also edit it. And the platform constantly generates the provenance that is needed to track. If someone has made any changes, then everyone knows that who is responsible for good and for bad. So I'd like to talk about a few use cases. One use case is actually was a precursor to Materials On. So as I said, I was working on this combinatorial high throughput project. This project was funded by the Israeli National Nanotechnology Initiative and FP7. It started in 2011. It was funded until 2015, but continued until 2017, where I started working on Materials On at the end of this project. So this is a schema of all the kind of interactions, data interactions, software interactions, instrument interactions, device interactions, materials that happened in this project. So it started with fabrication. These are the black boxes here. So spray pyrolysis, past laser deposition, and sputtering. And then it went into a set of high throughput measurements using robots, using scanners. So it did optical measurements where it captured simultaneously total transmission, total reflection, specular reflection, EDS, Raman, XRD, IV curves, and sheet resistance, and many more actually, but it's not covered here. And then the data went into various pipelines of data sort of processing and distillation, and also modeling. So for example, this optical modeling server used to calculate band gaps and tail energy and theoretical absorption. And then you could also calculate nanometric thicknesses of thin films and combine it with data that came from the other instruments. And then basically the idea was that every step, it's still actually operational, every step that you do. You may create several layers of a device, and then you might go into some treatments and start the process again and again and again, and everything is sort of logged and accessible. And then we had the collaboration and the internal work on machine learning and modeling, EFT, and design of experiments, and it sort of went into in a loop and generated a lot of data and a lot of publications. One example that I want to highlight is this story. So we wanted to convince Rust to become a photovoltaic device. Everyone knows that bandgap is almost ideal, also for water splitting. But the charge separation is too bad, and we actually were struggling on all sorts of oxides of iron oxides throughout the first 5 years. So you can see here the Y is a figure of merit. It's not an amazing performance here, but you can see that the first 5 years was really bad. So chronologically, most experiments has failed. There was no really significant trend. And then one day we managed to complete basically the development of the platform and start using the machine learning. And then we did the next sets of experiments. So the blue squares that we see here were 2 months of focused machine learning guided research, where we actually managed to almost triple the conversion efficiency of photons to electrons. So this is what we see here. And the nice thing about it is that once we started to use the machine learning, we got better guidance on improving variance in the data and reducing repeated experiments. And then once we had that, we sort of made several iterations on the genetic algorithm modeling. This is what we used. And we solved the model, and we came with another recommendation for this last set of experiments. So we did this within 2 days, and we got more than almost 5 times better performance than the first 5 years. And this has really convinced us that we should work on something that everyone can use. So today, this data, part of it is loaded into Materials. So here you can see the correlation engine. You can see the photovoltaic performance and a few of the components that you control in the processing. So this is really a process function correlation. And we saw here that the most significant parameter was temperature, and we realized that actually sintering sort of was killing the samples, and this was counterintuitive as a scientist, because typically you will struggle to create pure crystals and you would sinter, and apparently sintering sort of cracked the samples and created shortcuts, and was, you know, a lot of damage. So a few other use cases that are running today on the platform that I can disclose is this AI for QD project. This is a collaboration with an Italian startup called Glass to Power and the Italian Institute of Technology. So the story here is basically a synthesis of quantum dots and salt gel roots, and then checking its application in various functions. So one is creating photovoltaic windows, another one is creating LEDs, and the third one is creating solar cells. So the quantum dots are synthesized in both Glass to Power and IIT, where Glass to Power would take these quantum dots and implement them within a polymeric matrix and create sort of solar concentrators, where the photovoltaic modules are located at the edge of the window on the frame. So they sort of need to find new materials and better particle distribution and reducing you know, poisonous materials. And in IIT, it's really a collaborative project, and both projects are collaborative. But there's like different groups that some of them synthesize the particles, and then the other ones take them to something that is not mentioned here, but optoelectronic characterization, and then to device fabrication and so on. Another recent project that we started is a collaboration with this Bar-Ilan University, Tel Aviv University, University of Maryland, and a couple of startups, and Saft, a battery maker, which is purchased by Total. And the story here is like a 5 years project on solid state batteries. We're also checking the replacement of lithium with sodium. So this has just started, and we establish here like all the framework for battery research, creating all sorts of apps to talk with potential starts and cyclers, and the basic fundamental materials characterization. Another project that was concluded and hopefully will go live fairly soon, but it's also already in public domain. This is the perovskite database. This is was sort of led by Dr. Jesper Jakobsson and Professor Dr. Eva Unger from Helmut Zentrum Berlin. They used Materials to create this infrastructure for data collection and dissemination of information of 44,000 photovoltaic devices. This is actually data that is harvested from the literature. They recruited 80 researchers, 80 volunteers, students, postdocs, some principal investigators from these institutes, where they all collaborated to bring almost 100 attributes for each device. And they created these dashboards that you can see here, and where each point is really a link to the specific publication. It's not live yet, but if you're interested to access it, you can contact Eva or Jesper. And the last use case, I think, or one before the last use case I want to talk, this is another example of some of the part of the interface of Materials, and the idea here is that really everything is connected. So as you can see here on the right, this is a sample page or a material page actually of a mineral. So each mineral has a chemical formula and physical properties, and sometimes an image, or if there's any other measurement. This was harvested from the internet. It's a work that we did together with Dr. Vinis Venagopal. And we have almost 3,000 minerals in the platform, where only 586 minerals holds the full information, means both the chemical formula and all the properties. So what you could do with this kind of data, and this is sort of demoing the machine learning prediction tool, is run regression analysis. So here you would choose a team, and then you could choose the protocols. We have chemical formula and physical properties. It's not shown here. Then you would pick a target parameter. So molar refractivity in this case is a desired function. So it's going in between 1 and 4, something like that. And then you could choose only the chemical composition. So this is only the elements that makes these crystals, these minerals. So here we see 3, sometimes it's a combination of many. So once this is loaded into the engine, it looks for the part that has both molar refractivity and chemical formula, and it splits the data set automatically into train and test set, and run simultaneously the 3 models, the linear regression, decision tree, and random forest, and it gives you the rank. So once you see the output coming, you could click and use a 45-degree plot, and here you can see how nice the linear regression works with it in this case. So as you can see, the train set help to predict basically the test. So they all fall on the same line here, which means that if you take the remaining 3,000 minerals minus the 586, you could predict the refractive index without any theoretical or experimental attempts. So for us, it's really reassuring and convincing, and this is can be demoed on many other data sets. The idea is that you can very quickly navigate between different data sets, and when you click on each pointer, it takes you to this specific sample or material page. Another thing worth mentioning is that sometimes, and sorry for not showing it here, but the protocols includes linked data. So if you use like a formulation, for example, and you mix a polymer with a mineral, for example, you could link to the material properties, and these will participate in the machine learning and correlation analysis, where the machine, like the human, would look for the linked information and bring it as data that will be used for the analysis and for the generation of correlations and regression models. So this is the manufacturing use case. The idea is quite simple, but it works in the same language that the data collection worked. So basically, any protocol that you generate, you can sort of visualize it as a function of time. You can select the specific feature. If you work in manufacturing, you can specify specification limits and control limits, and it will use the basic 3 or 6 sigma approach. And basically, the system will build a model in the memory that it sort of tracks the trends. And if it identifies something strange, it would shoot an email to the users where they know that something is going wrong, and they can act upon it if it needs to stop the production or just fix something as it moves. So this is really useful. A few last slides, if I'm okay with time. So this is the idea of basically data overlap or ontology or whatever you want to name it. But the idea that each lab would have a specific set of physical measurements, for example, that they do. And then based on this metadata, you would find overlaps between labs, and you would be able to suggest data. This is a bit more futuristic at the moment, so it's next step. And here you can see the metadata about the lab and the metadata about the physical measurement. It's a snapshot. And you can see the size of the square, and the color is sort of highlighting overlaps between specific types of measurement or within a specific lab, what kind of measurements they are performing. So this is the Materials on team. We are currently 12 and we are growing, we are hiring. We are scattered, so some sits in the Netherlands and some sits in Ukraine, and the rest, actually also one in the US, and the rest are in Israel. And this is it. So thank you very much for your time, and thanks again for the invitation, Gianmarco, and the FAIR-DI people, and open for questions.
Thank you very much, Asaf. Questions? Yeah.
Thank you. You showed many different things, and I just have a very specific question, because you showed the example where of the perovskites, where there was this massive data was assembled. Now, was this also then used to make a better perovskite solar cell?
So this is really premature, and this is something that we actually facilitate for the users. So it's really not online yet. It's still closed for this bunch of people, but I think if you contact them, then you can join this. So this the first step is concluded, and this is about to go online with a publication in a Nature article of everyone that is involved. So the answer is not that I'm aware of at the moment, but know that Materials on is sort of a platform that the users are using sometimes without us knowing exactly what's going on.
Okay, thank you.
Other questions in the chat? Okay, maybe one by me. Okay, so you didn't mention the kind of model of machine learning that you're using. Are you allowed to say a few words about that, or it's really some kind of secret internal to the company?
I think I can say that you know, the machine learning and artificial intelligence tools are, you know, known to everyone, and there is no specific magic, you know, with the algorithms. You know, I guess most of this forum experience, you know, this at some point or another. The important thing is the architecture around everything, and then the, you know, the interaction with the user. Obviously, you know, the being able to, you know, have the data constantly ready to run another iteration on the machine learning. Whenever you add another data point, whenever you enrich another material descriptor, you can always, you know, jump immediately and see, you know, what happened to the model. And this is, I think, the magic in this case. And you know, it's not about really the, I mean, if you consider the architecture around the algorithms, then yes, it's a secret, but but the algorithm itself, it's you know, everything that you know.
Okay. And in terms of the representation of the data, I mean, the featurization. So in my introduction, I was mentioning featurization as an important point. Is it something that you also consider important from the experience that you have, or is it also something that you do in a rather standard way, I would say?
So if you can give, you know, featurization in 2 words, and I apologize for not following.
So I was mentioning, okay, in the case where you go from a structure to a property, that you need to represent the structure in some way. You have to have descriptors. So I said featurization. It's the descriptors that you use for your machine learning part. So I guess that when it's the process, the descriptors that you have are, I don't know, the temperature, the pressure, stuff like that. Do you go beyond these things, or?
Yeah, absolutely. So we distinguish between a material and a sample. So a sample is made of materials, always, you know, predecessor samples, and this is all linked. And if it's a material, then we can constantly enrich the material with descriptors and basically add any kind of representation. So, you know, there we are really not limited by our knowledge. It's like whatever the users want to add on the material descriptor is immediately becoming a parameter that participate in the analysis.
Okay, thank you very much. I don't see any other question. And so for the sake of our coffee break, which was a bit short yesterday, we're gonna stop here and resume in 29 minutes.
Okay.
See you then. Thank you all.
Thank you very much.
Beetje merk is dat je dan zegt, hey, de chemici die komen dan, ja, de chemie gaan doen.
Okay, welcome back, everyone. So we're back from the coffee break. And so our last speaker of this afternoon session is Anubhav Jain from Berkeley, the Lawrence Berkeley Lab. So Anubhav, you can, thank you very much for waking up so early. And so, yeah, the floor is yours for the presentation. You can share your screen.
Okay, great. Is everybody able to see my screen all right?
Yes, we can see you perfectly and the screen is perfect.
All right, so thank you everyone. Very happy to be here today virtually and to tell you a little bit about this project that we've been working on called MatBench. In contrast to some of the earlier presentations you saw, this is not really about a specific machine learning algorithm or a specific problem, but rather about how do we actually compare machine learning algorithms? How do we measure progress over time as we invent more and more machine learning algorithms? So it's more of a meta study than a particular study itself. So my name is Anubhav Jain. I'm a staff scientist at Lawrence Berkeley National Lab. I'm also deputy director of the Materials Project, which I think was mentioned in previous talks. So in terms of the outline for the talk that I am giving today, in the spirit of some of the overall workshop goals, I wanted to give a quick introduction to the Materials Project to the people that maybe are unfamiliar with this resource. And I also wanted to talk about a new platform that we have in Materials Project called MP Contribs. And this is a way for you to submit your own data sets to Materials Project and have it be visible on the Materials Project website. So this also relates to all the FAIR principles of making your data findable and accessible, et cetera. Finally, the main topic of this presentation is about how we can benchmark different machine learning algorithms using consistent data sets and using consistent protocols. And so that is the MatBench project that I'll be talking more in detail about. So let me begin with the Materials Project and just give a quick introduction. You know, I think most people are probably familiar with the Materials Project, but just in case, let me give a little bit of an overview. So the core of the Materials Project is really a free database of calculated materials properties and crystal structures. So the URL is materialsproject.org, and currently it has data on about 150,000 different materials. This includes things like electronic structure, photon and thermal properties, and other properties as well, such as magnetic, ferroelectric, dielectric properties, et cetera. As Jean-Marco mentioned earlier in the overview of the session, we don't have every property for every compound, and typically as the properties become more expensive to compute, the fewer compounds we have that on. But we are working continually on trying to fill in the database and have full data on all the compounds. There's actually also a button on Materials Project where you can request that certain properties be calculated. So for example, the elastic tensors. And so if there are certain materials that you are particularly interested in, there's a button that you can click and that will automatically prioritize that compound to be calculated versus some of the other compounds. So most of the Materials Project is really calculated data. So it's been powered by hundreds of millions of CPU hours in these density functional theory calculations. I say most because, as I'll talk about later in the talk, there's also a contribution section where people have contributed experimental data as well. So in the Materials Project, the core data set keeps growing with time. So this is not a static resource. We only made this plot up until the year 2018, but over time we've been increasing the number of crystal structures, but actually for a while now, we haven't been increasing the number of compounds so much, but what we have been doing is changing the number of properties or computing more properties per compound. So adding band structures, adding elastic tensors, recently adding more magnetic properties, more piezoelectric properties, dielectric properties, et cetera. So both the number of compounds as well as the number of properties per compound is increasing with time. In addition to just the raw data sets, the Materials Project also has what we refer to as apps. There are many apps, as you can see on the left portion of the slide. And one of the things that these apps do is it actually helps you make useful comparisons and plots from the data set. So for example, on the top right here, you see a phase diagram or phase stability diagram chart, which really shows you what are the stable phases and what are the phase equilibria for a particular chemical space. You can make these for 4 elements. You can project them to get like an open element. And so there's a lot of useful functionality that you can do without having to write the code yourself. Also, I should point out that, as was brought up before, a lot of these analyses require some kind of post-processing analysis where we are correcting energies or we're adding reference energies, et cetera. And so by using these online apps, you can kind of avoid some of that process and have it all done for you. So in addition to the data itself, the Materials Project has many codes that it makes available open source, either with a Berkeley license or an MIT license. Those are both very open licenses. They don't require you to also redistribute derivative packages in a certain way. They're commercial friendly, so companies can use them, et cetera. So there are many packages like Fireworks, PyMatGen, Custodian Atomate, and Crystal Toolkit. One comment that I'll make about this is that Materials Project takes more of a philosophy of having many separate packages versus one overall Materials Project package. And in some ways, this makes it so that you have to install lots of codes and not just one code. But the advantage to this is that there are people that like to use some of these packages, but not others. So to take one example, PyMatGen is the code that, given a crystal structure, will generate input and output files and parse the output files, et cetera. And Fireworks is the code that will actually run calculations on supercomputing centers, regardless of what type of calculation it is. And we haven't merged these two into one package. They're separate packages. And so there's some people that use Fireworks, for example, with ASE, Atomic Simulation Environment, instead of PyMatGen. And there's some people that use PyMatGen but never use all the automatic features of Fireworks. They might use their own automated scripts or things like that to submit to the computer. So we have many separate packages that people can use. So I'll talk just very quickly about two of these. One of them is called Atomate, and this is our calculation workflows. This is what Materials Project uses internally to run all of the calculations that it uses for its data sets. And really what Atomate is the way to generate calculation workflow. So you give it a crystal structure, you might give it a few other parameters, like what kinds of functionals you want to use or what kind of settings you want to use for a calculation. And then Atomate will do all the work of transforming this into a workflow. So a specific object that tells you what calculations to do and how to connect the outputs of one to the inputs of the other. And then we'll also take care of running that on the supercomputer, parsing the results into a database, and helping you plot the results. So these now, we have workflows now for many different types of workflows. Right now, Atomate is really VASP-centric, I would say, but we've been working with John Marco's group to actually get Atomate released in the future as well, so that way you could do everything fully open source without having to buy any sort of license whatsoever. So we were working more on Atomate. We're actually working on something called Atomate 2, which is an even user-friendlier way of doing some of these things. But we're happy to answer more questions about that if you have them. More relevant to this session, another package that Materials Project offers is called MatMiner. And MatMiner is really a way to generate feature sets for machine learning. It doesn't do the full machine learning process itself, so it doesn't do the machine learning model. It really is a way to just start with a composition or a crystal structure or a site in a crystal and generate different types of features for that. So right now, there are more than 60 featurizer classes. So there's many different types of feature sets that you can do. And each of those feature sets can generate maybe tens or hundreds of features. So you really can generate thousands of potential descriptors using the MatMiner package. The types of features that you would want to generate really depends on what type of data that you have. So for example, in the yellow over here is a composition class. And this, just given any chemical formula, can generate different types of features, like what are electronegativity differences, like a one-hot encoding of the element fraction, a featurizer related to the Medema model for alloy energies. So there's lots of different types of feature sets that you can get just with the composition. If you have a site in a structure, so for example, in a previous talk in this session, we were talking about adsorbates on a surface. And if you want to know, for example, geometrical properties of the adsorbate, like how many bonds does it have, what angles are the bonds, what sorts of coordinations are the bonds of this adsorbate on this thing, and you want to describe that numerically, you can use some of these site features that will take any site in a crystal structure and tell you things like what's the coordination environment, what's the shape, things like that. There are also overall crystal structure features. So for example, we have the Ewald energy, which will tell you what is the electrostatic energy of a structure that has charges assigned to it, for example. So again, there are many different ingredients of features that you can use, and you can use these features in many different types of downstream machine learning packages, as I'll show a little bit later as well. So the Materials Project is used heavily by the research community. At this point, we now have 180,000 registered users. And so this seems to be increasing exponentially. It obviously can't keep increasing exponentially. So at some point we will see where it kind of levels out. But over the last year, there's been many new users and lots of data being downloaded through the Materials Project from all over the world. Oops. All right. So let me, and then finally, I'll just say that a large fraction of the Materials Project users are actually from industry. So about 10% of our users are industry users, about 36% are academia, and almost half of our users are actually students as well. So this seems to be a resource that many different people can use, all the way from the student level to the real industrial level. Okay, so with that, let me end the introduction to Materials Project and tell you about something we've been working on for the past few years called MP-Contribs. And this is a way to take your own data sets and disseminate them through the Materials Project. So what we wanted to do was to actually leverage the Materials Project to help build a larger community of materials researchers. So for example, the Materials Project has high visibility in the sense that if you go to Google and you search for molybdenum diselenide, actually the first result is from PubChem. The second one is really the original paper, I guess, about the crystal structure. But then the third link is actually the Materials Project details page for the molybdenum diselenide. So what that means is that when people are searching for various chemical compounds in Google, they actually see Materials Project results relatively high up, and they're likely to see that data set page that comes up for a particular chemical composition. So obviously there's a lot of data on molybdenum diselenide and all these other compounds that aren't computed by Materials Project, that are either in the literature or things that people are measuring in the lab, et cetera. So we really want to use this platform as a way to help get that data out to the people that are clicking this link in Google. So that's where MP-Contribs comes in. MP-Contribs is a way to allow the research community to contribute their own data sets to Materials Project. The way that it works is that currently on the left is what Materials Project looks like. There's a materials details page and it has all our calculated information about a material. On the right side is MP-Contribs. And MP-Contribs is a platform that looks a lot like other data contribution platforms, where there's different data sets that are contributed by different research groups. And then there's the actual raw data, if you click one of these data sets, as well as some plots and things and visualizations of the data sets. But then what MP-Contribs does also is it takes the data from these data sets and it displays them on the Materials Project details page on the appropriate material. So that when people are actually searching through all these compounds like aluminum oxide and they're looking for other information, they also are looking through, in a sense, all of these other data sets that have been contributed by the community. And there could be some data in here that is actually linked on the Materials Project page. So, the way that we envision this going is that, Google links to the Materials Project. The Materials Project tells you all the data that we have, but then in one section of the Materials Project called User Contributions, it actually goes to external data that has been contributed by the user community, in this case by DTU. This is Ivano Castelli. Francesco is one of Gianmarco's old students. So this will actually tell you all the things that not only we compute, but other people have contributed as well. And then you can actually get to the full data sets if you're interested in not just this materials information, but all the other information as well as links to the original papers as well. So let me just end that section by saying that MP-Contribs is open for contributions. So if you have a data set that you think would link well with the Materials Project that you'd like to disseminate via the Materials Project, definitely get in touch or go to mpcontribs.org, and then we will help you with that process. One thing that I will say is that MP-Contribs is really designed for smaller data sets, so megabytes to gigabytes. If you have very large output files, charge density files or wave density files, things like that, that's not really the type of data that MP-Contribs is storing. So for that, we would suggest something like Nomad or some of the other repos for more general data deposition that can really handle very, very large data sets. What MP-Contribs is really intended to do is to say that, hey, I have a whole list of band gaps for 100 compounds or something, and I would like those band gaps to show up on Materials Project. That's a very small data set, and that can easily go on Materials Project. The other real thing about Materials Project is that it should really link to the Materials Project compositions in order for it to be useful. So if you had a data set on lots of organic compounds, we don't really have organic compounds in Materials Project. So it's unlikely that someone would get from Materials Project to your data set if you didn't have, some links to Materials Project compositions. So with those two caveats, if there's anything that really fits here, we'd really be happy to help you disseminate that. Okay, so let me move on to the final topic of this talk, which is benchmarking machine learning methods using the MatBench protocol. So Materials Project is now involved in an effort to look at different machine learning algorithms and try and understand better how much improvement are we making as we invent more and more, modifications to the old algorithms, and also which algorithms seem to work better for which types of problems. And these days there are so many different machine learning algorithms coming out in the literature. Every single one of them obviously reports that they are doing the best on all the different problems that they test for the most part. And so it becomes really, really difficult to decide if you want to use a machine learning model, for example, which one of these should I use? Am I using the right one? Is there some other one that I should be using, et cetera? So we wanted to really help organize some of this information. And one of the things that we see in the literature today is that it can be very difficult to compare performance that it's reported in papers from different machine learning models. So for example, if you have 3 different machine learning models on the top, they're often tested on different data sets. So one of them might be tested on a data set that's formation energies and doesn't involve the crystal structures, only the chemical compositions, and it has 4,000 samples. And then the second model might be tested on a different database that has structures available and has many more samples and has some data filters applied to make sure that it's only stable compounds and no crazy structures, et cetera. And model 3 might just take everything and it's very difficult or unspecified what's happening. And then they also report the errors in different ways. So one model might use an RMSE error, one might use a mean absolute error, another one might use some kind of a validation loss. So it's very difficult to know which of these models is really performing better, and how do you do like an apples to apples comparison. So in our opinion, what's needed is something like an ImageNet for material science. I think many of you are probably familiar with what ImageNet is, but really ImageNet is a data set that started now over 10 years ago. And according to this article, it was originally published as a research poster in the corner of a Miami Beach conference center. But ImageNet has become really the biggest and most important image analysis machine learning data set. And there's always competitions now to see how much better we can do in terms of getting a good classification performance on ImageNet. So this is the set of images that were hand labeled to say that, okay, this is an image of a cat, this is an image of a dog, this is an image of a train, et cetera. And then machine learning algorithms would compete to see, could they automatically classify these images as well as a human. And ImageNet was largely credited with really transforming the field of machine vision, because it gave people a unified data set to actually compete on and make improvements on. So if you were to actually plot, so on the left is the plot of over time from the year 2010 to the year 2017, how well did the various machine learning algorithms do on this sort of image analysis problem, again, classifying images into cats or trains or whatever. So in the first year, actually, no algorithm did better than 25% wrong. And there was a lot of scatter between the different algorithms that existed at the time, the different machine learning algorithms. But actually what happened over time is that people got better and better at using this data set and figuring out what are the best ways to actually understand images. And you can see that over time, 2 things happen. First of all, the best models actually get better and better to the point where it's almost as good as a human these days. So the problem is essentially solved. And then you also see that the scatter between the models becomes very, very narrow, which means that every model actually does quite well. And there's nothing that does bad. In fact, the one worst model in the year 2017 is like much better than the best model in 2010. And so what's really nice about these sorts of data sets is that they decouple the data generation from the algorithm development, which means that all these groups submitting to ImageNet didn't have to spend the effort taking 100,000 images and labeling them by hand. They just started with the data set and they could focus on the machine learning algorithm. And In contrast, a lot of times what happens with material science, less so with some of these materials databases, but what happens is that in order to do the machine learning, you first have to collect the data, and that data collection and cleaning process, et cetera, can be the thing that takes up 90% of your time, and then you don't have a lot of time to innovate on the machine learning algorithm. Okay, so what we wanted to do was to have a benchmark like ImageNet for material science, which we called MatBench. And to us, the three ingredients were having standardized data sets that everybody always runs the algorithms on the same data sets, standardized test splits. So even within the same data set to make sure that you're training and testing on the same part of the data. And then finally, an online leaderboard that has, what's the best performing algorithm, and also details on how to reproduce the data yourself. So the online leaderboard not only makes sure that the results are reproducible, but also helps kind of, incentivize people to try and get on the leaderboard and say, okay, ours is the best for these tasks, et cetera. So currently, MatBench includes 13 different machine learning tasks. And this is different than something like ImageNet or some of the other standardized machine learning test sets, like the GLUE test set or Stanford question and answer data set. And that it's not just one data set and one test. There's actually 13 different tasks. And one of the reasons that we ended up with more than one is because there's a lot of diversity in the types of problems that material scientists face. On one hand, you have problems that are very small in terms of the data that's available. And on the other hand, you have data sets that are very large, and that the types of machine learning algorithms that are appropriate might depend on whether you have a small or a large data set. So in MatBench, for example, we have both small and large data sets. We also want to have different types of materials properties that are computed. And so we end up having many different data sets that we've compiled from the various parts of the literature, as well as from the Materials Project database. So as I mentioned previously, there's a lot of variety to the problems. So we tried to pick, of the 13, different types of applications. So this includes stability, information energies, electronic properties like bandgap and dielectric tensors, mechanical properties like elastic moduli, as well as optical and thermal properties. We span the range of samples, so everywhere down from a few hundred samples to over 100,000 samples, to again see whether certain techniques work better for different sample sizes. There are also different types of inputs. So some machine learning algorithms only work if you have the crystal structure. Other machine learning algorithms don't use the crystal structure information at all and only work with the chemical composition. And so we wanted to have some problems that included the crystal structure information, and some that you don't have the crystal structure and you only have the composition. And then finally, we had both regression and classification tasks. The other thing with these data sets is that we try to pre-clean them because a lot of times a difference in reporting is depending on how you clean the data beforehand and what data you get rid of. And so we document all the cleaning procedures for these data sets so that you don't have to invent your own cleaning protocol and then end up with different scores that way. And it also includes both experimental and computed properties. So it's not all just calculated data, it also includes experimental data. So if you're interested in the data sets themselves, we actually used MP contribs ourselves to contribute these data sets to Materials Project. So if you go to ml.materialsproject.org, you will see the MP contribs site for these data sets, where you can actually see all the raw data as well as be able to download them as JSON or CSV, et cetera. Okay, so now we have standardized data sets. The next thing we wanted to do was to just standardize the way that we define the training and the test set and have standardized splits. And we did something a little bit different here, so I just want to quickly explain what that is. So the most commonly used test split procedure that you're all aware of is that you have in blue here some kind of a training set that the model has access to for training, and then you have some kind of a holdout set, a test set, which the model cannot use to train, but then is used to evaluate how good the model is. And then typically what would happen is that in the training data, you would internally split that into a training and a validation set. You would use that to help do your model selection and your model hyperparameter optimization. And then when you're finally all done, you run it once on the test set. And then you don't go back and rerun everything because you already used the test set, so it's kind of burned. So that's a typical procedure. What we do is a little bit different, which is we basically repeat this process multiple times, because if you just have one test set, so going back to the previous slide, if you just have one test set, if this test set just happens to be a type of thing that your model does really good at, or has certain weird characteristics, then you could end up with strange algorithms being the ones that perform the best. So ideally, you want to have every data point have some chance to be part of the test set, so that every data point is used for the evaluation. So what we use is something called nested cross-validation. And so the first part of nested cross-validation is just like before, where you have a test set that's holdout, and then you have a training set, and then you again use the training set to update your model, and then you evaluate it on your test set. But then you repeat that process multiple times with different parts of the data being your test set. And so your training data set changes in this next part, so that you have to retrain your model using the new training data, and then you test it on the new test data. And you repeat this process, let's say 5 times, so that every single data point has had one opportunity to be part of the test set. You take the 5 different scores in this case, and then you average them together to get one score. So basically, it's a lot like the typical procedure, except now you don't have this thing where one portion of the test set might be really well optimized for. You have to go through and use every single data point as your test set as well. So there's been some research that show that this kind of nested cross-validation procedure is better at getting an estimate of your true error than just having one test set. So that's what we use in MatBench. Okay, so we have standard data sets. We have a standard way to do the test splits with the nested cross-validation. The last part we've been working on is this online leaderboard that helps you get reproducible results. So right now, there's a site that we put up called matbench.materialsproject.org. And this is really an online leaderboard of the different tasks that we've set up and what are the algorithms and how are they been performing on them. So here, again, those 13 tasks that I introduced before with the different sample set sizes going from small to large. And then this algorithm here is of the current machine learning algorithms that we've tested so far with MatBench, which one has been performing the best, and then what is the mean absolute error or the ROC-AUC for classification for that particular model. Here's a plot of the same thing. So the different tasks going from left to right, and then you kind of see these different algorithms and how they're performing. You'll see different characteristics, by the way, which I'll point out again later. But for example, CGCNN is a graph neural network, and you'll see that in the beginning, so these data sets on the left have low data points, and you can see that CrabNet has CGCNN has relatively high errors up here, but then down here where you have very large data sets, these are the 100,000 points or so, it really does much better than some of the other algorithms. And so you see these sorts of trends as you go through the data of which algorithms are working better on which problems. So in addition to the raw scores on MatBench and just showing you what's doing the best on each task, there's actually a lot more information that you can get on every single model that's been tested. So for example, you can get sample by sample predictions, which means that for every single data point that was used in the test set, so every single data point, you can see exactly what was the number produced by each model. And that's actually useful because if you want to try to run the models yourself, sometimes you want to know, like, am I using the same hyperparameters, the same version of the code? Am I getting the same results that was previously gotten for these models? And having these sample by sample predictions will help you verify that when you run the model, you're getting the same results as everybody else. Similarly, there's IPython notebooks for every model that shows you how do I actually run the model, like how was the model run in order for me to get these results, so that you can run the same code yourself, and the Python codes scripts as well as the IPython ones. And so also for every single model, we have a lot of metadata. So some description of the model, as well as like, what were the parameters used, et cetera, to run this model. So it really helps not only tell you what the best models are, but also helps you run them and make sure that you're running them in the same way as other people. Yeah, so as I mentioned previously, you can compare the algorithms overall, or you can look within each task. So this is, I think, the dielectric function prediction task. And you can see, okay, these are the different algorithms on the x-axis. And you can see, which ones are doing better, which ones are doing worse. In this case, AutoMapMiner Express seems to be doing well along with CrabNet. The dummy model is just a very simple model where you take the average of the data set and see how well that does. And so, yeah, you can kind of dig into each of these and get more and more information about the different algorithms. Okay, so far, what have we done with MatBench? We've looked at a few different models, and we are hoping to get more and more of these machine learning models evaluated with MatBench over time. The first one is a very traditional model, which is basically using a code called MAGPIE to generate the features. These are very conventional features, like what's the average electronegativity and standard deviation of electronegativity of the elements in your compound. And then just using a random forest model to take those descriptors and either make a prediction, like a regression or a classification prediction. Then in addition to that very traditional model, we also have an AutoML model called AutoMapMiner. And this is a lot like the traditional model, but just kind of amped up a little bit. So in addition to the MAGPIE features, AutoMapMiner uses pretty much the entire library of descriptors that's available in the MapMiner package. So I mentioned there's like thousands of descriptors that you can generate. So it actually does generate many, many, many descriptors automatically for a given problem, given the data set. And then it has automatic routines to try and clean up the features and reduce the number of features down so that you don't have correlated features and things. And then, so once you have a list of reduced features, it uses AutoML to actually try and figure out what is the best machine learning model for that particular problem. So AutoML has a list of potential models that it can try. So it might try, kernel ridge regression, it might try random forest, et cetera. It'll try different hyperparameters for all the different models. And it uses genetic algorithms to kind of search through the space of different machine learning models and try to pick the best one. So AutoMapMiner is also available open source along with the MapMiner package. So this is something that, given the data set, will automatically train and give you a model. In addition to these more traditional paradigms, there's been a lot of work in the last couple of years about deep neural networks and also showing very, very good performance compared to the traditional things. So there's one called CrabNet that works just based on a composition and will actually figure out, what are good interactions between elements and things. So for example, if you have aluminum oxide, what's the interaction between aluminum and oxygen that helps you get to a particular property? So there's one called CrabNet. There's one from John Marco's group actually called ModNet, which is actually very similar in spirit to AutoMapMiner, but instead of using these more traditional ways of doing things, it actually uses neural networks to do some of the feature selection, as well as some of the prediction as well. And then there's also crystal graph neural networks, which many of you are probably familiar with, the original ones, as well as modifications like MegNet. So these are all the types of algorithms that we've been investigating. Some of these are already in MatBench. So for example, there's random forest as well as the AutoMapMiner is already in MatBench. CrabNet was recently added to MatBench. ModNet has a pull request in review. So they've done the work needed to put it into MatBench, and we're just going over some minor things, and that should be there very soon, and you should see it on the leaderboard. And then finally, crystal graph neural networks, CGCNN is already in MatBench. MegNet, we did a previous test for, but then some of the data got corrupted or something. So now we're just trying to clean that up and get that also in MatBench as well. So, so far what we're seeing, I kind of hinted at this earlier, is that some of the graph neural networks work very well for large data sets, whereas some of the more conventional methods seem to work better for smaller data sets. And so what we're seeing here is the data set size on the x-axis. And then this is a normalized error on the y-axis. It's a way of normalizing the error so that the different problems, which have different units and all that stuff, can all be on a consistent scale. And so what we see here is that on the data sets that have, let's say, 600 data points, in the blue is the AutoMapMiner, which is a more conventional machine learning approach, seems to be doing the lowest error. And things like CGCNN and MegNet, which are more the deep learning models, they don't have enough data to really train well. And so they end up with a much larger error. But as you actually get to a larger data set size, what you see is that the slope of some of these crystal graph neural networks like MegNet or CGCNN, they have a very sharp slope, which means that they rapidly get better with increased data. Whereas some of the more traditional models like random forest or AutoMapMiner in orange or blue, they have a more shallow slope so that they don't really get as better as you add more data points as some of the deep learning methods. So what happens is that, around 10,000 data points or so, you have this like crossover between, it's better to use maybe traditional on the left side, but it's better to use deep learning on the right side. And certainly by the time you get to like 100,000 data points, 10,000 or 100,000 data points, that's when you really see the advantage of the deep learning methods. Now, I will say that new methods are coming out all the time, and we might see methods that really do well across the spectrum. For example, the ModNet platform that I introduced earlier, that also seems to do that one seems to do good across the entire range. And so as we see more and more of these models come out, we're going to see progress on this sort of slope. So if you want to use MatBench and you have a machine learning algorithm and you want it to show up on the leaderboard, you want it to show up on these plots and everything, what do you have to do? It's actually probably not as difficult as you think it is. You can really run everything in about 10 lines of code. So you have to install the MatBench Python package, which you can do in one line. And then here's the code that you need to run in order to have all the things that you need in order to submit your model results to us. So you import the MatBenchmark package, and then you basically initialize it. And the auto load is false because if you turn it to true, it will actually load all the data sets at once, and it's going to just take a long time to load all the data sets. So this will just initialize it without loading the data sets. Then this will iterate through every single one of those 13 data sets that I mentioned and load that particular data set up. And then each of these folds is one of the nested cross-validation tests. And then what you do is you actually get the training and the validation. You get the training data basically for every single data set. And then what you have to do is you have to implement the method that will actually, given the training data, initialize your model, all the hyperparameters and all that stuff, which you probably already have if you have a machine learning model. Then you get the test data, and then your model has to be able to make specific predictions for the test data. Again, you probably already have that. And then what you basically do is to just record what the list of predictions is for that fold. So as long as you have a model that can, given a training data set, can initialize the model, and giving a testing data set can make a list of predictions, this task.record will automatically generate all the reports that's needed for MatBench to do everything. So once you've recorded the results of all of your predictions, you can just export that to a file. And that file is what's needed in order for us to put it into the MatBench protocol. So then you just submit that file along with your model metadata to a GitHub pull request, and then we'll review the pull request, make sure it looks all in order. And then once that's done, we can put it on the MatBench website. Okay, so those are the 3 ingredients that we've been working on for the MatBench benchmark. So in terms of overall and upcoming goals, so we've introduced methods that will allow researchers to evaluate machine learning models on a standard benchmark. So we're not all evaluating things on different benchmarks. We also provide metadata and code examples that allow others to reproduce those models and use those models maybe a bit more easily because there are code examples of how to do it. There's specific results that you should get when you make predictions on certain data sets, and then you can verify that you're getting the same results. MatBench can also be a place where you discover new machine learning models. So you can look through and say, okay, for the type of application that I have, or for the type of data set size that I have, these seem to be the best models today that I have that are available in the community, and those are the ones that I want to try. And in the future, we do want to expand the type of tasks. So if you have suggestions for types of tasks that are missing in MatBench, we'd be open to adding more tasks, performing more meta-analyses on what types of algorithms work better for certain problems. And we'd also really like to just plot progress on these tasks over time. So just like you saw in ImageNet, where in the year 2000 and 2010, the performance wasn't that good and it was very scattered. And then over the course of 10 years or so, things got very, very good, and you saw the narrowing of the performance of different algorithms. We'd like to kind of see, does that also play out in the material science space? How much better do we get than 5 years ago, et cetera? So just to conclude, if you're unfamiliar with the Materials Project, it's a free resource that provides data and tools to help you perform R&D of new materials. If you are interested in contributing your own data to Materials Project and making more of a unified community, we encourage you to look at the MP Contribs platform. And then finally, if you are developing machine learning models or you're interested in testing different machine learning models, we encourage you to give MatBench a try. And we look forward to seeing your algorithm on the leaderboard as well. So with that, let me stop and thank all the people that did all the work and contributed to this. So Alex Dunn is a grad student in my group who really set up all of MatBench and did a lot of work for the MapMiner package. Patrick Huck is really the one in charge of MP contribs. So if you do end up getting in touch about MP contribs, you will definitely get to know Patrick very well. And then Christy Pearson is the director of Materials Project. If you're interested in any of the slides, they're already uploaded to our group website where you can click the slides button and it'll have all the slides. So with that, let me stop and take any questions that might have come up.
Thank you very much, Anubhav. I'm looking at the audience to see. Yeah, we have questions in the audience.
Very impressive developments. I was wondering, you mentioned steels, and if I think of steels, then you can think in terms of compositions of alloys or compounds. But if you also mentioned that you can evaluate the hardness and the elastic constants of steels. But the elastic constants of steels are typically also very much determined by microscopic properties at grain boundaries, precipitates, and all these things that people took hundreds of years to develop. Is that in any way included in this, or are you only looking at alloys and compounds?
Yeah, so that's a great question. You know, the steels have many descriptors apart from the composition or crystal structure, et cetera, that completely change the mechanical properties of them. So the particular steels data set in here was from Citrine Informatics, where they had a bunch of steel compositions. And I think that, I don't remember all the details of that particular data set. I do know that it doesn't have anything like the microstructure size or anything like that. I just wanna see if I can bring that up really quickly and see exactly what's in there. Give me 1 second. Yeah, I think that data set just has yield strengths as a function of composition. And anything about like microstructure or grain boundaries or initial dislocations or something that affect the yield strength are not in there. So, you know, with machine learning, there's sometimes the case, right, that the input data doesn't have all the information that you need to actually really predict the output data. And I think the steels data set is one of those cases where it's really just the compositions that were measured along with the yield strengths and doesn't have the actual microstructure information included in the data set.
If I may, a similar question relates to interfaces, because also for interfaces, it depends very much on the interface is usually even the device. So is that in any way to be included in evaluating properties?
Yeah, so right now it is just you know, bulk compounds and properties. So there aren't any interfaces in the current MapBench test set. I actually am not familiar with a good interface data set that we could use and incorporate as part of the MapBench test routine. You know, the machine learning methods typically work on bulk structures and aren't tested on interfaces, and I'm not sure what might be a good data set to use there. So if you had actually any suggestions on what might be a good interface data set to use, that definitely would be an important contribution to MapBench, but I just am unfamiliar with what would be a good data set there.
So I'm going to give the word to Luca, but just one short comment on that. I mean, at one stage also there is descriptors that need to be defined for interfaces or for whatever other data sets. So there's also a lot of work to be done there. So, but I was going to bring the problem of the descriptors in our discussion afterwards. So I give the word to Luca.
Hello, can you hear me?
Yeah.
We can.
Okay. So hi, Anubhav. I have a bit of a technical question on this nested procedure in MatBench. So it is certainly good for benchmarking the algorithm, but I wonder which model one is actually benchmarking, because at every iteration, new test set, you will have a new model and then you average over different models. So the question is towards, okay, I done a benchmark and now I want to use a model to predict something for a new material. Which one I should use? Or even worse, how do you know that one is not hyper optimizing on each test set? Because you know the data. This is the case every time you know everything about the data because they are completely public, and then you say, okay, my algorithm is performing very good on the test set, but you knew the test set, so you are free to hyper optimize on that.
Sure. Okay, so let me take the first problem of, now there's 5 different test sets and 5 different training sets. How do you know which one to use, et cetera? So there's 2 things. There's, for the purposes of scoring the algorithm and getting an estimate of how good the algorithm is, and then there's finding the final algorithm that you use to make predictions for your application domain. So the purpose of scoring the algorithm, you have 5 different scores, one for each of the different nested cross validations, and then you take an average and a standard deviation. So the average score is what's reported on the website of the 5 scores, and then the standard deviation you can use as like a bit of an error bar. So that's that part of it, which is just scoring the algorithms. And then it's like, of the 5 models that you've trained, which one do you use on the final application? Actually, none of the 5. You would want to retrain your model on the entire data set, including the test set. And then you actually use that for going forward with your actual predictions. So that would solve the problem of just having one model for doing predictions. You just retrain it on the entire data set. In terms of hyper optimizing on the particular MatBench data set, it could potentially be a problem in the sense that you could imagine writing an algorithm that just memorizes the entire MatBench data set and given the input, just repeats what the output is, right? Because you have access to the test set. We didn't hold out any of the test set ourselves through an API or something that you can't access. So that is a possibility. What I would say is that in practice with some of these other test sets, other machine learning benchmarks, it hasn't been so much of a problem. There have been some papers actually that report that on some of these other machine learning benchmarks, that over time, some of the algorithms might be somewhat tuned to these particular things in the test set. And if you start to modify the test set a little bit, the rankings of these things, well, the rankings actually stay pretty consistent, but the actual numbers will actually change. So, in theory, because the machine learning model is only being trained on the training parts of each of these sets, and it's only being tested on the testing part of these sets, it shouldn't really be too much of a problem of this sort of a data leakage. But again, if you want it to be, if you really wanted to hack it, you could actually just memorize the entire MatBench data set, write an algorithm that spits it back out at you, and then you get a perfect score. And so again, in practice, I think it's been less of a concern over the last 10 years or so as we see on these other benchmarks, but it is something that can definitely creep in, especially as this thing gets older and older and people hyper optimize more and more. So I think it's just something that we have to be careful about, and maybe every couple of years, introduce a new test set or something and just re-rank these things to make sure that things are staying consistent with similar but different test sets.
Yeah, or has some kind of blind competition in which the final test set is held secret, like this.
Yeah, exactly. But
every now and then, because you can do only once for one test set, right? The moment it is known, then you can do it every time. And then.
Exactly, yeah. But even the blind test sets, you have to limit the number of times people can run the algorithm on the blind test set, right? Because otherwise people still find ways to hack the test set, where if you're allowed to evaluate your
that would be
score,
one shot.
Yeah,
I mean,
yeah.
On Kaggle is one shot. You are allowed to submit once and you get your score. When you're sure. Yeah.
Yeah, so they have like 2 blind test sets often, right? Where one you can kind of access a few times, and then one that's like, okay, this is your final score, and you don't get access to it. So you can also set up something like,
public, private, and so on.
Yeah. So these are all good suggestions. I think we're still in the beginning stages of some of this, but as we move forward, and if we're seeing evidence of this sort of hacking, then I think we'll have to move to more strict protocols to make sure that people aren't actually designing the models specifically to the test set, but are actually solving the actual problem itself.
Yeah, we have one question here.
I have a question about MatBench part. I think for most machine learning package, there are validation inside the model. And I'm wondering if there is a validation for the random forest. And if there is, what's the scoring method for it?
Yeah, so to be honest, I'm not sure that I understood the question. So do you mean in terms of training the hyperparameters? Like what is the validation set used for training the hyperparameters of these models? Or for, is that what you're meaning? Like the internal hyperparameter training, what's the score that's used for that?
Yeah, I mean for the random forest, there are hyperparameters. Sometimes we can use grid search for the hyperparameters. And through the article, I didn't see you talk about the grid search of the hyperparameters for the random forest.
Yeah, so the MapBench package itself just gives you a training set, and then you are free to do whatever you want to optimize your model with that training set. So you could split it up into a training and a validation set, and then use the training set to pick your model, and then use the validation set to update the hyperparameters, et cetera. So if you want to, you can follow that procedure where you use grid search, et cetera, to do it. And
I
that's
think he was referring to Automat Miner, if I'm not wrong.
Oh, I see. Okay. So how does Automat Miner do the actual search? So Automat Miner takes your training set, it splits it into an internal training and validation set, and then it uses that uses a library called Teapot to actually do a search of the hyperparameters as well as the model itself. And then Teapot is the AutoML package that actually searches through everything using your training set. So it uses genetic algorithms. So rather than using a grid search, which is very expensive, and then you have to try every single combination, it uses genetic algorithms to try and do it a little bit more efficiently and try to get to an optimum with less time. So with Automat Miner, there's actually a setting that says, how long do I spend trying to optimize hyperparameters? And so you can spend just a little bit of time, in which case I'll do a little bit of a genetic algorithm, try different hyperparameter combinations, and then give you the best result that it has. Or you can say spend 12 hours trying to look at hyperparameters, and then it will run this optimization process a bit longer and give you potentially a better model. I don't know if that answered the question or not.
Does that answer the question?
Yes, thank you.
Okay.
Thank you. So, yeah, we have one question there. Sorry.
Yeah, thanks, Anubhav, for the talk. It's just a follow up on Luca's comment. Maybe it's, I was also thinking about the fact that indeed the idea about what is the final model when you do this benchmarking is like an important point, because I agree it's sometimes confusing with this nested k-fold. And so maybe I was just thinking that maybe adding like the final model to MatBench could be a nice thing to maybe see in the future or anything to make it available somehow, but trained on the whole data then, and not just on the separate folds.
Yeah. So currently the MapBench was intended mainly to be more of just like, here's a ranking of the different algorithms, and if you want to know how to do the entire thing, if you want the model itself, go to like the model webpage and get the thing. And then the MapBench itself shows you the training on the different folds, like it shows you the code for training on the different folds, and then also so then you'd have to you'd have to rerun that code on the entire data set and then get your model out, right? So it wasn't a repository of the actual models themselves. Now there's someone named Logan Ward at University of Chicago that was working on actually having a repository of machine learning models. And I'm blanking on what the name of this resource was, but it was intended to be a repository of the model files themselves with all the hyperparameters all serialized and everything, so that you could just load it and use it right away. So what I think we would want to do is to try and maybe work with them because they already have set up a repository of different machine learning models. Let me see if I can find it really quickly and put it in the chat. A DL Hub, yeah, someone put it in the chat already. DL Hub is the name of what they've been working on. So maybe what we can do is in MapBench, just put a link to DL Hub where you can download the final model files and then just be able to use it out of the box. Sorry, Luca, if that was also what you were referring to, I just didn't understand, but I think maybe this clarifies a bit more. Yeah.
Yeah, thanks.
Okay, thank you. I don't see any other questions here in the audience. I don't see any in the online. So maybe we can move. Yeah, first, let's thank Anubhav again for the very nice talk and the answers. So we have now 2 speakers left, I think. So we have Asaf, at least last time that I was checked, he was there, but I don't see him anymore. So there's only you left, Anubhav, among the speakers. So for the discussion here, I wanted to maybe bring two things. One was actually is coming from the discussion that we had with our experimental colleagues. So they would be happy to see some success stories about using machine learning to predict something, or and so far most of the examples that we have seen are essentially to speed up the DFT calculation, and in a sense, MatBench mainly also goes in the direction, though. I mean, you showed that there are some of the databases were experimental ones, but usually the experimental ones are smaller. So those are those in which we make the biggest error. So I don't know if among the people still here, you have an example that we can show to our experimental colleagues where really using machine learning was a breakthrough or something really very helpful to, you know, to give success to one of the projects. So apart from speeding DFT, that's essentially the main application that you all see for, I mean, I think that, you know, the example that Yusung was showing where we can go in the direction of these generative adversarial network, for instance, could be a way to get success. I mean, we have seen from is that, first of all, it's not very easy. And from the example that he gave, he only had something like the stability, and it was not a full success. So maybe the amount of data that we have is not yet sufficient to go to something like that. So.
I may come back to you on this in a year or so. So we just finished a screening project where we were looking for new channel materials for oxides in transistor channels, and we're currently trying to create these materials, create actually transistors out of them, and test whether this happens. And these materials are actually being predicted after DFT calculations, training machine learning, and then developing new candidates. But now we have to do the actual experiment, and that is tough work.
No other examples? Okay, so then maybe I can bring my second point, which was about the representation. So we have seen that, I mean, the way in which you present the structure, and also in the case of MatBench, this is something that you didn't highlight, Anubhav. So you showed that the different methods have, you know, you presented them in terms of the classical random forest and so on. Then the neural networks with the convolutional graph networks. But there's also the way in which you represent the data that is important, and especially, I mean, when I think about again this these generative networks, what we want in the end is that to predict a structure or a composition. And so, what is the best way to represent that? Did we already achieve some kind of agreement about that? So yesterday we were discussing about SOAP and then ACE. Sorry, is there other ways to represent things that are found to be more appropriate than others? Yes, Anubhav.
So regarding the topic of descriptors and representation, you know, what seems to me to be happening is that as you have more data points, the less important it is that you upfront come up with a good descriptor, because the layers of the neural network will learn your descriptors for you. And so, you know, I'm not sure that we've come up with the best descriptor, but as the data sets get longer or get larger, it might become less and less important for us to come up with the best descriptors.
It depends it depends for what, Anubhav, because precisely, I mean, with you know, with Automat Miner, we have a huge amount of features, and so you're perfectly right with respect to that. But now let's say that you want to optimize. There was the, you know, in the talk of Yusung, he was presenting this global optimization or the generative adversarial network, where what you want to do is to achieve one specific property. What is the structure that you need to create? And since, I mean, what we would do in the case when we use the Automat Miner, we would be able to say, oh, if a material had these features, then it would have this property. But we aren't able to say which material has this feature. So this is why I'm asking the question.
Yeah, I mean, for that, you know, this is still a tough problem. I've seen people have a second model, right, that takes the descriptors and tries to turn them back into a crystal structure, right? So you end up with two models that end up needing to be used. But yeah, it's still an open problem as far as I know, right?
Someone else wants to comment on that?
Well, so in my case, I just only use the composition as a descriptor, because I want to search for a certain composition.
But so how did you represent the composition?
Oh, my composition is just a weighted average of the weighted composition vector. That's
So you have a
nothing else.
vector with the
I just have like
number of
12 elements, and my first number is the amount of element 1, and the second vector of the second entry is the amount of element 2. That's just.
But then you have to do this what was called a global optimization in that case. So that means that you have to search that I don't know how many elements you consider.
Yeah. So I mean, I didn't talk about this, but it could have been in this session as well, right? So basically, I have a 12-dimensional element space. So we did a pre-selection on the elements, and I calculated the properties, 5 properties effectively that I'm interested in, for all the primary and binary oxides. So I take 1 element oxides and 2 element oxides. So three elements, right? So 2 elements and oxygen. And that basically I developed until a database of 4,000 materials, amorphous materials, which I then use to generate models that predict properties of arbitrary complexity. And then I use minimize an objective function that tries to kind of improve, or let's say define the optimal candidate for all my properties at the same time, because I don't just want to tune the band gap or something. I need to kind of have 5 properties in the right range at the same time.
Yeah. Other experience, maybe? Or the questions that people want to bring about these machine learning models?
So yeah, I think in the case of inverse design, the feature choice will be much more important than in the direct problem, where it's of course much less important, because if you have more data, then it doesn't really matter. But in the reverse, when you do generative modeling, I think that case is very tricky, and I don't know. I mean, I think it's still somehow an open question to see how we could.
Yeah, I mean, in the video that I was showing where, with the faces, if we were able to find this latent space in which we can say, okay, I'd like this material to be more conducting or more transparent or whatever, then it would be super cool, I think. But indeed, it's still a very open and difficult problem.
You have seen some examples in the first talk, but they were quite.
But it was
limited.
about stability mainly, and so we could see really two things, and so.
I mean, limited in composition.
But when you have the faces, people, I mean, I showed the example of the women man thing, but they have something about also different kind of thing. They can make the people younger, older. They can make their change the color of the eyes, the color of their hairs. So they found in this space of the faces, they found very many direction, and so it would be interesting to have something like that for materials as well.
And also the big limitation, I think, in my opinion, will be the amount of data we have with respect to what they have for faces in our material space, which is more limited.
Yeah.
Well, I've also seen that some properties are much easier than other properties. Stability, in my case, oxides, almost, I mean, with very easy to model that correctly. Other properties, things that effectively measure electronical conductivity of an amorphous material is way harder to model properly, and you have much more noise, and even gaps is also already way more tricky to model properly. So it's a tough problem, and per observable it's differently complex.
Is there any other point that people would like to bring in this discussion about the machine learning, where we should go? So, I mean, there's there's a proposal by Luca for a SECAM workshop. Anubhav. Yeah, I just go finish my sentence and then I'll leave it to you.
Yeah, why don't you finish it and I'll go after you. Go ahead. Yeah.
Yeah. So, well, Luca is proposing a second workshop in order to find similarity between structure, and this also, in a sense, goes in the direction of the representation of the structures, because to find some similarity, you need to find some representation of the structure and then measure the distance in a sense. Yes, Anubhav, please.
So yeah, just in terms of other topics, one specific problem that we ran into recently in our group is we were just interested in investigating these GANs for materials prediction, and there have been many people that have been publishing crystal structure GANs for doing various things, and many journal articles have been published. But what we wanted to do was to actually say, okay, let's just try running some of these other methods first before we try and invent our own and just see how these things are doing. And what we found is, I don't remember the exact statistics, but let's say there were 5 things published, code was actually available for 2 or 3 of them. The rest of them would say code available on request. And then, you contact them and they say that the code's not ready. And so, of the 5, we can actually get code for 2 or 3 of them. And then of the 2 or 3 that have the code, only 1 of them is actually installable. And the other 2 or 3 just are broken. And so of the 5 things that are available in the literature, you can actually just try 1 of them. And the other ones are just inaccessible. And so you're kind of forced to it. So I just wanted to put out, is there something that we can do as the leaders of the community or something to try and improve on these statistics and try to make it so that, we can at least try and run 70%, 2/3 of the things that have been published out there and be able to try it. So yeah, if any suggestions would be welcome on that front.
Yeah, I mean, this morning there was Giovanni pointing to the FAIR aspect of the workflow. So sharing the workflow. I mean, what you're suggesting here is sharing the algorithm to do this GANs. I think it's important indeed.
Yeah, and we talked about the DL Hub earlier, which I think could help with some of this stuff. Which if it's on DL Hub, you at least have some file that you can be runnable. But I think it's better in the computer science community in the sense that when people publish things, you can actually run them, and it's more of a requirement. It's not like you can just be like, "Hey, code available on request," and still be able to publish. So I don't know if people are for being strong, taking a stronger position on this, or whether it's something that we just kind of leave alone, and hopefully the community will sort itself out by having more tools and things to make it easier for people to do this.
Are we done? Okay, thank you very much to everyone, especially to Anubhav for waking up so early. And so we'll reconvene tomorrow. So as you have seen, the morning session starts a bit later than usual. We're going to be starting at 10:15. And also there's a slight change in the afternoon. Unfortunately, the chair of the afternoon session has some medical issues, and so he cannot participate. And so basically all the talks are, all the session is shifted by 15 minutes, the introduction being removed. Okay, so see you tomorrow at, at 10:15 CET. I cannot give that in all the different times in the world. Okay, thank you all very much and see you tomorrow. Bye.